Good morning everyone, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing amazing. All of you guys are doing great. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know in the chats with some fire emojis. Quick. Everyone. Everyone, people. After completing the today's session, I'll share the combined PDF of part 1 and part 2 together, okay? You need not to worry about that. You need not to worry about that. So quickly, let me know in the chats. So my dear students, as you all must be knowing, in the last session, we took class 11th Physical Chemistry part 1, right? And today it's going to be class 11th Physical Chemistry part 2. So basically, after completing the today's marathon, our class 11th chemistry will be completed, right? Class 11th physical is done, class 11th inorganic is done, class 11th organic is done, right? Similarly, class 12th physical is done, class 12th organic is done. We are left with only one marathon, that is going to be class 12th inorganic, right? Which will happen in the coming week. I mean, in this week itself. Perfect? Perfect, people? Right. The session will be for how long? I don't exactly know. Till we complete all the chapters, I'll be here. Yeah? So how many of you are done with the part 1 of this particular marathon? How many of you are done with the part 1 of this particular physical chemistry class 11th marathon? Say it in the chats once. I want to see it. Okay, I think majority is done with. I think majority is done with part 1, yeah? That's great. That's great. That's great, people. Yes, PDF I'll be sharing once we complete this one, right? Then I'll share the combined part 1 plus part 2 PDF with you after the session. Okay? I would want you guys to call up all your friends because we are now going to start. And let me exactly tell you which all chapters we are going to cover today. We'll start with atomic structure. We will start with atomic structure, then we'll go to chemical equilibrium, then we'll go to ionic equilibrium, and then your thermochemistry part. Yeah? What about the P block? P block will be done in class 12th inorganic chemistry marathon. Okay? P block will be done in that. Perfect, guys. So I think we should start the session. Just give me a second and I'll be getting the slides over here. So first of all, have a look on this particular slide. In the last marathon, we were done with mole concept, we were done with redox, we were done with thermo. Today we'll start with atomic structure, then we'll go to chemical equilibrium, then we'll go to ionic equilibrium, and after that, it's going to be thermochemistry part, right? This is going to be the session flow. This is going to be the session flow. And I hope all the things which I've discussed in the last marathon, I hope all those things are absolutely clear to you. I hope that. So are you guys ready with your pen and paper? Are you guys ready with your pen and paper, guys? Quickly in the chats. Quickly, let me know in the chats. Are you all ready with your pen and paper? Yes, you can see this session for VIT as well. Absolutely, why not? Because the syllabus is same, the level of the examination is same. Perfect, guys. So let's get going then. Let's get started with the first topic which we are going to cover in the chapter Atomic Structure. That is going to be Planck's quantum theory, right? Planck's quantum theory. Let's exactly see what this Planck's quantum theory is all about and what kind of questions can be asked from this Planck's quantum theory. My dear students, one statement which you just need to know. As per Planck's quantum theory is concerned, as per your Planck's quantum theory, I must say, as per this particular theory, energy is transmitted in the form of small packets. Energy is transmitted in the form of small packets. And those small packets, you already must be knowing, right? So let me use the plain slide over here. I'll make you understand what exactly it's all about. See guys, for example, over here you have got the energy source. It is the source of energy. It is the source of energy. And I'm assuming the source of energy, it is emitting radiations. Basically, it is emitting energy in the form of radiation. It is emitting energy in the form of radiation. As per Planck's quantum theory is concerned, this energy, this radiation, it consists of small packets. It consists of small packets which have got a definite, a discrete amount of energy. These small packets over here, if I talk about one small packet, as per Planck's quantum theory, this one small packet, this is something which you call as quantum, and a lot of these small packets you call as quanta. So basically, I have taken a source of energy which is emitting energy in the form of radiation. As per Planck's quantum theory is concerned, this energy, right, it is transmitted in the form of small packets. It is transmitted in the form of discrete packets which have got definite amount of energy. And my dear students, you will be calling these discrete packets, you will be calling these small packets as quantum. And a lot of these small packets is something which you call as quanta, right? This is point number one. Point number two. My dear students, in case of light radiation particularly in case of light radiation, imagine this is the light radiation over here. Imagine this is light over here. Now, if this is the light radiation, it will be also, it consists of small packets of energy as well. Particularly in case of light radiations, this small packet over here, you should be calling as photon. So in case of light radiation, the small packet, right, which carries a particular amount of energy, you call that as the photon. Okay? Now comes the point. Let me tell you, energy carried by one photon. Energy carried by one photon. It is always equal to h nu, where nu is the frequency of light. I'm pretty much sure you all must be knowing, if I talk about frequency, nu is equal to c divided by lambda as well, right? You should be knowing this. I believe you know it. Nu is equal to c divided by lambda. So what is c? C, it is speed of light, 3 into 10 raised power 8 meter per second. What is lambda? Lambda is the wavelength. It is the wavelength of the light radiation. So my dear students, I can say energy carried by one photon is equal to h nu. I could have said it like this as well. Energy carried by one photon is equal to hc divided by lambda. hc divided by lambda. Similarly, my dear students, if I ask you, since energy carried by one photon is h nu, therefore energy carried by two photons will be 2 times h nu. Energy carried by 3 photons will be 3 times h nu. If I ask you, what will be the energy carried by n photons? What will be the energy carried by n number of photons? It has to be equal to n times h nu, or you can say energy carried by n photons is equal to n times hc divided by lambda. I believe all these things are absolutely clear to every one of you, right? Energy carried by one photon, energy carried by n photons in terms of nu as well as in terms of lambda. Point number 1. Point number 2. My dear students, from now onwards, you already, I believe, must be knowing what is the SI unit of energy. What is the SI unit of energy? SI unit of energy, you all must be knowing, that is joule. That is joule, right? That is joule. SI unit of energy is joule. And in this particular chapter, I'm going to use one more unit of energy. In this particular chapter here, I'm going to use the other unit of energy as well. And what is that other unit of energy? That is electron volt. Electron volt is one more unit of energy which I'll be frequently using over here, right? And do remember, my dear students, 1 electron volt is equal to 1.6 into 10 raised power minus 19 joules. 1 electron volt is equal to 1.6 into 10 raised power minus 19 joules. Apart from that, there is one more thing which you need to know. After that, I'll show you what kind of questions are asked from it. My dear students, remember, this h is a Planck's constant. H is a Planck's constant. C is the speed of light. Remember, h multiplied by c, its combined value, you'll be taking as 12400 electron volt angstrom when you will be taking lambda in angstroms. Right? H multiplied by c value, you will be taking as 12400 electron volt angstrom. At that point of time, lambda has to be taken in angstrom. Right? Similarly, my dear students, h multiplied by c value, you will take as 1240 electron volt nanometer. But at that point of time, you will have to take lambda in nanometers. Only these things you are supposed to know. You are supposed to remember. That's all. Am I clear till here? Am I clear till here, people? Am I clear till here? This is the energy carried by one photon in terms of nu. This is the energy carried by one photon in terms of lambda. Energy carried by n photons in terms of nu. Energy carried by n photons in terms of lambda. Right? SI unit of energy is joule. Similarly, one more unit which we shall be frequently using, that's electron volt. And remember, 1 electron volt is equal to 1.6 into 10 raised power minus 19 joules. Right? H multiplied by C combined value has to be taken as 12400 electron volt angstrom. At that point of time, lambda has to be taken in angstroms. H multiplied by C combined value, you can take as 1240 electron volt nanometer. But at that point of time, lambda you'll be taking in nanometers. I am sure it is clear to everyone. If it is clear to everyone, let's have a look what kind of question can be asked. But before that, have a look on this. According to this theory, energy is transmitted in the form of small packets, and those small packets are what you call as quantum, right? In case of light energy, these packets are called as photons. Photon travels with the speed of light in vacuum, and this is the value of your Planck's constant h. You can remember this as well, 6.6 into 10 raised power minus 34 joules second, right? And this is the energy possessed by n photons, etc., etc. So I'll directly jump into the question which is in front of you. I'm directly jumping into the question which is in front of you. It's not lagging or something, it's perfectly fine. I think you have got some connectivity issues. Okay? Or maybe you're a paid spammer, is that? Okay. See guys, look at this particular question. Calculate the energy carried by 100 photons if the wavelength of the light is 2000 angstroms. Can you give it a try? A simple and basic question this is. A simple and basic question this is. My dear students, how many photons are we given with? As per the question, we are given with 100 photons, right? Wavelength of light is given as 2000 angstroms. 2000 angstroms. This is the wavelength of the light. This is the wavelength of the light. We are supposed to calculate energy carried by n photons. Energy carried by n photons has to be equal to n times hc divided by lambda. So I'll write E is equal to n value is 100. N value is 100. Lambda is given in angstroms, so H multiplied by C I'll be taking as 12400 electron volt angstroms divided by lambda is given to me as 2000 angstroms. So angstrom gets cancelled out. E value you can calculate from here how much it's coming out to be. I can see people are coming up with the answer as 620. So this is 620 and the units are going to be electron volts, right? This is the energy carried by 100 photons which were given to us. Now, if they ask you, calculate the same energy in joules, then what do you need to do? 620. 1 electron volt is how much? 1.6 into 10 raised power minus 19. Then the answer will come in joules. I believe these basic questions, I'm pretty much sure you can easily solve from now onwards. Is that clear? Is that clear, people? Be very quick. Be very quick. Be very quick. Because this is a very simple topic, guys. Right? You need to be very quick with the calculations, etc. Okay, one more similar type of question, and I'm pretty much sure you can easily solve this one as well. I'm pretty much sure you can easily solve this question as well. Look at the question carefully. A light source of wavelength 2000 angstroms emits energy 0.5 joules. The number of photons emitted from the source will be. The number of photons emitted from the source will be. So basically, E value is given to us. Let's have a look. E value is given to us as 0.5 joules, right? Lambda value is given to us as 2000 angstroms. Perfect. 2000 angstroms. What do we have to calculate? We have to get the value of N. Already I gave you one result which relates all these terms. You know, E is equal to N times Hc divided by lambda. Perfect. E is equal to N times Hc divided by lambda. Right? Now guys, I believe you can easily solve this equation, get the value of N. Am I clear? Am I clear, people? Am I clear? See guys, you can solve this equation in many ways. For example, E value is given as 0.5 joules. So left hand side, I'm taking in joules. Joule is the SI unit of energy. So left hand side, I'm taking as per SI system. Therefore, right hand side also I have to take as per SI system. Therefore, right hand side also I need to take as per SI system. So I'll write N. What is the value of H as per SI system? 6.6 into 10 raised power minus 34. What is the value of C? 3 into 10 raised power 8 meter per second divided by. What is the value of lambda? It will be 2000 multiplied by 10 raised power minus 10 meters. Why did I do this? Since I took left side as per SI system, therefore all the terms on the right side are to be taken as per SI system as well. Right? After solving this particular equation, you can get the value of N from here. This is one way of solving. This is one way of solving. Have a look on one more way. Have a look on one more way of calculation. Since you know, E is equal to N times Hc divided by lambda. Energy is given in joules, 0.5 joules, right? 0.5 joules. If I divide this with 1.6 into 10 raised power minus 19, so therefore left hand side is coming in electron volts, right? Therefore left hand side is coming in electron volts. Similarly, if I'm taking left hand side in terms of electron volts, therefore right hand side should be also in terms of electron volts. So N I'm writing as such. Hc value I'm using 12400 electron volt angstroms divided by lambda is given to us as 2000 angstroms. So angstrom cancel. You can check left hand side is an electron volt, right hand side is an electron volt. Now you can equate them and get the value of N. Either this way of calculating or this way of the calculating, the choice is all yours. Am I clear to everyone, people? Am I clear to everyone? Quickly, am I clear to everyone? Say it in the chats. Out of these two, you can use any method of doing the calculation. Perfect, perfect. Now, my dear students, there is one more term which you need to know. The question can be asked from that as well. I'm writing a term power. Power is represented by P. Power is represented by P. How do you calculate it? It is equal to energy transmitted by the source divided by time. E divided by T. So in short, P. I'll write P. P is E divided by T. Let's say you've got a source of energy. This is a source of energy. It is emitting energy in the form of radiation. Right? Okay, it is emitting energy in the form of radiation. It is emitting energy E in time T. If I want to define the term power of this particular source, power is nothing, it is energy transmitted divided by time taken, right? Now, my dear students, you know, E is nothing, it is h nu. It is N times h nu divided by T. Or you can write it as N divided by T, hc divided by lambda. This is the equation by the help of which we can calculate the power of the source. Right? What is this N by T over here? This N by T is called as, what do you call as? Can you let me know in the chats? What this N by T is called as? This is called as the rate of emission of photons. Or you can simply call it as number of photons per unit time. Right? Rate of emission of photons, you can call it. So this is a general equation with the help of which you can calculate the power of the source. For example, you have got a question over here. Look at the question carefully. A simple question. How many photons are emitted per second? So basically, you have to calculate the rate of emission of photons. Number of photons emitted per second. N by T value we have to calculate. Rate of emission of photons we have to calculate. By a 5 milliwatt laser. So, power of the laser is 5 into 10 raised power minus 3 watts. Right? Operating at 620 nanometers. So, lambda is equal to 620 nanometers. Perfect. What do we have to calculate? N divided by T. I believe you can easily solve this question. Already you know the equation. P is equal to N times Hc divided by lambda. And this is T over here. What do we have to calculate? We have to get the value of N by T. N by T will be equal to P multiplied by lambda divided by H multiplied by C. So this whole term value is to be calculated. Now, power is given to me as 5 into 10 raised power minus 3 watts as per SI system. Take lambda as per SI system as well. 620 into 10 raised power minus 9 meters as per SI system. H value 6.6 into 10 raised power minus 34 joule second SI system. T value is equal to 3 into 10 raised power 8 meter per second as per SI system. It's a matter of calculation now. And here you can calculate the rate of emission of photons. You can calculate the number of photons emitted per second, which I was supposed to calculate. Am I clear with this one? People? Say it in the chats quickly. Say it in the chats quickly. Yes? Perfectly done. All right. Moving ahead, guys. There is something called as photodissociation. What is photodissociation all about? Try to understand this one. Photodissociation. Photodissociation, it is defined as breaking of a chemical bond. With the help of what? With the help of light energy. breaking of a chemical bond with the help of light energy. Now, what it means exactly? Try to understand. My dear students, for example, there's a bond between A and A. There's a bond between A and A. There's a single bond between A and A. Let's assume that. There's a single bond between A and A. What is a bond? What is this chemical bond? It is the force of attraction, right? This chemical bond between A and A, it is the force of attraction which is holding these atoms together. It is the force of attraction which is holding these atoms together in a molecule, right? Perfect. My dear students, in order to break this bond, what are we supposed to do? In order to break this bond, we are supposed to supply energy. Or I can say, energy is required to break this bond. Energy is required to break this bond. Imagine I'm supplying energy which is required to break the bond. I'm supplying energy in the form of a photon. Imagine I'm supplying energy in the form of photon to break this bond, right? Breaking of a chemical bond with the help of, by supplying light energy. This phenomenon is what you call as photodissociation. Breaking of a chemical bond with the help of light radiation is something which you call as photodissociation. Whenever you break a chemical bond with the help of the light energy, right, you call the phenomenon as the photodissociation. Now, there are few things which you need to know. Try to understand what exactly I'm going to talk about. My dear students, for example, I'm writing a term here, bond energy of AA. Bond energy of AA is equal to x kilojoules per mole. I'm writing bond energy of AA is equal to x kilojoules per mole. What does this mean? Bond energy of AA is equal to x kilojoule per mole. That means in order to break 1 mole of bonds, in order to break 1 mole of these bonds, how much energy is required? X kilojoules, right? I'll write it over here. In order to break 1 mole of bonds, how much energy is required? X kilojoules. In order to break 1 mole of bonds, x kilojoules of energy is required. Now, 1 mole of bonds means what? It means 6.022 into 10 raised power 23 bonds. So can I say in order to break 6.022 into 10 raised power 23 bonds, this much amount of energy is required? Now, my dear students, if in order to break Na bonds, x kilojoules of energy is required, can you tell me, in order to break 1 bond, how much energy is required? Use the unitary method. It's going to be x divided by Na kilojoules. So what is this x divided by Na kilojoules? This is the amount of energy which is required to break 1 single bond between A and A. Okay? Right? As simple as that. This is the amount of energy which is required to break 1 particular bond between A and A. Right? Assume that this much of energy I am providing in the form of photon. This much energy is required to break 1 single bond between A and A, right? Now, if you are supplying the same amount of energy in the form of photon, right, in the form of photon, the bond will break. Perfect. So can I equate this term with h nu? Or we can say it like this. Imagine that, for example, n photons are required to break this bond. What will be the energy carried by n photons? It will be n times h nu, right? If n times h nu is equal to this term, then only I would say the bond will break. Right? So you can write it like this. X divided by Na is equal to, this is going to be n times, and this is going to be hc divided by lambda. Perfect. It's going to be hc divided by lambda. My dear students, did you understand how this particular equation is formed? Say yes or no in the chats. I'll show you a question with the help of which you'll perfectly get the idea of photo dissociation. But first of all, tell me in the chats whether you got the idea of how this equation came. Let me know in the chats quickly. I'm asking everyone. I'm asking everyone. I'm asking everyone. Yes? Perfect. Let me show you one single question with the help of which you will understand what exactly it's all about. Look at this particular question, guys. Look at this particular question. You'll understand properly. Calculate the wavelength of photon. Calculate the wavelength of photon. Required to break one CL-Cl bond if the bond energy of CL-Cl is 1.2 kilojoules per mole. Calculate the wavelength of the photon. So basically, you've got a bond between two chlorine atoms, right? As per the question, bond energy of this Cl2 is how much? It is given as how much? 1.2 kilojoules per mole. 1.2 kilojoules per mole, right? Okay. Now, in order to break this bond, a photon is going to strike here. A photon is going to strike here, right? Calculate the wavelength of that photon, right? We need to calculate lambda of that photon. We need to calculate the value of lambda. Perfect. So one photon is going to strike this particular bond and it's going to break it, right? Now, we have to calculate the wavelength of the photon which is going to strike here and break the bond. How do we calculate it? How do we calculate it? How do we calculate it? Check it out quickly. See guys, as per this particular phenomenon, as per this particular value which is given to us, bond energy is equal to 1.2 kilojoules per mole. What does that mean? That means in order to break 1 mole of bond, how much energy is required? 1.2 into 10 raised power 3 joules. This much of energy is required. Therefore, I can say in order to break Na bonds, how much energy is required? 1.2 into 10 raised power 3 joules. Therefore, in order to break one bond, how much energy is required? 1.2 into 10 raised power 3 divided by Na. So this much amount of energy is required. This much amount of energy is required to break one bond. And this much amount of energy you are supplying in the form of a photon, right? Let's assume that energy carried by this photon is equal to hc divided by lambda. Hc divided by lambda. So you just have to solve this particular equation. I can simply write 1.2 into 10 raised power 3 divided by 6.022 into 10 raised power 23 is equal. This particular term I've taken as per SI system in joules. Therefore, I'll be taking all the terms as per SI system. H value is nothing but 6.6 into 10 raised power minus 34. Perfect. C is nothing but, how much is C? C is 3 into 10 raised power 8 meter per second and divided by lambda. Since this is as per SI system, this is as per SI system, so lambda after solving will come as per SI system only. So you just have to solve this particular equation, cross multiple and get the value of lambda in meters from here. Right? Am I clear, people? Am I clear to everyone? Am I clear to everyone? So you just have to solve this particular equation, just cross multiple things and get the value of lambda from here. Yeah? Just equate these two terms and we are done. I hope if a question is asked from photo dissociation, this is the procedure of solving the question as per photo dissociation. Right? What is the final answer? Final answer even I do not know. You just need to cross multiple and get the final answer. Okay? Right, people? Now, have you heard about photoelectric effect? This again one important topic. Have you heard? Sir, how you put Na value? Na is the Avogadro's number whose value is 6.6 into 10 raised power 23. Sorry, 6.022 into 10 raised power 23. Photoelectric effect, I believe you would have studied in your modern physics as well, right? And here also a question is frequently asked when it comes to the photoelectric effect. So how do we exactly define it? First thing, my dear students, when you talk about the photoelectric effect, it supports the particle nature of light. It supports the particle nature of light. Number one, when light is incident on the certain metal, electrons are emitted. The emitted electrons are what you call as photoelectrons. The current which flows due to the motion of these photoelectrons is called as photoelectric current or photocurrent. And this phenomenon exactly is what you call as photoelectric effect. Now, what exactly it means? Try to understand all the things in detail. My dear students, for example, I'm not going to stretch it a lot. Okay, for example, this is a metal surface. Let's say this is the metal surface. Okay, if this is a metal surface, so there will be positively charged kernels as well as electrons. Right? If this is a metal surface, imagine this is a metal surface. Let's say this is made up of cesium. Let's say this is the surface of cesium. If this is the surface of cesium, there will be Cs positive ions as well as electrons. Right? Cs positive ions as well as electrons. So there are basically positively charged ions with the electrons. Now tell me one thing. If I select an electron, is this electron free to move or this electron is bounded? Can you let me know that? Is this electron free to move or it is bounded? You just tell me that. See, this particular electron, it will be attracted by all these positively charged kernels, right? If I talk about this particular electron, it is attracted by all these positively charged kernels. Yeah? It's not free. It's bounded. It's attracted by all these. It's attracted by all these positively charged kernels. Right? Now, my dear students, if I want to take this electron out from the metal surface, what am I supposed to do? I'm supposed to supply energy. I'm supposed to supply energy in the form of, light, right? So when the light strikes the metal surface, and if the electron is coming out from the metal surface, this overall phenomenon is what you call as photoelectric effect. As per the definition which you saw over here, when light is incident on the certain metal, electrons are emitted. These electrons are called as photoelectrons. The current which flows due to the motion of these electrons is what you call as photoelectric current or photocurrent. And this overall phenomenon is what you call as photoelectric effect. As you can see, this was your metal surface. Light is incident on the metal surface. Electrons are coming out from the metal surface, right? Perfect. And this phenomenon overall is what you call as photoelectric effect. My dear students, since this electron is in bounded state, it's attracted by these kernels. So basically, in order to take the electron out, I have to break all the attractions. Since let's assume this kernel is attracting it, this kernel is attracting it, this is attracting it. So in order to take this electron out, I have to break these attractions. And to break the attraction, you have to supply energy. You are supplying energy in the form of light. To break the attraction, you have to supply energy, and you are supplying energy in the form of light. Perfect. You are supplying energy in the form of light. First thing, the minimum amount of energy which is required, to eject the electron, to knock out the electron, the minimum amount of energy which is required to eject the electron from the metal surface, that's called as work function. Or you call it as threshold energy. And this work function, this threshold energy, it is represented by phi naught, right? Which is equal to h nu naught. Which is equal to h nu naught. Which is equal to h nu naught. Number one. Number two. Number two. The minimum frequency of the incident light, which is required to knock out the electron, is called as threshold frequency. Which is represented by mu naught. The minimum energy which is required to knock out the electron is called as threshold energy. The minimum frequency of the incident light required to knock out the electron, that's called as threshold frequency. Now you know, nu is equal to c divided by lambda. Therefore, nu naught will be equal to c divided by lambda naught. I told you threshold energy, it is the minimum frequency. If frequency has to be minimum, that means wavelength has to be maximum. So I'm defining one more term, that is threshold wavelength. That will be defined as the maximum wavelength of the incident light. Required to knock out, required to eject the electron is something which you call as threshold wavelength. And that threshold wavelength is represented by lambda naught. So three terms we have. One is threshold energy, one is threshold frequency, and one is threshold wavelength. Right? One is threshold wavelength. Perfect. Now guys, if you can understand carefully, I'm going to let you know one important thing. What is that? For example, this is the metal surface which contains kernels and electrons. These are the electrons which I'm showing. Okay, these are the electrons which I'm showing. For example, I have to take this electron out. The minimum energy which is required to take the electron out, let's say that is 50 joules. The minimum energy which is required to take the electron out, let's say that is 50 joules. So can I say this is the value of work function? Minimum energy required to take the electron out. That's what you call as work function, right? Perfect. Let's say this is the photon which is going to be incident on it. Let's say the photon carries the energy of 80 joules. For example. Perfect. When this photon carrying the energy of 80 joules is going to strike this electron, out of 80 joules, I would say 50 joules will be used. 50 joules will be used to break the force of attraction here and to take the electron out. Out of 80 joules, 50 joules will be used to break the attractions and eject the electron. The remaining 30 joules will be given to the ejected electron in the form of its kinetic energy. So in short, incident energy is divided into two parts. One part of incident energy is required to break the attractions, or I would say one part of incident energy is required to knock out the electron. The remaining part of the incident energy is imparted to the electron in the form of its kinetic energy. So can I generalize a statement? Can I say energy of incident light will be utilized in two parts? One is work function. Second is impart maximum kinetic energy to the photoelectron. Am I clear with this? Am I clear with this, people? Am I clear with this? This equation, you know, you call this equation as the photoelectric equation, right? Einstein's photoelectric equation. Now you can further, modify this particular equation. Energy of incident light is h nu. This is equal to h nu naught. This can be written as maximum kinetic energy of the photoelectron. This can be one more format of this. Or you can write hc divided by lambda is equal to hc divided by lambda naught plus Ke max. This is one more format of this photoelectric equation, right? Or I hope you know, if I write the first equation can be written as Ei is equal to phi naught plus, instead of maximum kinetic energy, you can write it as EV naught, where V naught is the stopping potential. I hope you know it. where V naught is the stopping potential. V naught is the stopping potential. Right? These are the different forms. These are the different forms of your Einstein's photoelectric equation. I hope I'm perfectly clear to every one of you. Right? I hope I'm clear to every one of you. Right, people? Now, my dear students, before making certain graphs over here, there are a few more things which you need to know. And what are those things? Understand. Few very, very, very important points. See, guys, one photon. You call this photoelectric effect as one photon, one electron emission. You call this as one photon, one electron emission. What does that mean? That means one photon will take away only one electron. One photon can never take away two electrons. Remember that. Okay? One photon, one particular photon, it can take away only one electron. It can knock out only one electron. It can eject only one electron. One photon can never take away two electrons. Or two photons can never take away one electron. No. One photon for one electron. One photon for one electron. Number one. Number two. There is no time lag. There is no time lag. What does that mean? That means as soon as the photon strikes the metal surface, at the same time, electron is ejected. As soon as the photon strikes the metal surface, at the same time, electron is ejected. So there is no time lag in between striking of photon and ejection of electron. No, there is no time lag at all. There is no time lag at all. Okay? Now, my dear students, next point. Try to understand it very carefully. First thing, understand it. If you increase the frequency of the instant light, if you're increasing the frequency of the instant light, if you're increasing the frequency, E is equal to incident energy, is equal to h nu. If you're increasing the frequency, that means you are increasing the energy of incident photon. You're increasing the energy of incident photon. You're increasing the energy of incident photon. And incident energy is divided in two parts. One part is to break the attractions and take the electron out. The remaining part is given to the electron in the form of its kinetic energy. So can I say, if you increase the frequency of the incident light, energy of the incident light will increase? Due to which, if energy of incident light is increasing, phi naught is fixed, phi naught is constant, work function is constant, right? What will happen? Can I say kinetic energy of the photoelectron will increase? And if kinetic energy of photoelectron is increasing, what will happen to stopping potential? Stopping potential automatically will increase. This is one statement which I want you guys to remember. I hope I'm clear with this. Number one. Number two. If you increase the intensity of the instant light, intensity means you're increasing the intensity. If you're increasing the intensity, that means more photons are incident on the surface. If you're increasing the intensity of the incident light, that means more photons are incident on the surface. One photon is enough to take out one electron. If more photons are incident, more electrons will come out. If more electrons are coming out, if you are increasing the intensity of the light, I will say more electrons will come out. If more electrons are coming out, that means if more electrons are coming out, what will happen to photoelectric current? What will happen to photocurrent? More the moment of the charge in a particular direction, more is going to be the current. So I would say more over here will be the photocurrent. Remember it directly. This is one more important statement which you need to know. Okay? Now you tell me the answer of one question. If I'll increase the frequency of the instant light, what will happen to photocurrent? If you are increasing the frequency, guys, be careful what I'm saying. If you are increasing the frequency of the instant light, what will happen to photocurrent? Quickly. photocurrent will remain the same. When you increase the frequency of the incident light, that means energy of incident light is increasing. That means energy of incident photons are increasing, right? Number of photons are not increasing. Only energy carried by one photon is increasing. Energy carried by the photon is increasing. Work function is same. Therefore, kinetic energy only increase. Okay? I hope I'm clear with this. I hope I'm clear with this. I hope I'm clear with this. My dear students, if all these things are clear, what do you think about this particular graph? This is the graph between kinetic energy versus frequency of the incident photon. Kinetic energy versus frequency of the incident photon. See guys, this equation we already derived, right? Or you can write it in this format. You can write this equation in this particular format as well. Now, if you think carefully, kinetic energy maximum you are plotting along y-axis, right? And this nu you are plotting along x-axis. This is your m, and this is your c, and the sign is minus. So y is equal to mx minus c. Y is equal to mx minus c. So it's going to be a straight line with a negative slope. It's a straight line with a negative slope, and the intercept here, which is represented by c, that's equal to what? That's equal to h nu naught, right? That's equal to h nu naught. If I ask you slope is your m basically. M is nothing but h. Slope of this particular curve is h. So this is the first graph which can be asked, right? This is the first graph which can be asked. I believe I'm clear. If this particular graph is clear, I would ask you one more graph. See guys, can you plot a graph between stopping potential versus the frequency of the incident light? Look at this particular graph. Stopping potential versus frequency of the incident light. I give you one equation if you remember. Energy of incident light is equal to phi naught plus EV naught, where V naught is the stopping potential. So I can write this equal to h nu, this equal to h nu naught plus EV naught. Or I can say EV naught is equal to h nu minus h nu naught, or I can say V naught is equal to h divided by E nu minus h divided by E nu naught. Look at this particular equation now. V naught you are plotting along y-axis, right? And this term you are plotting along x-axis. This is going to be your m. This whole term is going to be your c. Sign is minus. Y is equal to mx minus c. So it's a straight line, but with a negative intercept. So this is going to be the straight line with a negative intercept. What about the value of this intercept? Intercept is represented by c, and c value is nothing but h divided by E nu naught. What about the slope? Slope is m, and m here is h by E. Slope here is h divided by E. Perfect. This is the graph which can be asked. Look at this particular equation. I want you guys to give it a try. I want you guys to solve this particular equation. Give it a try. Give it a try, people, quickly. Give it a try, quick. As per the question, if the work function is represented by phi naught, is equal to 3.1 electron volt. Threshold wavelength. Find the threshold wavelength. Number one. And maximum kinetic energy. Threshold wavelength and maximum kinetic energy of the electron emitted when the radiation of wavelength 300 nanometers strikes the metal surface. So a radiation of wavelength 300 nanometers is striking the metal surface. We have to calculate phi naught. We have to calculate maximum kinetic energy. How do we do it? First of all, phi naught, you know, it is equal to hc divided by lambda naught. This is equal to 3.1 electron volts. Or I can say lambda naught has to be equal to hc divided by 3.1 electron volt. So lambda naught will be equal to h multiplied by c, if I write it as 1240 electron volt nanometer, divided by 3.1 electron volts. So electron volt cancel. So can you let me know the value of lambda naught over here? How much it comes out to be? It will be approximately some 400. right? It will be approximately 400. Is that 400 or 40? It will be 412 nanometers. So this is first of all your threshold wavelength, which you were supposed to calculate, number one. Number two, what do we have to calculate? What do we have to calculate? Ke max. Tell me first of all, energy of the incident light. Can we solve it? It will be hc divided by lambda. hc will be taken as 1240 electron volt nanometer divided by lambda is your 300 nanometers. So nanometer cancel. So what will be the energy of incident light here? This will be how much? 4.1, is that? 4.1 electron volts approximately. So you got the energy of incident light, right? What do we have to calculate the next? Lambda naught is calculated. Ke max has to be calculated. You know, incident energy is equal to phi naught plus Ke max. Phi naught plus Ke max. So I would say the maximum kinetic energy of the photoelectron will be equal to Ei minus phi naught. What is Ei? 4.1 electron volt. What is phi naught? Phi naught is given to you as 3.1 electron volt. So the value exactly comes out to be 1 electron volt. So maximum kinetic energy with which the photoelectron moves. It is going to be what? It's going to be 1 electron volt. I hope it's clear. I hope I'm clear. Yes? Is it clear, people? Say it in the chats once. Say it in the chats quickly, if it is clear. All right, can you give this question a try once? Can you give this particular question a try once? Check the question first. The work function of some metals is listed below. You are given with certain metals and you are given with their work functions. The number of metals which will show photoelectric effect when light of 300 nanometer wavelength falls on the metal. So basically, the incident light has got the wavelength of how much? The incident light has got the wavelength of 300 nanometers. So can I calculate energy of the incident light? Can I calculate energy of the incident light? That will be equal to how much? Hc divided by lambda. Hc divided by lambda. Energy of the incident light. Hc will be 1240 electron volt nanometer divided by lambda. Lambda is how much? Lambda is 300 nanometers. So this term cancel. So energy of incident light will be how much? It will be approximately 4.1 electron volts. This is the energy of incident light. This is the energy of incident light. Now, over here, before solving this particular question, let me tell you the criteria for the photoelectric effect. Criteria for the photoelectric effect. When can you say that photoelectric effect is going to happen? When can you say that the electron is going to get emitted? Electron is going to get ejected. My dear students, if the energy of incident light will be greater or equal to work function, if the energy of incident light is greater or equal to work function, we'll say that photoelectric effect will happen. Number one. Number two, energy of incident light is what? H nu has to be greater or equal to phi naught. Phi naught is H nu naught, H cancel. So nu has to be greater than nu naught. You can say frequency of the incident light has to be greater than the threshold frequency. Frequency of the incident light has to be greater or equal to threshold frequency. Then only photoelectric effect will happen. Or let's talk in terms of wavelength. Since nu has to be greater than nu naught, what is nu? C divided by lambda. C divided by lambda has to be greater than C divided by lambda naught. Or I'll say lambda has to be less or equal to lambda naught. Okay, you can say the incident wavelength has to be less or equal to threshold wavelength. You can talk in terms of all these three parameters over here. In short, I would want you to remember this one. Energy of incident light should be greater or equal to threshold energy, then only photoelectric effect will happen. Right? Then only electron will come out. Perfect. Now, what is the energy of incident light? 4.1. What is the threshold? What is the work function for lithium? 2.4. So energy of incident light is greater than this. So over here, it will happen. Energy of incident light is greater than this value. Yes, it will happen. Energy of incident light is greater than this value. Yes, it will happen. Energy of incident light is greater than this value. Right? It will happen. Energy of incident light is less than here. Less than. So in all these three cases, photoelectric effect will not happen. So there'll be four metals which will be showing what? There'll be four metals which will be showing the photoelectric effect. I believe I'm perfectly clear to every one of you. Is that? Is that, people? Am I clear? Am I clear with this question? Am I clear with this question? Okay. Can you solve this one? Can you solve this one? So what is the criteria for photoelectric effect? Energy of incident light should be greater or equal to the threshold energy. Or I can say energy of incident light should be greater or equal to the work function. If you look at this particular question, light of wavelength 400 nanometers. Light of wavelength 400 nanometers. So what will be the energy of incident light? First calculate that. Hc divided by lambda. Hc is 1240 electron volt nanometer divided by lambda is 400 nanometers. So energy of incident light is coming out to be 3.1 electron volts. The first thing which I calculated, number one. Number two, your work function as per the equation is given to us as 2.3 electron volts. What do we have to calculate? Stopping potential V naught. V naught we have to calculate, right? V naught we need to calculate. Now, how exactly you're going to do it? You know, your incident energy is equal to work function plus Ke max plus Ke max. Or instead of Ke max, you can write what? Instead of Ke max, you can write EV naught. EV naught, right? So what is energy of incident light? This is 3.1 electron volt. What is phi naught? Phi naught is 2.3 electron volt plus electron V naught, EV naught. So E and E everywhere cancelled out. So 3.1 minus 2.3 comes out to be 0.8. So 0.8 volts is the value of V naught over here. So this is the stopping voltage which you are supposed to calculate. I hope you can solve this sort of equation on your own. Right, people? Am I clear? Am I clear to everyone? Enthalpy and Gibbs free energy, they have got same units. They have got the unit of energy, right? Entropy will be joules per Kelvin. Entropy will be joules per Kelvin. I hope you can solve the questions based on photoelectric effect on your own from now onwards, yeah? Okay, talking about the Bohr's model. Well, I'm not going to talk about the postulates, etc., etc. I'll directly go into the actual stuff from which the question is asked. Rest, I believe all the things you know, right? As per Bohr's model, which is applicable only to single electron species, you know it. It's applicable to single electron species. You know it already, right? Atom consists of your protons, electrons. Electrons are continuously revolving, etc., etc. I'm not going into that. I'm directly jumping into the fact from which the questions come, right? From which the questions come. What is that? The first thing that is going to be the first thing from which the question is asked. What is that? That is the radius of nth Bohr's orbit. That is the radius of nth Bohr's orbit. This will be the first question which will be asked in your examination, right? Okay. Radius of nth Bohr's orbit, I'm representing with what? I'm representing with Rn. Radius of nth Bohr's orbit. I'm representing with Rn. My dear students, one direct result I'm going to give you. For example, this is the nucleus and this is the shell. This is the shell in which electron is revolving, for example. Right? I've taken the atom whose atomic number is Z. What do I need to calculate? I need to calculate this particular radius. Radius of nth Bohr's orbit. You must be knowing there is a direct result. There is a direct result by means of which you can calculate the radius of nth Bohr's orbit. It is equal to R naught n square divided by Z. R naught n square divided by Z. What is R naught here? R naught is a constant whose value is 0.529 angstroms. 0.529 angstroms. Number one. Number two. If you need to compare the radius of two Bohr's orbits, this is how you compare it. R1 divided by R2 will be equal to N1 square divided by N2 square. And this is going to be Z2. This is going to be Z1. This is how you compare the radius of two Bohr's orbits. As simple as that. As simple as that. As simple as that. Just give me a second, guys. I hope this part is clear. This is the first question from which a question is asked. That is the radius of the nth Bohr's orbit. I'll show you its application part in some time. Right? This is the first question from which this is the first topic from which the question is asked. Simple formula-based question will come, nothing else. Nothing else. Okay? Nothing else. Second question that will be asked on velocity. Velocity of the electron in the nth Bohr's orbit. Velocity of the electron in the nth Bohr's orbit, which I'm representing by Vn. Velocity of the electron in the nth Bohr's orbit, which I'm representing by Vn. Okay? And velocity of the electron in the nth Bohr's orbit has to be equal to V naught multiplied by Z divided by N. Right? V naught multiplied by Z divided by N. Approximate value of V naught you can take as 2 into 10 raised power 6 meter per second. Let me check the exact value. Just a second, guys. Let me check the exact value. Exact value is 2.18. 2.18 into 10 raised power 6 meter per second. 2.18 into 10 raised power 6 meter per second. 2.18 into 10 raised power 6 meter per second. If you need to compare the velocities of different Bohr's orbits, velocity of electrons moving in different Bohr's orbits, V1 divided by V2 is equal to, this will be Z1 divided by Z2 multiplied by N2 divided by N1. A question can be asked from this particular formula as well. Question can be asked from this particular formula as well. So first question will be based on the radius. Second question will be based on the velocity, right? Can you let me know the formula for time period? Quickly. Quickly. The third thing I'm writing over here, that is time period. Time period of the electron, which I'm representing by Tn. Okay? How much time it takes for electron to complete one revolution? How much time it takes for an electron to complete one revolution? You should be knowing it. I'm directly giving you the result. Time period of the electron in the nth Bohr's orbit is equal to T naught n cube upon Z square. T naught n cube upon Z square. Right? What is T naught? T naught here is 1.6 into 10 raised power minus 16 seconds. If you need to compare the time period of two electrons, so T1 divided by T2 has to be equal to N1 cube divided by N2 cube. This is Z2 square divided by Z1 square. This is the formula with the help of which we can compare the time period of two electrons moving in two different Bohr's orbits. Right? And at the end, people, the fourth thing, what is that? That is frequency of the electron. Frequency of the electron, which is represented by nu n. Frequency of the electron in the nth Bohr's orbit. Frequency of the electron in the nth Bohr's orbit. Well, frequency is inverse of time period. You can say frequency of the electron in the nth Bohr's orbit. It will be equal to 1 divided by time period of the electron in the nth Bohr's orbit. Perfect. 1 divided by time period of the electron in the nth Bohr's orbit. Or you can say frequency of the electron in the nth Bohr's orbit is directly proportional to what? It is directly proportional to Z square, inversely proportional to N cube. Or my dear students, if you want to compare the frequencies of two electrons moving in two different Bohr's orbits, it will be nu1 divided by nu2 is equal to z1 square divided by z2 square. This is n2 cube and this is n1 cube. This is the formula with the help of which you can compare the frequencies of two electrons moving in two different Bohr's orbits. Right? I hope I'm clear. I hope I'm clear, people. First formula was for the radius. Second is for the velocity. Third is for the time period. Fourth one is for the frequency. Now, the fifth one. You know total energy. Total energy possessed by the electron in the nth Bohr's orbit. Total energy possessed by the electron in the nth Bohr's orbit. How much that is? You must be knowing it. I'm not deriving any results. This is minus 13.6 Z square divided by n square electron volts. Okay, this is the formula with the help of which you can calculate the total energy of the electron in the nth Bohr's orbit. Similarly, if I talk about the kinetic energy of the electron in the nth Bohr's orbit, it will be 13.6 Z square upon n square electron volts. And the last one, that is potential energy in the nth Bohr's orbit is equal to minus 27.2 Z square upon n square electron volts. So these are the different results from which questions can be asked. These are the different results from which the questions can be asked. Let me give you few questions with the help of which you can understand, you can remember what kind of questions can be asked. See guys, for example, this is the basic question which we have on the screen. Check it out. Look at the question carefully. Look at the question carefully. Look at the question carefully. Quickly, guys. So people have already come up with the answer, that is 8:9. Is that? Are you sure? Calculate the radius ratio of second orbit of He positive, second orbit of He positive, and third orbit of Be tripositive. Okay? Be tripositive. If I represent He positive by number 1 and I'm representing this by number 2, okay? First of all, what is the atomic number of helium? Hydrogen, helium. What is the atomic number of beryllium? Hydrogen, helium, lithium, beryllium. 4, right? Okay. Calculate the radius ratio of second orbit. Second orbit of He positive and third orbit. And third orbit of Be tripositive. Okay. Let the radius here is R1. Let it be R2 here. So what I need to do, I need to just get the value of R1 divided by R2. R1 divided by R2 as per formula, I gave you already. Radius of nth Bohr's orbit is equal to R0 n square by Z. So this is going to be n1 square, this is going to be n2 square, and this is going to be z2, this is going to be z1, right? So R1 divided by R2 is equal to n1 square. So 2 ka square is 4, n2 square, 3 ka square is 9, z2, that is 4, z1, that is 2, right? So the value will be 4, 4, 16, 16 divided by 18, right? The value will be how much? 2, 8 to 9. So 8:9 is the radius ratio which we were supposed to calculate. Yeah? Simple and basic question this was, and I believe all of you would have already solved this particular question. Number 1. Number 2, look at this particular question carefully and tell me what should be the correct answer of this particular question. If the velocity of the electron in the first Bohr's orbit of hydrogen atom is V, what will be the velocity of the electron in the third orbit of Li dipositive? What do you think about this? What do you think about this? My dear students, on one side you are given with hydrogen atom, on the other side you are given with Li dipositive ion. If I call this as number 1, I'm representing this as number 2, right? Atomic number of hydrogen is 1. Atomic number of lithium dipositive. Hydrogen, helium, lithium. That is 3, right? Here I'm given with the first orbit, and here which orbit which orbit they are talking about? The third orbit, right? What will be the velocity of the third orbit of allied hypothesis? Okay. As per the question, the velocity of the electron in the first orbit of hydrogen atom is V. So V1 is V. We have to calculate the value of V2. We have to get the value of V2. Again, one simple and basic question, right? Again, one simple and basic question. Can you give it a try? You know, velocity of the electron in the nth Bohr's orbit, that is V naught Z by N. So V1 divided by V2 is equal Z1 divided by Z2, and this is going to be N2 divided by N1. What is V1? That's V. V2 we have to calculate. Z1. Z1 is 1. Z2 is 3. N2. N2 is 3. And N1 is 1. So 3 cancel. So you got to know your V2 is nothing but V. I hope this sort of a question you can again solve easily from now onward. Yeah? I hope I'm clear. I hope I'm clear. My dear students, if you remember, these three equations I already gave you. One is total energy possessed by the electron in the nth Bohr's orbit. This is the kinetic energy possessed by the electron. And this is the potential energy possessed, right, in the nth Bohr's orbit. If you look at this particular expression, as the value of n increases, if the value of n increases, that means electron is going far. N is increasing, electron is going far. If the value of n is increasing, this whole term, there's a minus sign here, this whole term will increase. This whole term will increase because there's a minus sign in the front. There's a minus sign in the front. If there was no minus sign, at that point of time, n increases, E decreases. But there's a minus sign here. So n increases, E increases. So as the electron goes far from the nucleus, energy possessed by the electron, total energy possessed by the electron, that increases. Remember this particular statement, right? As the value of n increases, as the electron goes far, total energy possessed by the electron, that actually increases. Okay? Now guys, understand few more things. If you particularly talk about hydrogen atom, you should know one thing. When the electron makes a transition from lower energy state to higher energy state, energy is absorbed by the electron, right? Energy is absorbed by the electron. When the electron makes a transition from higher energy state to lower energy state, energy is emitted by the electron. Now, how much energy is absorbed or emitted by the electron? For example, the electron is making a transition from shell number 1 to shell number 3. So from lower to higher, energy is absorbed. How much? Whatever will be the energy gap between these two shells, same amount of energy is absorbed by the electron. Similarly, if the electron is coming back from 3 to 1, higher to lower, energy is emitted. How much? Same, whatever is the energy gap between these two shells, same amount of energy is emitted by the electron. Yes, that is something which I believe every one of you would be knowing. Okay. Now, if I talk about the hydrogen atom, what is the energy of the electron in the first shell of hydrogen? Minus 13.6. If you use the formula, minus 13.6 n square by z square. For hydrogen, z is 1. Put n as 1, you get this value. This is the energy of the electron in the second Bohr's orbit, third Bohr's orbit, fourth orbit, right? This is the energy of the electron in the infinite energy state. What is meant by infinite energy state? What is meant by that? Infinite energy state. See guys, understand one simple thing. I told you one thing. As the electron goes far from the nucleus, total energy possessed by the electron increases. As the electron goes far from the nucleus, total energy possessed by the electron increases, right? Now, my dear students, understand one thing. If the electron is going far from the nucleus, distance between electron and nucleus is increasing. If distance is increasing, force of attraction is decreasing. When electron reaches the infinite energy state, there'll be no force of attraction between nucleus and electron. If there is no force of attraction between nucleus and electron, that means electron is out of the influence of the nucleus. Right? That means electron is out of the influence of the nucleus. So if I say electron is present here, that means between nucleus and electron, there is no attraction. This electron is out of the influence of the nucleus. Okay? As you can see, here you have got the minus sign. This is 0. Basically, the minus sign, this negative sign over here, it tells you that the electron is under the influence of the nucleus. This negative sign indicates that electron is under the influence of the nucleus. Okay? Right? Now, if you calculate energy gap between first and second shell, it will be 10.2 electron volts. Second and third, 1.89. How do you get the energy gap? This minus this. This term minus this term will be this. This term minus this term will be this, right? So basically, as the number of shells increase, the energy gap between the successive levels, what happens to that? First, the energy gap was between 1 and 2, it's 10.2. Between 2 and 3, it's 1.89. Decreases. It decreases when number of shells increase, right? As you can see over here. So remember this particular point as well. This is important. As the shells increase, the energy gap between the successive levels, what happens to that? That decreases. Energy gap between the successive shells, that decreases. Okay. First of all, this was your n is equal to 1. N is equal to 1 is what you call as ground state. N is equal to 2, the second shell. You call it as the first excited state. This is second excited state, third excited state, etc., etc. Okay, these are some general values which I believe every one of you would be remembering from now onwards. Right? Every one of you will be remembering these values from now on. And this is particularly valid for hydrogen atom. This is the energy possessed by the electron in the first shell of hydrogen, second shell of hydrogen, third shell of hydrogen, fourth shell of hydrogen. Negative sign indicates that electron is under the influence of the nucleus, right? If the electron is here, that means electron is out of the influence of the nucleus, right? This is the ground state. This is the first excited state, second excited state, etc., etc. Okay, right? Now, guys, there are few things basically, few important things from which questions are frequently asked. Let me tell you those important things from which questions are frequently asked. Just give me a second. Okay, here comes the actual stuff from which questions are asked. I believe you all would have heard about something called as hydrogen spectrum, right? Hydrogen spectrum. My dear students, the electron in hydrogen atom, when it gets excited to higher energy state, at higher energy state, electron is unstable. It just resides there for 10 raised power minus 8 seconds. Electron when in higher energy state, electron when excited to higher energy state becomes unstable. It just resides there for 10 raised power minus 8 seconds. Then it jumps back. Then it jumps back. And you know when electron makes a transition, when the electron jumps back, when the electron makes a transition from higher energy state to lower energy state, energy is emitted in the form of radiations. Now remember, when the electron makes a transition from higher energy states to shell number 1, it can be 2 to 1, 3 to 1, 4 to 1, 5 to 1, infinite to 1, whatever. When the electron makes a transition from higher energy states to shell number 1, the series of radiations which we get, is what you call as Lyman series. When the electron makes a transition from higher energy state to shell number 2, we get a series of radiation which you call as Balmer series. Similarly, Lyman, Balmer, Quotient, bracket, Fund. You should be knowing this, right? This is something which I believe you all know, right? When the electron makes a transition from higher energy state to shell number 1, the series of radiations which we get is called as Lyman series, right? Perfect. Then Balmer, Quotient, bracket, Fund. Perfect. Now, guys, here comes something important. If I particularly talk about Lyman series, this is what you call as first line of Lyman series, or you call it as H alpha line of Lyman series. This is called as second line of Lyman series, or H beta line of Lyman series. This is called as third line of Lyman series. Sorry, this is not the third line. Third line should have been from here to here. This is the third line of Lyman series, which is what you call as H gamma. So remember when I use the term first line of Lyman means 2 to 1. Second line of Lyman, 3 to 1. First line of Balmer, 3 to 2. Second line of Balmer, 4 to 2. Right? Remember these things. Why you need to remember these things? Because over here, I'm going to tell you a question which is frequently asked. What is that? That is calculation of the wavelength, calculation of the wavelength of a radiation, emitted or absorbed. My dear students, you already know one thing. When the electron makes a transition from lower energy state to higher energy state, energy is absorbed by the electron in the form of a radiation. Similarly, when the electron makes a transition from higher to lower, energy is emitted by the electron in the form of radiation. Those radiations will be definitely having certain wavelengths, certain frequencies. Now, how do we calculate the wavelength of the radiation emitted or absorbed? How do we calculate the wavelength of the radiation emitted or absorbed? For that, I'll be using the Rydberg's formula. Rydberg's formula says that wave number is equal to 1 divided by lambda is equal to RH Z square 1 upon N1 square minus 1 upon N2 square. This is the direct result with the help of which we can calculate the wavelength of the radiation emitted or absorbed. But remember, this N1 over here is what you call as lower energy state. N2 is something which you call as higher energy state. Lower energy state, higher energy state. Z, you know, that's atomic number. Do remember, in order to reduce the calculation, 1 divided by RH value is taken as 911.5 angstroms. This term you also should know. Now try to understand what exactly I'm going to do. For example, I'm writing Lyman series. Let's try to analyze Lyman series. Right? Let's try to analyze Lyman series. And in the Lyman series, I'm writing a term that is calculation of series limit. Or you call it as shortest wavelength. Series limit or shortest wavelength. In case of Lyman series. First of all, my dear students, you know delta E is inversely proportional to lambda, right? For the wavelength to be shortest, energy gap has to be maximum. In case of Lyman series, if you look at the Lyman series, when is the energy gap maximum? When the electron makes a transition from infinity to 1, right? So whenever I need to calculate the shortest wavelength of Lyman series, I have to take the maximum energy gap. Maximum energy gap is from when the electron makes a transition from infinity to 1. So this is your lower energy state and this is your higher energy state. So 1 divided by lambda minimum has to be equal to R. Hydrogen Z is 1 upon N1 square minus 1 upon N2 square. When you solve it, 1 divided by lambda value only comes out to be R, or I can say lambda is equal to 1 divided by R, and 1 by R you already know, that is 911.5 angstroms. So this is the shortest wavelength in case of the Lyman series, which is what you call as the series limit, right? It is what you call as series limit. Similarly, if I ask you in the same Lyman series, if I ask you the maximum wavelength, calculate the lambda max. In what? In Lyman, I'm asking. In Lyman. Calculate the lambda max in Lyman. My dear students, one thing. You know, delta E is inversely proportional to lambda. For lambda to be max, delta E has to be minimum. Energy gap has to be minimum. Now, in case of Lyman, what is the minimum energy gap? In case of Lyman, the minimum energy gap is this one. That means we have to take the transition from 2 to 1. So, we have to take the transition from 2 to 1. Lower energy state is N1, higher energy state over here is N2. Perfect. So, I can say 1 divided by lambda is equal to R, Z square, 1 upon N1 square minus 1 upon N2 square. So, 1 divided by lambda is equal to R. This is going to be 1 minus 1 by 4, right? So, 1 divided by lambda here will be R. This will be 4 minus 1, 3. 3 divided by 4. Or I can say lambda is equal to 4 by 3 multiplied by 1 by R. 1 by R is 911.5. And you just need to solve it. This is going to give you the maximum wavelength in case of what? In case of Lyman series, right? Perfect, guys. Am I clear till here? Am I clear till here? Am I clear till here? Quickly in the chats. Yeah. Same things you can calculate in case of Balmer, Paschen, etc., etc. Right? Okay, I'm asking you one simple question. If I'm asking you to calculate series limit in Balmer, what is the transition you are going to take? If I'm asking you to calculate series limit of Balmer, what is the transition you are going to take? From where to where? From where to where? Quick. From where to where? Series limit of Balmer. It is going to be infinity to 2. Absolutely, you're right. Exactly, guys. Exactly. Perfect then. Do you remember one table which I'm going to give you? Okay. This table you need to remember. In case of Lyman series, we get a series of radiation which fall into ultraviolet region. In Balmer series, we get a series of radiation which fall into visible. Then infra, far infra, far infra. So U, V, I. Right? Do you remember in your NEET 21 or 22, the question is asked, right? Balmer series falls in which region? Falls in visible region. So this table is important. U, V, I. Okay, you have to remember this directly. You have to remember this directly. Lyman series, all the lines, all the radiations in Lyman series, they fall in the ultraviolet region. All the radiations in the Balmer series, they fall into visible spectrum. Similarly, Paschen falls in infrared spectrum, etc., etc. So do remember this as well. Now guys, these are the two formulas from which you will be getting the sure shot question. Calculation of maximum spectral lines obtained. Number two, lines of a specific series. What it means? Maximum spectral lines obtained when the electron makes a transition from higher to lower. It is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. For example, try to understand. Let's say the electron is making a transition from 6 to 1. Let's say the electron has to come from 6 to 1. How many maximum spectral lines it will emit? How many maximum spectral lines will be produced? So maximum spectral lines produced has to be equal. Lower energy state is N1, higher energy state is N2. So N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. So this value comes out to be 15. So in total, 15 spectral lines will be obtained. In total, 15 spectral lines will be obtained. In total, 15 spectral lines will be obtained. Now, out of these spectral lines, few spectral lines will fall into Lyman category, few spectral lines will fall into Balmer category, few spectral lines will fall into Paschen category, etc., etc. Right? So, how do we check out of these 15 how many will fall into Lyman with the help of this particular formula? So, number of spectral lines falling into Lyman category. It has to be equal to N2. N2 is 6 minus ground state of Lyman. Ground state of Lyman is 1. It's 5. Out of 15, how many will fall into Balmer? N2. N2 is 6 minus ground state of Balmer. That's 2. So this will be 4. Similarly, Paschen. N2, that is 6 minus ground state of Paschen. 3. Right? Lyman, Balmer, Paschen. Bracket. N2 minus ground state of bracket. 4. Right? Fund. N2 minus ground state of fund. That is 1. So 5 plus 4 plus 3 plus 2 plus 1. It has to come out to be exactly as how much? 15. So anything can be asked over here. Anything can be asked over here. Either you'll be asked the calculation of maximum spectral lines, which is valid for large number of atoms, and then you'll be asked about the number of lines falling in a particular series. For that, this result is important. I hope I'm clear to this. Let's try to solve certain questions by means of which all these things will be clear. Look at the question and try to solve quickly. Hydrogen atom in the ground state. Hydrogen atom in the ground state is excited by the monochromatic radiation of wavelength lambda. On coming back to ground state, 15 different spectral lines were observed. Calculate lambda. Hydrogen atom in ground state is excited. Quickly, can you give it a try? It's a simple question, formula based one. Formula based one. Formula based one. As per the question, first of all, initially the hydrogen was present in the ground state. So N is equal to 1. So hydrogen was initially present in the ground state. Then it's excited to a higher energy state. It is excited to a higher energy state. Okay. Then what happens when the electron comes from N2 to N1? When the electron comes from N2 to N1, what is observed? In total, 15 spectral lines are observed, right? In total, 15 spectral lines are observed. So first of all, maximum spectral lines observed is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. This is equal to 15, correct? So this has to be N2 minus N1 is 1. This is N2, right? This one cancelled. Divided by 2 has to be 15. So 15 twos comes out to be 30. 15 twos comes out to be 30. So what has to be the value of N2 here? N2 has to be 6. Then only 6 minus 1 is 5. 6 minus 1 is 5. So 5 into 6 is 30. So N2 has to be 6. So basically, I got to know the electron is making a transition from 6 to 1. The electron is making a transition from 6 to 1. So first of all, we identified the transition. It is from 6 to 1. And when the electron is making a transition from 6 to 1, it will be emitting energy in the form of radiation. That radiation will be having certain wavelength as well. So 1 divided by lambda is equal to R. Z square, that's 1. 1 upon N1 square minus 1 upon N2 square. Right? So 1 divided by lambda is equal to R. This is 1 minus 1 upon 6, 36. So it has to be 1 divided by lambda is equal to R. 36 minus 1 is 35. So 35 divided by 36. So I'll say lambda is equal to 36 divided by 35. 1 by R is nothing but 911.5 angstroms. So this is the wavelength emitted, which I was supposed to calculate. I hope I'm clear. I hope I'm clear with this. You got the concept of solving? Yeah? I hope you got the concept of solving. Can you solve this one? In hydrogen-like atom, electron makes a transition from fourth excited state. Fourth excited state means N is equal to 5 to second state. It is not second excited state. It is second state. It is second state. So electron is making a transition from 5 to 2. So total lines, total spectral lines, maximum spectral lines, N2 minus N1, N2 minus N1 plus 1 divided by 2, right? So 5 minus 2 is 3. 5 minus 2 is 3. 3 plus 1, 4. Divided by 2, 3, 4, 12. 12 divided by 2 is 6. So in total, 6 spectral lines. In total, 6 spectral lines, right? So 6 spectral lines are observed in total. Perfect. And out of these spectral lines, how many will fall into Balmer, Paschen, etc.? You can do that. N2 minus ground state of that series. I already gave you the result. 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 Okay. When it comes to de Broglie's hypothesis, again, this is something which you would have studied in physics, right? Are you done with de Broglie's hypothesis as well? In the dual nature you would have studied. Quickly. See guys, I hope you already would have studied this, right? Let's quickly revise this. Let's quickly revise this. Let's quickly revise this. Let's quickly revise this. First of all, de Broglie's hypothesis, what it explains? It explains what? The dual nature of matter, right? It explains the dual nature of matter. For example, if you talk about light, right? We say light has got the dual nature. What does that mean? That means some of the phenomenon shown by the light, are explained by considering light to have the particle nature, and some of the phenomena shown by the light are explained by considering light to have the wave nature, right? So light, in short, it has got dual nature, wave nature as well as particle nature. Similarly, what de Broglie exactly said, matter can also behave as a wave. Matter, anything, this object, it can behave as a wave, right? Matter can also behave as a wave, right? And the wave nature of the matter, it was proven by Davison-German experiment. This is something which you would have studied in physics. I do not have to go into the details of this experiment, right? So de Broglie said, according to this hypothesis, matter can also behave like a wave, and it was further supported by this particular experiment. Now let's have a look what this de Broglie's hypothesis is all about. As per de Broglie's hypothesis concerned, if you have got an object which has got certain mass, if you have got an object, right, having certain mass, moving with certain velocity. This is the object, for example, which has got the mass m and it's moving with velocity v. Can I say this object, there is a linear momentum associated with this object, right, which is equal to m multiplied by v. There is a linear momentum associated with this object, which has got mass velocity v, and that linear momentum is m multiplied by v. Now, as per de Broglie is concerned, when the object having certain mass moving with certain velocity, right, apart from its particle nature, there will be a wave associated with it. And that wave he called as the matter wave, or you can call that wave as the de Broglie's wave. You can call that as de Broglie's wave as well. So whenever you'll see an object moving with certain velocity, apart from the particle nature which the object has, it would be having the wave nature associated with it as well. That means there will be a wave associated with the object as well, and that wave is something which you call as matter wave or de Broglie's wave. If there is a matter wave or de Broglie's wave associated with every particle, right, which has got certain mass moving with certain velocity v, right, that matter wave will be having certain wavelength as well, and that wavelength is what you call as de Broglie's wavelength. That's called as de Broglie's wavelength. And over here, what he concluded, de Broglie concluded that the wavelength, de Broglie's wavelength, and the linear momentum, they are inversely related. Lambda is inversely proportional to P, and you can finally remember the result. Lambda is equal to h divided by mv. I'm not going into the details of everything. I'm just showing you the results right now, and I'll tell you exactly how do we apply them in the questions, right? So lambda is equal to h upon what? H upon mv. For example, my dear students, for example, this is the pen, right? You're throwing it. I'm throwing this pen. This pen has got the mass. It has got certain velocity, right? So it has got the particle nature. It has got the linear momentum associated with it. Now, apart from the linear momentum, apart from the particle nature, there will be a wave associated with this particle as well. That wave is what you call as de Broglie's wave, whose wavelength is lambda. And de Broglie gave the relation between lambda and P. So lambda is equal to h divided by P, or you can say lambda is equal to h divided by mv. Point number 1. This is your de Broglie's wavelength in terms of momentum. Now, you can write it like this as well. Lambda is equal to h upon, instead of P, you can write under root of 2m multiplied by kinetic energy of that particular particle. This is the de Broglie's wavelength in terms of kinetic energy. H divided by under root of 2m multiplied by kinetic energy. Similarly, if you have got a charged particle, accelerated, under the potential difference V, then de Broglie's wavelength associated with that charged particle, which is accelerated at a potential V, it is equal to h upon under root of 2m. What is kinetic energy? It can be written as Q, charge on the particle multiplied by potential difference at which it is accelerated. One more thing. If that charged particle is electron, I'll say if an electron is accelerated, at a potential difference of V, then de Broglie's wavelength associated with the electron will be equal to 12.27 divided by under root of potential difference at which it's being accelerated. So these are few results which I would want you guys to remember, because questions will be asked out of these particular results as over here, right? Okay. And one more result. Remember it directly, 2 pi r is equal to n lambda. I believe you would have studied this result. 2 pi r is equal to n lambda, where r is the radius of the shell, lambda is the de Broglie wavelength, right, associated with the electron, n is the shell number, rest everything is constant. There can be one more question asked. Number of waves made by an electron when moving in a particular shell, it's always equal to n. It's always equal to n. If the electron is moving in the first shell, it will make only one wave. If the electron is moving in the second shell, it will make only two waves. Third shell, three waves. Fourth shell, four waves. Right? Perfect. Let me exactly show you where do we use all this. First of all, tell me the answer of this particular question quickly, without wasting a lot of time. Quick. Quick, people. Tell me the answer of this particular question quickly. Is it done? Is it done, guys? If the kinetic energy of the proton is increased 9 times, the wavelength of de Broglie's wave associated with it would become. I told you lambda is nothing but h divided by under root of 2m multiplied by kinetic energy. Okay? Now, if the kinetic energy is made 9 times, if it is made 9 times, that 9 comes out of the root as 3, it becomes 1 by 3. So, new wavelength will be 1 by 3 times the old wavelength. New wavelength will be 1 by 3 times that of the old wavelength, right? It was a simple basic question. It was a very simple and basic question. Okay, now comes one more important topic, right? It's been very long. A question is not asked from this. That is your Heisenberg's uncertainty principle. Perfect. Let me see what kind of questions can be asked. Let me show you. Perfect. I'm not going into the detailed explanations, etc., right? We'll just see the mathematical part and see what kind of equations can be asked. I mean, what kind of questions can be asked from your Heisenberg's uncertainty principle. First of all, I would want you guys to remember its statement. It states that the momentum and the position of a microscopic particle like electron, the momentum and the position of a microscopic particle like electron cannot be calculated simultaneously with 100% accuracy. The exact position and the momentum of a microscopic particle like electron cannot be calculated simultaneously with 100% accuracy. Cannot be determined simultaneously with 100% accuracy. If you will try to get the position of the electron, right? If you try to calculate the position of the electron with 100% accuracy, there will be error or uncertainty in its momentum. Similarly, if you try to calculate the momentum of the electron with 100% accuracy, there will be uncertainty into its position. So both cannot be calculated simultaneously with 100% accuracy, right? Both cannot be calculated simultaneously with 100% accuracy. If you want to check the position, there will be uncertainty in the momentum. If you want to go for momentum, there will be uncertainty in the position, right? Perfect. And I'm writing a term delta x. What is delta x? That is error or uncertainty. Error or uncertainty in position. Error or uncertainty in position. Delta V is error or uncertainty in velocity. Delta P is error or uncertainty in momentum, m delta V. Delta P can be written as m delta V. This is error or uncertainty in the momentum. Correct? Similarly, delta lambda. Delta lambda can be written as h divided by m delta V, right? Which is error or uncertainty in de Broglie wavelength. Perfect, right? And as per your Heisenberg's uncertainty principle is concerned, error in position multiplied by error in momentum is greater or equal to h upon 4 pi. This is the statement which you need to remember. Number one. Number two, you can write delta x, delta p is m delta v. I can write delta x dot delta v is greater or equal to h upon 4 pi m. This is one more result of your Heisenberg's uncertainty principle. This one more result of your Heisenberg's uncertainty principle. There is one more result which I would directly want you to remember here, right? I'm not deriving that. That is delta x dot delta lambda. Delta x dot delta lambda. Delta x, error in position, error in de Broglie wavelength, it is greater or equal to lambda square divided by 4 pi. It is greater or equal to lambda square divided by 4 pi. This is one more result which I would want you to remember. One more result of the de Broglie hypothesis which I would want you to remember. First one is delta x delta p is greater or equal to h upon 4 pi. Second is delta x delta v greater or equal to h upon 4 pi m. Third is delta x delta lambda is greater or equal to lambda square divided by 4 pi. These are the three results from which the question is going to be asked. For example, let me show you one. Let me show you one. If you look at this particular question, an electron is accelerated from rest by applying a voltage of 6 volts. Can you calculate the lambda for it first of all? It will be 12.27 divided by under root of V. What is V? Under root of 6. Perfect. From here you can calculate lambda in angstroms. So you got lambda first of all. Delta X is error in position is already given. 7 divided by 22 nanometers, right? Into 10 raised per minus 9 meters. What do we have to calculate? Delta lambda. Delta lambda is to be calculated. What just happened? So night mode on. Night mode on. So basically you calculated delta x, you calculate lambda. Now you have to calculate delta lambda. How do I calculate delta lambda from here? This result. Delta x we calculated, right? Lambda we calculated. 4 pi you already know. So from this equation you can easily get the delta lambda value, right? You can easily get delta lambda value. I believe all these things can be done. For example, you have got one more question. If the error in velocity is delta v. If the error in velocity and position are same, if these two are same, what will be the error in de Broglie's wavelength? What will be the error in de Broglie's wavelength? What is de Broglie's wavelength all about? Delta lambda. That's h upon m delta v. H upon m delta v. So basically you have to get the value of delta v. Now you know delta v dot delta x. I'll use the equal sign here. Is equal to h upon 4 pi m. Correct? H upon 4 pi m. If delta v, delta x are same, I can write it as delta v ka square is equal to h upon 4 pi m. So from here, you can get the value of delta v, which is equal to under root of h upon 4 pi m. Under root of h upon 4 pi m. Now, this delta v value, I will be putting here, right? So I'll be getting delta lambda is equal to h upon m. What is delta v? Delta v is under root of h upon 4 pi m. So delta lambda you can calculate from here. If you take the root common, this will be h square divided by, this m will come inside, this is h, m square divided by 4 pi m already here. Now see what all things will get cancelled, h gets cancelled, mm gets cancelled. So my final result is going to be under root of 4 pi h divided by m. This is the value of delta lambda which we were supposed to calculate. I hope this is also clear to every one of you. Right, people? These are the different types of questions which can be asked from your Heisenberg's uncertainty principle as well. Now, what are quantum numbers? What are quantum numbers? Guys, one topic in atomic structure I won't be teaching you, that is electronic configuration, because I believe you already know, right? That 1s2, 2s2, 2p6, etc., etc. Correct? That will be, I believe you know that. Yeah? Okay? One topic, that's electronic configuration, how to write the electronic configuration of different elements. You should be knowing that. You should be knowing that. All the things clear till here? All the things clear till here quickly? All right, so now we'll be talking about something called as quantum numbers. What are quantum numbers exactly? My dear students, quantum numbers, these are the set of four numbers. These are the set of four numbers which are required to locate an electron in an atom. These are the set of four numbers which are required to locate an electron in an atom. You know, in the atom, what do we have? We have got shells. Now, in the shells, what do we have? Subshells. In the subshells, what do we have? Orbitals. With the help of these quantum numbers, you will get to know exactly. You will get to know exactly in which orbital of which subshell of which shell electron is present. So, quantum numbers, they give us exact information about an electron in an atom. How many quantum numbers we have in total? We have got 4 quantum numbers in total. Principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. Out of these 4 quantum numbers, the first 3, they are the outcome of Schrodinger's wave equation. The first 3 quantum numbers are the outcome of Schrodinger's wave equation. Your principal quantum number represented by N, right? Azimuthal represented by L, magnetic represented by M. And you know, spin, that is represented by S. Now, one by one, we shall see what these quantum numbers exactly are all about and how they are going to give us the information about everything. First of all, principal quantum number, that is represented by N. Principal quantum number lets us know exactly. It gives us the idea of in which shell the electron is present. Principal quantum number gives me the idea of in which shell basically electron is present. Let's say I'm saying N is equal to 1. N is equal to 1 means the first shell, which is what you call as K shell. So the electron is present in first shell, right? If N is equal to 2, that means electron is present in the second shell, which is called as L shell. N is equal to 3, electron is present in the third shell. Similarly, N is equal to 4, electron is present in the last fourth shell. So basically, with the help of principal quantum number, we can check exactly in which particular shell electron is present. That's all. That's all. It represents the size and the energy of the shell as well, right? This is something which you know. As the value of N increases, size and energy of the shell increases. The maximum number of electrons which can be accommodated in a particular shell. The maximum number of electrons which can be accommodated in a particular shell, that's equal to N square, right? So if N is equal to 1, if I talk about the first shell, in the first shell there'll be 2 electrons. In the second shell there'll be 8 electrons. In the third shell there'll be 18 electrons, right? The maximum number of electrons which can be accommodated in a particular shell, that's equal to N square, right? So this was your principal quantum number. Now comes the actual one. That is your azimuthal quantum number. That is your azimuthal quantum number. Just a second. That's your azimuthal quantum number. My dear students, azimuthal quantum number, it gives the idea about, azimuthal quantum number gives us the idea about, it gives us the idea about the subshell in which the electron is present. In which the electron is present. This azimuthal quantum number, its value is from 0 to n minus 1. And let me tell you, every value of azimuthal quantum number represents a subshell. Every value of azimuthal quantum number, it represents what? It represents the subshell. Every value of azimuthal quantum number, it represents the subshell. Okay? L is equal to 0 represents your S subshell. L is equal to 1 represents your P subshell. L is equal to 2, it represents your D subshell. L is equal to 3 represents your F subshell. F subshell. Now have a look. Try to understand. Try to understand what exactly I'm going to talk about. My dear students, for example, n is equal to 1. N is equal to 1 means the first shell, your K shell. Right? What can be the possible values of L? L is from 0 to n minus 1. So 0 to 1 minus 1. So L is equal to 0. So how many values of L did I get over here? I got one value of L, which came out to be 0. Every value of L represents a subshell. So we got one value of L. We got one value of L, which is equal to 0. Right? So L is equal to 0 will be representing a subshell, and that particular subshell I'll be calling as S subshell. So basically in your first shell, there is one subshell, that's S subshell. That is S subshell. Okay. Similarly, N is equal to 2. The second shell, L shell. How many L values will be getting over here? How many L values I'll be getting over here? 0 to 2 minus 1. 0 to 2 minus 1. So L is 0, L is 1. L is equal to 0 represents your S subshell. L is equal to 1 represents your P subshell. So basically in your second shell, there are two subshells, S and P. In your third shell, how many subshells will be there? There'll be 3 subshells, right? Similarly, in your fourth shell, how many subshells will be there? There'll be 4 subshells. So basically, every value of azimuthal quantum number represents a subshell. Right? Represents a subshell. Right, people? So in your first shell, there is one subshell. Second shell contains 2 subshells. Third contains 3 subshells. This carries 4 subshells. Right? Now, guys, there is one important question basically here, which is asked. That is about orbital angular momentum. Calculation of orbital angular momentum, which is equal to under root of L into L plus 1 h upon 2 pi. Right? This is how you calculate orbital angular momentum. Question is asked frequently on this as well. For example, you'll be asked to calculate the orbital angular momentum of 2s, 2p, let's say 3d, right? How do you do that? For s subshell, L is equal to 0. For p subshell, L is equal to 1. For d, L is equal to what? L is equal to 2. Now you can just use the formula. Orbital angular momentum is equal to under root of L, 0. So this whole term is 0. Orbital angular momentum here will be equal to under root of L into L plus 1 h upon what? 2 pi. So this is root 2 h upon 2 pi, which is coming out to be under root of h upon under root of 2 pi. Perfect. Right? Similarly here, L is equal to 2. So under root of 2 into 2 plus 1 h upon 2 pi. 2 plus 1 is 3. 3 2s are 6. So root of 6 h upon 2 pi is the orbital angular momentum here. And here the orbital angular momentum was 0. So basically with the help of this result, from this particular result, the question is frequently asked. Orbital angular momentum. It is just you should know the value of L, nothing else. You're done. You're sorted. Okay? Right, people? Am I clear? Am I clear with this? Am I clear with this? I hope this particular table you know, you got to know. How do we get? Now comes your magnetic quantum number. Magnetic quantum number is represented by what? It is represented by M. It is represented by M. Let me be very short and precise, like what kind of information it gives us. See, principal quantum number gives us the idea about the shell number. Azimuthal quantum number gives me the idea about the subshells. Okay. Magnetic quantum number gives me the idea about the orbital. It gives the idea about the orbital. Every value of M represents an orbital. Every value of M represents an orbital. And how do we get this M value first of all? It is from minus L to plus L. How do we get this M value? It's from minus L to plus L. Minus L to plus L. Now have a look. In case of S subshell, what is the value of L? L value is 0. If L is 0, M will be 0 only. So how many values of M I got? One value of M, that is 0. And every value of M represents an orbital. So in case of S subshell, there is only one orbital. In case of S subshell, there is only one orbital. In case of S subshell, there is only one orbital. Right? Let's say I'm talking about P subshell. let's say I'm talking about P subshell. L is equal to 1. So how many M values can be there? M is from -1 to +n. So -1, 0, +1. So we got 3 values of M, right? 3 values of M means 3 orbitals. So in P subshell, there are 3 orbitals. One is designated as Px, one is called as Py, one is called as Pz. One is called as Pz. Similarly, if I talk about your D subshell, L value is how much? 2. M will have how many values? 5 values. -2, -1, 0, +1, +2. So 5 values of M means 5 orbitals, right? 5 orbitals in D. So in your D subshell, there are 5 orbitals. One is called as dxy, one is called as dyz, one is called as dxz, one is called as dx square minus y square, and one is called as dz square. Similarly, if you talk about F subshell, in your F subshell, how many orbitals we have? In your F subshell, there are 7 orbitals, and their shapes are complex, etc. Right? Just remember it directly. Okay? Perfect. So basically, your magnetic contour number, it gives me the idea about what? It gives me the idea about the orbitals. Perfect. I hope I'm clear with this. So look at this particular table, guys. N is equal to 1 means first shell. In the first shell, L value is 0. L value is 0. That means every value of L represents subshell. In your first shell, there is only one subshell. What do you call that as? S subshell, right? M is 0, 1 orbital, S orbital. So second shell, L can have 2 values. These are the possible values of M, right? So S orbital and 3 p orbitals. Same goes for D, whatever I've discussed with you till now. Correct? So in short, if you see in first shell, there is 1 orbital. In second shell, there are 3 plus 1, 4 orbitals. In third shell, there are how many? 9 orbitals. 5, 3, 8, 1, 9. So total number of orbitals in a particular shell. Total number of orbitals in a particular shell is equal to what? It's equal to n square. It is equal to n square. Okay? It is equal to n square. I hope you guys are clear with this as well. Okay? I hope you guys are clear with this as well. And my dear students, spin quantum number you already know. It gives us the idea whether the electron is going with clockwise spin or anti-clockwise spin. Right? S can have 2 values, plus 1 by 2, minus 1 by 2. Plus 1 by 2, minus 1 by 2. Okay? This represents clockwise spin. And this represents anti-clockwise spin. If the electron is going with clockwise spin, so plus 1 by 2 S value, right? Anti-clockwise spin, minus 1 by 2 S value. The most important topic of this particular chapter, the most important topic from which surely this year you are going to get the question, that is going to be your nodes and your probability distribution diagrams. But before that, before going into that, I'm going to give you the idea about the shapes of orbitals as well. Then we'll go into the nodes, etc., right? Shapes of orbitals. The first orbital which you all must be knowing, that is your S orbital. Right? S orbital. And you know, S orbital is spherical in shape. S orbital, it is spherical in shape. S orbital is spherical in shape. For example, like this. Let's say this is the nucleus. Around the nucleus, you will find a spherical region. Wherein the probability of finding the electrons will be maximum. That spherical region around the nucleus, wherein the probability of finding the electron will be maximum. That's what you call as S orbital. Number one. Similarly, how your p orbital exactly looks like? If I ask you, it's a dumbbell shape, right? It's dumbbell shaped. Perfect. It is dumbbell shaped. So I'll be representing it like this. This is the nucleus here, right? This is one lobe of the p orbital. This is one more lobe of the p orbital. I'm roughly showing you how these orbitals exactly look like, right? In detail, I'll show you in some time. Perfect. If, for example, this is the internuclear, if let's say I'm calling this a z-axis, then this becomes your pz orbital. If I call this as x-axis, then it becomes px. If I call this as y-axis, then it becomes py, right? It's a dumbbell-shaped one. Similarly, your d orbitals. If you talk about your d orbitals, how many d orbitals do we have exactly? 5 d orbitals. What all? dxy, dyz, dzx, dx square minus y square, dz square, dz square. These three are what you call as non-axial orbitals. These are called as non-axial d orbitals. These are called as axial d orbitals. In case of non-axial d orbitals, electron density, it lies between the axes. Here, electron density lies along the axes. Along the axes, right? Let me show it to you. For example, this is x, this is y. Double shaped. This is going to be your dxy. This is going to be your dxy orbital, right? Let's say this is y and this is z. This is going to be your dyz orbital. dyz, right? dyz. Let's say this is x and this is z. This is going to be your dxz orbital. This is going to be your dxz orbital, right? What about dx square minus y square and dz square? See guys, let's say this x-axis, this y-axis, and these are the lobes here. This is your dx square minus y square. Lobes are along the axis. How the dz square looks like? How the dz square looks like? How the dz square looks like? Have a look exactly how this dz square looks like. Let's say this is your x-axis, this is your y-axis, and for example, this is your z-axis. This is your z-axis, right? This is one of the lobe. This is one more lobe here. And there'll be electron density on this plane as well. Bangle kind of electron density, a bangle-like electron density which will be present on xy plane as well. This is how your dz square exactly looks like. This was the quick visualization of how these orbitals exactly look like. S is spherical, P is dumbbell, D is double dumbbell, right? D is double dumbbell. And this is your dz square here. Now guys, talking about this a bit more in detail, right? Before talking about the shapes of these orbitals a bit more in detail, you should first of all know how do we calculate the nodes. What is a node? Node is first of all a region where the probability of finding the electron is 0. Region where the probability of finding the electron will be 0. Now, I'm not going into the definition and stuff. I just need to tell you your nodes, total number of nodes, are calculated with the help of the formula n-1. These nodes exactly are of two types. One is called as spherical or radial nodes. One is called as angular nodes. Angular nodes are calculated with the help of L value. Whatever is the L value, same angular nodes. Spherical nodes will be n minus L minus 1, right? This is the first thing which you need to know. Now let's have a detailed discussion about these nodes and the shapes, etc., etc. For example, guys, let's say you have got 1s. In case of 1s, what is the value of n? N is 1. What is the value of azimuthal quantum number? That is 0. How many total number of nodes will be there? N minus 1. There is no node. There is no region wherein the electron density is 0. Okay? Total number of nodes is 0. So how this 1s will look like? This is the nucleus, for example, and this is the region around the nucleus wherein the probability of finding the electron is maximum. So this is your s orbital. Do you see any region over here? Do you see any region wherein the probability of finding the electron is 0? No. There's no region like that. So there is no node over here in 1s. Okay. Now here we have to plot two graphs. Here we have to plot two graphs. One is psi versus r graph. Second one is psi square versus r graph. Second one is psi square versus r graph. These are the two graphs which can be asked. Remember, in case of S, all the psi versus r or psi square versus r, they start from top. They start from top, right? They start from top. So the graphs will be like this. These graphs, they won't be touching the r-axis. Why? Because if the graph touches the r-axis, at that point of time, psi square becomes 0. Psi square 0 represents node. Psi square is equal to 0. That represents a node. But in 1s, there is no node. There is no node. Okay? Therefore, it's not going to touch the r-axis. Okay? Let's say I'm talking about 2s. Just give me a second. Just a second. Okay, have a look here. In case of 2s, if I ask you about 2s, what is the value of n? N is 2. What is the value of L? L is 0. Total number of nodes, n minus 1. 2 minus 1 is 1. Right? Now, since total number of nodes are 1, now which node is it? Is it spherical or angular? Calculate. Spherical nodes is equal to n minus L minus 1. It comes out to be 1. Therefore, angular node is equal to L. L is 0. So first of all, you should be in a position to check total nodes and spherical and angular nodes. Now after this, first thing, there is one node. Which node is that? Spherical node. So in 2s, you will find one spherical region. Wherein the probability of finding the electron will be 0. Have a look. Imagine this is your 1s. After this 1s, you'll find a region wherein nothing will be present. It is blank. And after that region, electron density will start. Okay? Right? So, if you look here, this region over here, I'm calling what? I'm calling it a spherical node. This is a spherical region wherein the electron density is 0. Okay? This is the spherical region where the electron density is 0. Now, how do you make it psi versus r and psi square versus r graph? Have a look. This, for example, psi versus r. Similarly, this is psi square versus r. All the S graphs for psi versus r and psi square versus r, they start from the top, come downwards, right? For 2s, it will start from here and will come like this, right? At this particular point, it represents a node. Now, because the node is 1, there is one node and this is that node which I'm representing over here. Now you have to make psi square versus r. Is there any portion of this particular graph which is lying down r-axis? Yes, this portion. Take the reflection of this portion. From here to here, it's okay. Now, take the reflection of the other portion. It comes like this. Okay, this is psi square versus r for 2s. Okay, the psi square versus r for 2s. Now, for example, you have got 3s. I believe you can make all these things for 3s as well. For 3s, your n value is 3, your L value is 0, total nodes, 3 minus 1 is 2, angular nodes, L, that is 0, radial nodes or spherical nodes, you call them spherical nodes, right? Spherical nodes will be n minus L minus 1, that will be 2. So if spherical nodes are 2, that means there will be two spherical regions. There will be two spherical regions wherein electron density will be 0. Two spherical regions wherein electron density will be 0. So I have to show 3s. But before that, let's say this is 1s which I'm representing, right? After 1s, there will be a spherical node. Then there will be 2s. This is your 2s. After that, there will be one more spherical node. This is one complete 3s over here. How many spherical regions you are seeing over here wherein the electron density is 0? 1 and 2. So there are 2 spherical nodes present in case of what? In case of 3s. If I make the psi versus r graph, you can do that. Psi versus r. Or if you want to make psi square versus r graphs, you can do that as well. So first of all, how many nodes are there? 2 nodes. 2 nodes. So the curve should touch 2 times r axis. This is 1, this is 2. Done. Is there any portion of the graph lying down the r axis? Yes, this portion. Now take the reflection of it. When you take the reflection of it, it comes up like this. Okay, these are the 2 spherical nodes. These are the 2 spherical nodes wherein psi square is r. I hope this is clear. This was about S. Now, what about P? What about P? Let's say you have got 2P. Let's say you have got 2P. First of all, 2P, it is dumbbell shaped. I mean, P is dumbbell shaped. It is dumbbell shaped, number 1. Number 2. Number 2. In case of 2P, what do we have? In case of P, what do we have? Let me tell you, in case of P, your psi versus r graph and psi square versus r graph, right? They start from origin. They start from origin. How exactly? Have a look. N is equal to 2, L is equal to 1. Correct? Total number of nodes is n minus 1. And this node will be angular node for sure. Right? Because L is 1. Spherical nodes will be 0. N minus L minus 1 will be 0. So basically, there is one angular node. There is no spherical node. See how it looks like. This is the nucleus. This is one lobe of it. This is one more lobe of it. Right? There will be no spherical region here wherein the probability of finding the electron is 0. But if you cut the orbital in the middle, there will be a plane. There is a plane which cuts the orbital in the middle. There is a plane which cuts the orbital in the middle wherein the probability of finding the electron is 0. And this plane is something which you call as nodal plane, or you can call it as angular node. You can call it as angular node. This is the plane in the middle wherein the electron density will be 0. Right? This plane is something which you call as the nodal plane, or you can call it as angular node. Now, how the graph will look like? Let me show it to you. This is psi versus r. And over here, this is, for example, your psi square versus r. These graphs, they start from the origin, right? From here, like this. Perfect. There is no part of the graph lying down it, right? So, no need to take reflection of anything. So, this is the graph of 2P. This is the graph for 2P. Now, let me show for 3P so that it becomes clear. If you talk about 3P, N values 3, L values 1, total nodes N minus 1, angular nodes L value, spherical nodes N minus L minus 1. So there are total 2 nodes, out of which one is angular and one is spherical. So there will be one plane as well as there will be one spherical region wherein the electron density will be 0. Okay? And how it exactly looks like? Just a second. See guys. This is the nucleus, for example. This is your 2P. These are the 2 lobes of 2P. Right? After this, you will find a spherical region wherein electron density is 0. And after that, electron density will again start like this. Okay? So this is a spherical region wherein electron density is 0. So this is a spherical node. Apart from this. This is a plane. This is a plane on which electron density is 0. This is a plane, and you call this plane as the angular node. So one spherical region and one angular node. How do I show it over here? This is, for example, your psi versus r, and over here I'm showing psi square versus r. Okay? So the graph starts from the origin. From here it will start, and this is your spherical node here, right? This is your spherical node here, this one. Perfect. And it comes like this. Perfect. So is there any part of the graph lying down r-axis? Yes, this part. So take the reflection of it. So from here to here, it's same. Then take the reflection. This represents your radial node, your spherical node. So this is how you make the graphs for your 3P as well. Perfect, guys? Similarly, you can make for 4P. Perfect. For 4P, there will be one more like this. Perfect. For 4P, it will go from here to here. For 4P, it will come down a bit, then go up. Yes? My dear students, one topic which I'm keeping for you, that is electronic configuration. I'm not going to teach you electronic configuration. That's something which you will do on your own, because I believe every one of you would be already knowing how to write the electronic configuration of different elements, hydrogen, helium, lithium, etc., etc. Okay. The next chapter which we are going to start with this, your atomic structure. And guys, nothing is going to be asked apart from all these things. Only remember the electronic configuration of chromium and copper. Chromium 3d5 4s1, copper 3d10 4s1. Reason? In case of chromium, half-filled configuration is more stable due to exchange energy or symmetry, right? Do remember that. Now, you tell me which chapter we are going to start the next. We'll be starting chemical equilibrium, but this chemical equilibrium chapter will be started after a break, right? The time right now is 12:40 almost. So, break till, I'm giving you the lunch break, okay? Guys, be back on time, but okay? Please and please be back on time. This is the most important chapter which we are going to start now. All right? Thermodynamics we have completed in the last session. There is only thermochemistry part left in that. There is only thermochemistry part which is left there. Dynamics part we have completed. Okay? I would want every one of you to be back exactly at 1:15, because at 1:15 we shall start this, one of the most important chapters. That is your chemical equilibrium. Okay? See you after the break. Take care. Is everyone back? Is everyone back? Yes. All right. So, people, is the atomic structure part clear? Is the atomic structure revision clear to you? Let me know quickly in the chats. Perfect. Perfect, guys. Okay. Have you studied this chapter before, chemical equilibrium? Just say yes or no in the chats once. I just want to see. Have you studied this particular chapter before, the chemical equilibrium? All right, okay. Got it. Chalo, let's start with the chapter then, chemical equilibrium. Okay, this is one very, very, very important chapter, I must say. From in your upcoming NEET 2024 examination, from the equilibrium chapter, you can expect 3 to 4 questions for sure. 3 to 4 questions you are going to expect from this chapter this year, right? Okay, so I'll be starting from the basics only. Correct, I'll show you the different problem patterns which can be asked. You need not to worry. The ones who think that this chapter is tough, it is not tough, provided you know the basics properly. Okay? Perfect then. So let's get going. Let's get started with the chapter chemical equilibrium. So first of all, my dear students, let's start the chapter from certain basic things which you must know. And what are those basic things? Let's have a look. My dear students, the first thing. Let's say you have got a reaction as A gives B. Let's say this is one reaction. I'm assuming that this reaction is taking place in a container which has got volume V liters. V liters is the volume of the reaction vessel. V liters is the volume of the reaction vessel. I'm defining a term concentration here. How do you define the concentration? Moles per unit volume. Moles per unit volume, right? Now, my dear students, if I ask you, as the reaction proceeds, what happens to the moles of reactants with time? Can I say moles of reactants with time decreases and moles of product with time increases? Absolutely. Over here, if I define the term concentration of reactant means moles of reactant divided by volume of the reaction vessel in liters. Similarly, concentration of product, moles of product divided by volume of reaction vessel in liters. Now, I told you, as the reaction proceeds, number of moles of reactant decrease with time, number of moles of product increase with time. Therefore, if moles of reactant decrease with time, I would say concentration of reactant decrease with time. Similarly, concentration of product increases with time because they are directly proportional to each other. So do remember, as the reaction proceeds, moles of reactant decreases and moles of product increases. Also, concentration of reactant decreases and concentration of product that increases with time. Okay. Now, my dear students, if I want to plot the same thing graphically, I can do that as well. If I make the graph between concentration versus time for reactants and products, you should be able to draw this graph. Concentration versus time. Now, since we know concentration of reactant decreases with time, so with time the concentration of reactant will keep on decreasing, and with time the concentration of product will keep on increasing. Therefore, this particular graph, it is valid for the reactant And this particular graph, it is valid for the product. It is valid for the product. Okay, I'm just telling you the basic things which are required in this chapter. Okay, I hope these two things, these small things, they are absolutely clear to you. Now, my dear students, one more thing I would want to share with you here. For example, you have got the reaction. A gas, it gives B gas. A gas gives B gas. Let's assume that this reaction, it is taking place in a closed container. In a closed container. If I say time t is equal to 0, at time t is equal to 0, at time t is equal to 0, when the reaction has not started, when the product formation has not taken place, can I say at time t is equal to 0, I'll be only having moles of A in the container, moles of B in the container will be 0. If I ask you something, at time t is equal to 0, how many gases are there in the container? At time t is equal to 0, how many gases are there in the container? I'll say there'll be only one gas in the container. That's going to be gas A. Initially, there won't be gas B in the container. So, at time t is equal to 0, there is only one gas in the container, that is gas A. So, initially, whatever will be the total pressure, that total pressure is only due to what? That total pressure is only due to what? That's only due to A. That's only due to A. Correct? That's only due to A. Because there is no B in the container at time t is equal to 0. Now you tell me, as the reaction proceeds, number of moles of reactant, they decrease with time. Number of moles of product, they increase with time. If number of moles of reactant decrease with time, that means the amount of gas A in the container is decreasing with time and amount of gas B in the container is increasing with time. For example, at a given time t, if I ask you at a given time t, how many gases will there be in the container now? There will be now 2 gases in the container. There will be some moles of gas A in the container and some moles of gas B which would have got formed. So, at time t, there will be 2 gases in the container. Correct? So, can I say at time t, there is a gaseous mixture present? There is a gaseous mixture present. Let the total pressure of the gaseous mixture at time t be Pt. This is the total pressure of the gaseous mixture at time t, which will be equal to total pressure of the mixture at time t. Total pressure of the mixture at time t. Will the total pressure of mixture be only due to gas A, only due to gas B, or both would have contributed? I'll say at time t, both the gases will contribute towards the total pressure of the mixture. And as per Dalton's law, the total pressure of the mixture will be the sum of partial pressures, will be the sum of the contributions made by each gas A and B. So what is PA? PA is the contribution made by gas A towards the total pressure at time t. PB is the contribution made by gas B towards the total pressure at time t, which is what you call as partial pressures. I hope you know it. I hope you know it. Perfect. This is just the basics which I would want you guys to know. Now think over one thing. As I told you, as the reaction proceeds, number of moles of A will decrease with time. Therefore, pressure due to A will decrease with time too. So remember this thing. As the reaction proceeds, pressure due to A, it decreases with time. It decreases with time. And pressure due to B, that increases with time. That increases with time. Do remember these two things as well. So my dear students, till now, I told you as the reaction proceeds, moles of reactant decreases, concentration of reactant decreases, pressure due to reactant, that also decreases with time. Similarly, moles of the product increases, right? Concentration of the product increases, pressure due to product, that also increases with time. Okay? So these are the few things which I would want all of you to remember. Point number 1. Point number 2. I did not define the term equilibrium yet. Before defining the term equilibrium, let me tell you. Do you remember in the last session, we have discussed law of mass action? Anyways, I'm going to define law of mass action again in some time, right? I'm going to define law of mass action again in some time. For example, you have got the reaction A gives B. Let's say you have got the reaction A gives B, right? I'm keeping the sign reversible over here, right? It's a reversible reaction. I'm assuming that I've got the reaction which is reversible. Reversible means this reaction proceeds in both the directions, forward as well as backward. It's a reversible reaction. It is a reversible reaction, correct? If it is a reversible reaction, can I say actually these are two reactions? This is your forward one and this is your backward reaction. This is your forward reaction and this is your backward reaction. Okay. In the forward reaction, your reactant is A. In the backward reaction, your reactant is B. In the forward reaction, your reactant is A. In the backward reaction, your reactant is B. Correct? Now, as per law of mass action is concerned, rate of reaction is directly proportional to concentration of reactant. You know it? Well, I'm going to discuss law of mass action in detailed way after some time. Over here, I just want one point. As per law of mass action, rate of reaction is directly proportional to what? Concentration of reactant, amount of reactant. As the concentration of reactant decreases, rate of reaction decreases. Okay. Now, my dear students, this particular reaction which we have, this particular reversible reaction which we have got actually two reactions, one forward, one backward. A is the reactant for forward reaction, B is the reactant for backward reaction. If I write rate of forward reaction, can I say rate of forward reaction is directly proportional to concentration of reactant, and reactant here is A. Rate of backward reaction is directly proportional to concentration of reactant, and reactant here is B. Correct? So tell me one thing. What happens basically? Initially at time t is equal to 0, there was only A in the container, right? As the reaction proceeds, concentration of A decrease with time and concentration of B increase with time. So as the reaction proceeds, concentration of A decrease with time and concentration of B increase with time. If concentration of A decrease with time, I'll say rate of forward reaction decrease with time. Therefore, if concentration of B increase with time, rate of backward reaction increase with time. So my dear students, as the reaction proceeds, rate of forward reaction decreases with time and rate of backward reaction, it increases with time. Rate of forward reaction decrease with time, rate of backward reaction increase with time. Can I say a stage will come at which rate of forward and rate of backward reaction becomes equal, and that state in a reaction at which rate of forward and backward reaction becomes equal, that state is what you call as equilibrium state. Right? So at equilibrium, what happens? I'll say at equilibrium, when equilibrium is established in a reaction, rate of forward and backward reaction, they become equal. Right? Rate of forward and backward reaction becomes equal. Perfect? Right? So this is one thing which you need to remember. When it comes to the chemical equilibrium. At equilibrium, right? This is the consequence of equilibrium basically. Okay. At equilibrium, the rate of forward and backward reaction, they become equal. If I want to show the same thing graphically, we can do that as well. This is rate versus time. You know, rate of forward reaction, it decreases with time, and then attains a fixed value. Similarly, rate of forward reaction, it increases with time, then attains a fixed value. Can I say this is the point after which rate of forward and rate of backward reaction are becoming equal, right? So this represents what? Equilibrium. So this point represents equilibrium in a reaction. Okay, this point represents your equilibrium. Perfect. Now guys, let's try to understand this equilibrium a bit more in detail, right? So that the chapter gets properly clear to you. Understand. First of all, what is equilibrium in a reaction? Equilibrium is basically a state. It is a state, right? It is a state at which entropy attains its maximum value and Gibbs free energy attains its minimum value. And as per thermodynamics point of view, that state at which entropy attains the maximum value, Gibbs free energy attains the minimum value, that is considered to be the most stable state of the system. So your equilibrium, it is basically considered to be the most stable state of the system. Equilibrium is basically considered to be the most stable state of the system. That is the reason why every reaction wants to attain equilibrium as soon as possible. Why is that? Because equilibrium is considered to be the most stable state of the system. Everything wants to attain stability, right? So in a reaction always leads towards stability. Perfect. So that is the reason why every reaction wants to attain equilibrium as quickly as possible. Why is that? because equilibrium, it is considered to be the most stable state of the system as per the thermodynamics point of view. Okay, point number one. Point number two. Understand and remember. Point number two. When equilibrium is established in the reaction, all the measurable properties, all the measurable properties of the system, like moles, like concentration, like pressure, right? When equilibrium is established in the reaction, all the measurable properties of the system, like moles, like concentration, like pressure, they attain a fixed value. So what you will see exactly, when equilibrium is established in the reaction, all the measurable properties, be it moles, be it pressure, be it concentration, whatever, they always attain a fixed value. What does that mean? That means when equilibrium is established in the reaction, the moles of reactants and products, the concentration of reactants and products, pressure of reactants and products, they become fixed. They do not change after that. So once equilibrium is established, every measurable property, it attains a fixed value. It does not change at all. Attains a fixed value. Okay. Now, one more thing. Equilibrium, it is dynamic in nature. Once equilibrium is established, after the reaction never stops. The rate with which forward reaction takes place, with the same rate backward reaction takes place. So it's always dynamic. Forward, backward, it's continuously taking place with the same rates, right? It's always dynamic in nature. It does not stop. Okay. And similarly, your equilibrium is established in closed vessels. It's established in closed vessel. Now, I'll make you understand all these things, whatever I mentioned over here. I'll make you understand all these things one by one. One by one, I'll make you understand. Try to understand carefully what I'm going to say. For example, you have got the reaction. You have got the reversible reaction. A gives B. It's a reversible reaction. A gives B. My dear students, let's assume that this reaction is taking place in a container whose volume is, let's say, 1 liter. Volume of the reaction vessel is 1 liter. Let's assume that initially at time t is equal to 0. Let's say I have got 10 moles of reactant. So this will be 0. Right? Because the reaction has not started yet. Now, my dear students, as the reaction proceeds, number of moles of reactant decrease with time, number of moles of product increase with time. Okay. I am assuming that when 20% of the reaction is completed, equilibrium is established in the reaction. Right? So, I'm assuming when 20% of the reaction is completed, equilibrium is established in the reaction. What is meant by 20% completion? 20% completion means when 20% of the reactant got converted into product. When 20% of the reactant got converted into product, at that point of time, equilibrium is established. This is something which I'm assuming. What is 20% of 10? 20% of 10 means 2. So, I'll say at equilibrium, out of 10 moles of A, 2 moles have got converted into products. So, I'll be left with 8 moles of reactant. And similarly, 2 moles of product would have got formed. Okay. Now, I'm assuming a stage has reached in a reaction at which rate of forward and backward reaction has got equal. So, if 1 mole of reactant is getting converted to product, at the same time, 1 mole of product is getting converted into reactant. So, rate of forward and backward reaction has got equal now. If 1 mole of reactant is getting converted into product, at the same time, 1 mole of product is getting converted into reactant. Right? So, once equilibrium is established, can I say moles of reactant and product, they have got fixed? They are not going to change now, as I told you, at equilibrium, all the measurable properties of the system, they attain a fixed value. So at equilibrium, right, I would say the moles of reactant and product, they have got fixed. They are not going to change now. Similarly, if I talk about concentration, of reactant product at equilibrium, concentration is moles per unit volume. Moles divided by volume. So 8 molar. Moles divided by volume. This will be 2 molar. So concentration of reactant product also have attained a fixed value. They have attained a fixed value. Perfect. Right? So moles of reactant product are not going to change now. Concentration of reactant product is not going to change now. Pressure of reactant product is not going to change now. once equilibrium is established in the reaction. So all the measurable properties of the system, they have attained a fixed value. They have attained a fixed value. Now, my dear students, if I plot the same thing graphically, let's say I'm plotting concentration versus time. Let's say I'm plotting concentration versus time. What happened to concentration of reactant? Concentration of reactant decreased initially, then attained a fixed value, right? Concentration of product increased initially, then attained a fixed value, This is the time after which, the concentration of reactant and product, they became fixed, right? And when the concentration of reactant and product attains the fixed value, we say equilibrium is established in the reaction. So at this particular point, I would say equilibrium is established in the reaction, right? Perfect. And my dear students, if you see this particular point, this is going to give you the concentration of product at equilibrium, and this particular point, it's giving you concentration of reactant at equilibrium, right? As you can see, this graph is telling you that concentration of reactant at equilibrium is greater than that of concentration of product at equilibrium. I'm sure it's clear. Similarly, I can make you understand it like this as well. Let's say you have got the reaction A gives B. Okay. Initially, we have got 10 moles of reactants, and this is 0. I'm assuming that when 50% of the reaction is getting completed, equilibrium is established. That means out of 10 moles, when 5 moles got converted into product, at that point of time, I'll be left with 5 moles of A as well as 5 moles of B, right? Now I'm assuming equilibrium is established. If equilibrium is established, the rate with which forward reaction will be going, with the same rate, backward reaction will be also going. Perfect. If I ask you what is the concentration of reactant product at equilibrium, this will be 5 molar. This will be 5 molar because volume of the system is 1 liter. Now, if I ask you, I'm telling you, since equilibrium is established, that means, will the concentration of reactant product change now? It is not going to change. If 1 mole of reactant gets converted into product, at the same time, 1 mole of product also is going to get converted into reactant. So concentration of reactant product is not going to change at all now, right? If you want to plot it graphically, you can do that as well. For example, this is concentration, this is time, right? You know, concentration of reactant is decreasing first of all, and then attains a fixed value. Concentration of product also increases with time, then attains a fixed value, right? This is the time after which the concentration of reactant product has attained a fixed value. Perfect. And this is the point which represents basically equilibrium. I would say after this point, equilibrium is established in the reaction, right? Perfect. Similarly, guys, there can be a scenario like this. Let me show that in a different slide. For example, you have got the reaction A gives B. This is the reaction. Initially, at time t is equal to 0, we are starting with 10 moles of reactant. This is 0. I'm assuming that when 80% of reaction is getting completed, equilibrium is established. 80% of reaction complete means 80% of reactant has got converted into product. So out of 10 moles, 8 moles of reactant has got converted. So I'll be left with 2 moles. This will be 8 moles. Now I'm assuming equilibrium is established. So now the number of moles of reactant and product are not going to change at all, right? If I ask you what is the concentration of reactant product at equilibrium, you'll say this is 2 molar, this is 8 molar, assuming that volume of container is 1 liter. Okay. Now guys, if you want to plot it graphically, concentration versus time. Perfect. Concentration versus time. Moles of reactants are decreasing with time and then finally attaining a fixed value. Moles of products are increasing with time and finally attains a fixed value. This is the point after which equilibrium is established in the reaction. So it represents what? It represents your equilibrium. What is this particular point? This is the concentration of product at equilibrium, and this particular point is the concentration of reactant at equilibrium. As you can see, concentration of product at equilibrium, it can be greater than that of concentration of reactant at equilibrium as well, right? This was the case which was showing concentration of reactant at equilibrium can be greater than concentration of product at equilibrium. This is the case which is telling you concentration of reactant and product at equilibrium can be equal as well. And this is the case which is telling you concentration of product can be greater than that of concentration of reactant at equilibrium, right? So condition is when you define equilibrium in terms of concentration, we say at equilibrium, concentration of reactant product, they should be fixed. They can be equal as well. As in this case, they can be equal as well. They can be equal as well. The condition is concentration of reactant product, they should be fixed, right? They can be equal as well. So this graph represents your equilibrium. Even this graph represents your equilibrium. And at the same time, this particular graph represents your equilibrium, right? But when you are defining equilibrium in terms of rate, we say at equilibrium rate of forward and backward reaction must be equal, right? In terms of concentration, constant. In terms of rate, equal, right? So when you make graphs between concentration versus time, there are three graphs which can represent equilibrium. But when you want to show equilibrium in terms of rate versus time, there is only one graph which shows your equilibrium. I hope this is clear. Is it clear, people, till now? Can you let me know in the chats once quickly? Is it clear? Is it clear? Okay, tell me one thing. If I'm making a graph like this, tell me whether this is the correct representation of equilibrium or not. Rate versus time. Is this correct? Is it correct, people? Is this graph showing equilibrium? No. When it comes to rate versus time, there is only one graph, right? There is only one graph. Do you see rate of forward and backward reaction equal here? See, this is for forward. This is for backward. This represents rate of forward. This represents rate of backward. Are these equal? No. When it comes to rate, only one condition. Rate of forward, backward reaction has to be equal. Okay? Perfect. I believe you got the idea of what this equilibrium is all about. Correct? Now, guys. Now, people. Something called as law of mass action. Law of mass action, which we have discussed in chemical kinetics as well. Okay? Try to understand. Law of mass action. Let's say I've got the reaction N1A plus N2B. It's in equilibrium with N3C plus N4D. This is the reaction, for example. This is the reaction. How many reactions actually these are? These are two reactions actually, right? One is your forward, one is your backward. One is your forward, one is your backward. These are the reactants of forward reaction. These are the reactants of backward reaction. Okay. Now, as per law of mass action is concerned, rate of reaction is directly proportional to the product of active masses of reactants. As per law of mass action, rate of reaction is directly proportional to the product of active mass of reactants. The product of active masses of reactants. So first of all, here we have got actually two reactions. N1A plus N2B. It gives what? It gives N3C plus N4D. This is my forward reaction. Similarly, if I write my backward reaction, that is N3C plus N4D. It gives what? It gives N1A plus N2B. This is my forward and this is my backward. As per law of mass action, rate of forward reaction is directly proportional to product of active masses of reactants. I'll write active mass of A multiplied by active mass of B. Raised to the power, their stoichiometric coefficients, that's N1, N2. Similarly, rate of backward reaction is directly proportional to product of active masses of reactants. I'll write active mass of C raised per N3, active mass of D raised per N4. Correct? Right? Simple. Now, if I remove the proportionality sign, I'll get a constant Kf multiplied by active mass of A raised per N1, active mass of B raised per N2. Similarly, rate of backward reaction is equal to Kb multiplied by active mass of C raised per N3, active mass of D raised per N4. Few minutes back, I told you at equilibrium, rate of forward and backward reaction becomes equal. And if rate of forward and backward reaction becomes equal, I'll say rate of forward reaction is Kf, active mass of A raised per N1, active mass of B raised per N2. This is equal to Kb multiplied by active mass of C raised per N3, active mass of D raised per N4. Right, people? Correct till here? Now, look at this particular equation. What I'll be getting from here? I'll write it like this. Kf divided by Kb. Kf divided by Kb is equal to active mass of C raised per N3, active mass of D raised per N4 divided by active mass of A raised per N1, active mass of B raised per N2. This Kf is what you call as rate constant of forward reaction. This is what you call as rate constant of backward reaction. And division of two constants will give you one more constant, That's what you call as equilibrium constant. So what is equilibrium constant? It is the ratio of the rate constant of forward and backward reaction. Equilibrium constant is the ratio of rate constant of forward to that of backward reaction, right? Now over here you are seeing the term active masses. Remember one thing. Whenever you have got the reactant or product present in aqueous state, that means in the bracket it will be mentioned as aqueous. Whenever you'll have reactant or product in aqueous state, its active mass will be its concentration. Whenever you will be having reactant or product in gaseous state, its active mass will be its concentration, or you can take it as pressure, right? You can take it as pressure. Whenever you have got pure solid or pure liquid, its active mass is taken as constant, and to reduce the calculation, we take it as 1. We take it as unity. So do remember these particular things as well. Do remember these 3 things as well. When active mass is taken as concentration, active mass pressure, active mass 1, right? Do remember these things. Now, my dear students, if you look at the expression of equilibrium constant, in the expression of equilibrium constant, you have got numerator and denominator. In the numerator, we have written products, C and D. In the denominator, we have got reactants, A and B. So in the products, we'll always write the reactants, we'll always write the products. In the denominator, in the numerator, we'll always writing the products. In the denominator, we'll be always writing the reactants. Okay, the active masses, I mean. Perfect. And if you want to define the equilibrium constant, it is defined as the ratio of rate constant of forward to that of backward reaction. Am I clear with this? Am I clear with this? Am I clear with this? Say it once. Say it once. So my dear students, your equilibrium constant, you know how do we write its expression? It's active mass of C raised power n3, active mass of D raised power n4 divided by active mass of A raised power n1, active mass of B raised power n2. Okay. My dear students, your equilibrium constant, I'm classifying here into 3 categories, out of which 2 we have to discuss. One is called as Kp, or let me write, one is called as Kc, one is called as Kp, and one is called as Kx. First of all, do remember, whenever you have got a reaction in which active masses are the concentrations. If in this particular expression, you replace these active masses by the concentration of C, concentration of D, concentration of A, concentration of B, at that point of time, your equilibrium constant Keq is what you call as Kc, nothing else. If active masses are taken as concentration, then Keq becomes Kc. If active masses are taken as the pressures, right, at that point of time, your equilibrium constant becomes Kp. And at the same time, if active masses are taken as the mole fractions, at that point of time, your equilibrium constant becomes Kx. Okay? For example, how do I write the expression for Kc now? It will be equal to concentration of C at equilibrium raised power n3, concentration of D at equilibrium raised power n4 divided by concentration of A at equilibrium raised power n1, concentration of B at equilibrium raised power n2. If you write equilibrium constant in terms of pressure, it becomes Kp. Over here, you'll write partial pressure of C at equilibrium raised power n3, pressure of D at equilibrium raised power n4, pressure of A at equilibrium raised power n1, pressure of B at equilibrium raised power n2. Similarly, your Kx, it becomes mole fraction of C at equilibrium raised power n3, mole fraction of D at equilibrium raised power n4, mole fraction of A at equilibrium raised power n1, mole fraction of B at equilibrium raised power n2. Am I clear? So this is the general expression. If you replace active masses by the concentrations, it becomes Kc. If you replace active masses by the pressures, it becomes Kp. If you replace active masses by the mole fractions, it becomes what? It becomes your Kx. Am I clear with this? Say yes or no once. Say yes or no once. Say yes or no once. Let me show you exactly how do we write the equilibrium constants now. How do we write expression for Kp, Kc? Let's say this is the reaction. This is the reaction. This is the reaction. Reactants products are in gaseous phase. For gases, active mass can be, it is expressed as concentration as well as pressure for gases. For aqueous things, only concentration. Okay. So first of all, can I write the expression for Kc over here? Yes, we can do that. concentration of H2 at equilibrium raised power 1, concentration of I2 at equilibrium raised power 1 divided by concentration of Hi at equilibrium raised power 2. Similarly, if you want to write the expression for Kp, you can write the expression for Kp because for gases, pressure as well as concentration, both the things are defined. So it's going to be pressure of H2 raised power stoichiometric coefficient, pressure of I2 at equilibrium raised power stoichiometric coefficient, pressure of Hi at equilibrium raised power stoichiometric coefficient, right? My dear students, if I ask you what about the delta Ng for the reaction, delta Ng will be number of moles of gaseous products, which is 1 plus 1, 2, minus number of moles of gaseous reactant, which is 2, so 2 minus 2 is 0. Simple. Can you write Kc expression for this? Yes, I can do. I have to start with the product. It's an aqueous state, so take its concentration. So concentration of NH4 positive raised power 1, concentration of OH negative raised power 1 divided by concentration of NH4OH raised power 1, raised power stoichiometric coefficient basically, right? Now, can you write the expression for Kp? You cannot write the expression for Kp because all these are aqueous. For aqueous, active mass is only concentration. If they were in gaseous phase, then you could have written Kp expression as well. You cannot write the expression for Kp. Okay? I hope I'm clear. I hope I'm clear with this. I hope I'm clear with this. Okay. Look at this particular case. Solid, gas. If it is a gas, then you can write expression for Kp as well as Kc. So write the expression for Kc first of all. It is going to be concentration of carbon dioxide at equilibrium raised by stoichiometric coefficient. Solid, nothing to do with this. Solid, nothing to do with this. Similarly, Kp expression will be partial pressure of carbon dioxide at equilibrium raised by 1. Solid, nothing to do with them. If I ask you what about the delta Ng for this particular reaction? Siri is working. Okay, delta Ng is equal to number of moles of gaseous products, which is 1, minus number of moles of gaseous reactant, that's 0. Okay? Right? Similarly, guys, if you look at this particular equation, right? If you look at this particular reaction, solid, gas, so you can write the expression for Kp as well as Kc. So your Kc expression is going to be concentration of SO3 at equilibrium raised by stoichiometric coefficient divided by concentration of O2 at equilibrium raised by stoichiometric coefficient. This is solid, nothing to do with that. If you want to write the expression for Kp, you can do that as well. It's going to be partial pressure of SO3 at equilibrium raised by stoichiometric coefficient, partial pressure of O2 at equilibrium raised by stoichiometric coefficient, that's 3 by 2. And similarly, my dear students, if I ask you to write the expression for delta Ng, number of moles of gaseous product, which is 1, minus number of moles of gaseous reactant, which is 3 by 2. The value comes out to be minus 1 by 2 over here. So this is the value of delta Ng for the reaction which was given to us. I hope you got to know how do we write the expression for Kp and Kc. Yes? I hope you got to know how do we write the expression for Kp and Kc. Okay? I hope you got to know how do we write the expression for Kp and Kc. Now, what is the relation between Kp and Kc? For a particular reaction, what is the relation between Kp and Kc? Understand. Let's say you have got the reaction N1A gas. It's in equilibrium with N2B gas. This is your reaction, for example. This is your reaction, for example. First thing, we can write Kp as well as Kc expression for both. For this reaction. So Kp is nothing but partial pressure of B at equilibrium raised by N2, partial pressure of A at equilibrium raised by N1. Similarly, Kc has to be concentration of B at equilibrium raised by N2, concentration of A at equilibrium raised by N1. Correct? Yes, we know it. If I ask you what is the delta Ng for this reaction, delta Ng for this reaction is equal to number of moles of gaseous products, which is N2, minus number of moles of gaseous reactant, that is N1. N2 minus N1. Yes, N2 minus N1. Now, my dear students, try to understand very carefully. Ideal gas equation, I believe everyone would be knowing PV is equal to nRT. I can write P is equal to N divided by VRT, right? P is equal to N by V is concentration, RT. So I can say PA is equal to concentration of ART. I can say PB is equal to concentration of BRT. I can say something like this. Now here in this particular expression, what do you see? Here in this particular expression, what do you see? Kp is equal to partial pressure of B at equilibrium. Instead of PB, I can write concentration of B, RT, whole raised by what? Whole raised by N2 divided by PA, concentration of A, RT, whole raised by N1. Whole raised by N1. So Kp is equal to concentration of B raised power n2, concentration of A raised power n2. What do we call that as? That's called as Kc. So it becomes Kc RT raised power n2 minus n1 is something which you call as delta Ng here. So for this gaseous phase reaction over here, which I'm assuming is carried out at constant temperature, your Kp is equal to Kc RT raised power delta Ng, right? So this is basically your relation between Kp and Kc for a particular reaction which is carried out at constant temperature. Kp is equal to Kc RT raised power delta Ng, right? I hope I'm clear. See, there are other relations as well between Kp, Kx, Kc, Kx, then their logarithmic form. No need to go for that. Just remember this one. This much is enough for you. This much is enough for you. Okay. Now, people, tell me the relation between Kp and Kc for all these reactions. Tell me the relation between Kp and Kc for all these reactions. For the first reaction, if you see, what is the value of delta Ng for the first reaction? Number of moles of gaseous products minus number of moles of gaseous reactants, 1 plus 1, 2. So delta Ng is 0. If delta Ng is 0, you know, Kp is equal to Kc RT raised power delta Ng. Delta Ng is 0, anything raised power 0 is 1. So your Kp and Kc are becoming equal here. So Kp is equal to Kc for the first reaction. If you look at the, for example, second reaction, for the second reaction, calculate delta Ng. Number of moles of gaseous products, 1 plus 1, 2, minus number of moles of gaseous reactants. So 2 minus 1 is 1. So your Kp is equal to Kc RT raised power 1. Correct? Similarly, if you look at the third reaction, for the third reaction, get the delta Ng value first of all. Delta Ng is equal to number of moles of gaseous products, which is 2, minus number of moles of gaseous reactant, 3 plus 1, 4. The value comes out to be minus 2. So your Kp here will be equal to Kc RT raised power delta Ng. This is the relation between Kp and Kc. Similarly, you can check for this one as well. No issues at all. Right? Correct? I believe it's very clear to everyone. I believe it's very clear to everyone. Yes? So remember the relation between Kp and Kc, that's very important. And one more thing. Units of Kp, Kc, you need to remember, right? Unit of Kc is going to be moles per liter raised by delta Ng of the reaction. And unit of Kp is going to be unit of pressure raised by delta Ng. If the pressure unit is atm, then atm raised by delta Ng, bar raised by delta Ng, mmHg raised by delta Ng. Right? Perfect, guys. Remember these units of your Kp and Kc as well. Correct? Now there are few things. There are few things which you need to remember basically. And what are those few things? Let me tell you that. Remember these 3 important points. They are important. Out of which questions can be asked. Have a look, people. We say when the reaction is reversed, equilibrium constant gets inversed. For example, you have got the reaction A gives B. Right? If its equilibrium constant is K. If its equilibrium constant is K. If I reverse the reaction, now its equilibrium constant becomes 1 upon K. So when you reverse the reaction, equilibrium constant is inversed. Number one. Number 2, if you multiply this reaction by some number, let's say it becomes, I'm multiplying the reaction by n. When you multiply this reaction by some number, that number has to go to the power of equilibrium constant. Now the equilibrium constant of this particular reaction will be K raised power n. If you will be having any reaction at equilibrium, if you are multiplying that reaction by number, that number goes to the power of equilibrium constant, right? At the same time, when you'll be adding 2 reactions, let's say you've got the reaction like this, let's say A gives B, right? C gives D. Equilibrium constant for this one is K1, this is K2. If I add these two reactions, it becomes like this. When you add these 2 reactions, it becomes like this. And remember, when you add the reactions, equilibrium constants are to be multiplied at the same time. So the new equilibrium constant of the net reaction has to be K1 multiplied by K2. If I'm clear, let me know in the chats. Quickly. Because questions are asked from these. Basic questions, that too. Let's say you have got one simple question like this. You are given with a reaction whose equilibrium constant is 49. You have to calculate equilibrium constant for this reaction. Remember one thing, just remember. The reaction whose equilibrium constant is to be calculated. You will have to make that reaction out of the given reaction. The reaction whose equilibrium constant is to be calculated, you will have to make that reaction out of the given reaction. The given reaction is this. If I reverse the given reaction, it becomes 2 times NH3. 2 times NH3, it gives what? It gives N2 plus 3 times H2. And when you reverse the reaction, equilibrium constant is inversed. Now it becomes 1 upon 49. Correct? If I multiply this reaction by 1 by 2, when I multiply this reaction by 1 by 2, 2 cancelled, this becomes 1 by 2 N2, and this becomes 3 by 2 H2. And since I've multiplied the reaction by 1 by 2, that 1 by 2 has to go to the power of equilibrium constant. So this is 1 by 49 raised power 1 by 2, which comes out to be 1 by 7. So 1 by 7 is the equilibrium constant for the reaction which was given to us. This is the equilibrium constant for this particular reaction, right? This particular reaction is what? It is 1 by 7. As simple as that. Correct? You get these sort of basic equations, by the way. You get these sort of basic equations over here. Okay, for example, you have got one more question like this. One more similar question. A reaction is given whose equilibrium constant is K1. One more reaction is given whose equilibrium constant is K2. We have to get the relation between K1 and K2. A relation between K1 and K2. If I reverse this reaction, what it becomes? It becomes 3 times A2 plus 3 times B2. It gives what? It gives 6 times AB. Since I reverse this reaction, its equilibrium constant now is 1 upon K2. Inversed. Now, if I multiply this reaction with 1 by 3, it becomes A2 plus B2 gives 2 times AB. Since you multiplied this reaction by 1 by 3, that 1 by 3 goes to the power of equilibrium constant. Power of equilibrium constant, right? Now, look at this particular reaction and look at this particular reaction. Aren't these reactions same? Yes. So, equilibrium constant was K1, so this is the value of K1. So, K1, K2, this is the relation. You can check the options and select, right? Again, simple. Yes. Again, a simple question this is. Again, a simple question this is. Okay, one more basic question I'm giving you. Basic question. One basic question. You're given with a reaction. Reaction is 2 times A in equilibrium with B plus C. Concentration of A, B and C at equilibrium are given to us. What do we have to calculate? Kc. How do you write the Kc expression? Concentration of B at equilibrium raised by stoichiometric coefficient. Concentration of C at equilibrium raised by stoichiometric coefficient. Concentration of A at equilibrium raised by stoichiometric coefficient. My dear students, all these terms are given to us. Concentration of B at equilibrium is given to us as 2 into 10 raised power minus 3. Concentration of C at equilibrium, that's given to me as 3 into 10 raised power minus 3. Concentration of A, sorry, this is raised power 2, okay? Concentration of A is given to me as 1 into 10 raised power minus 3 raised power stoichiometric coefficient 2. So this term cancelled, 3 2s are 6. So value of Kc is nothing but 6. So option B has to be the correct answer of this question. Very basic and simple one. Right? Very basic and simple one. Okay. Look at this particular basic question. Identify the reaction in which Kp and Kc are not equal. Kp and Kc are not equal. See, for that particular reaction whose delta Ng is 0, we say for that particular reaction Kp and Kc are equal. And if delta Ng is non-zero, that means Kp and Kc, they won't be equal. Now find that reaction for which Kp and Kc are not equal. If you look at the last reaction, calculate delta Ng for the last reaction. Number of moles of gaseous products minus number of moles of gaseous reactant. Right? So 2 minus 1 is 1, which is non-zero. If delta Ng is non-zero, Kp and Kc won't be equal. Right? Perfect. The question was are not equal. They are not saying are equal. They are saying not equal. Correct? Done with this? I hope you can solve this sort of a question on your own from now onwards. Tell me the answer of this very basic question. I'm not solving this. You tell me. Look at the question and tell me. Quick. Look at the question and tell me quick. Guys, just a second. I'll have to turn off one light. because there is electricity shut down here due to the heavy rain. Just a second. Is it done? So people are saying it's option A. Absolutely, it's option A. Absolutely, you're perfectly right. It's option A. Now comes the actual stuff, which people find tough a bit. Okay, which people find tough a bit. That is calculation of Kp and Kc. Let's have a look. Just a second. Okay. How do we exactly calculate Kp and Kc? There are two methods for that. One is called as mole method, one is called as degree of dissociation method, right? One is called as mole method and one is called as degree of dissociation method. Mole method and degree of dissociation method. So first of all, we need to understand what this mole method is all about. Then we'll understand what this degree of dissociation method is all about. Then we'll get to know how Kp and Kc is to be calculated actually, right? Okay. My dear students, so let's start with the mole method. But before showing you Kp Kc calculation with the help of mole method, there is one thing which you need to know. What is that? That is calculation. That is calculation of moles. Calculation of moles of reactants and products at equilibrium. This is the most important point which you need to know. How do we calculate the moles of reactants and products at equilibrium? Okay. How do we do that? See guys, for example, I'm writing a reaction, a very simple reaction. A gives B. Let's assume it is a balanced chemical equation. Assume that it's a balanced chemical equation. My dear students, for example, at time t is equal to 0, I have got A moles of reactant. Since the reaction has not started, so this will be 0. Now at equilibrium, I'm assuming out of A moles of reactant, X moles got converted into product. So I'll be left with A minus X moles of reactant at equilibrium. Now use the stoichiometry. 1 mole gives 1 mole. Therefore, X moles would have given X moles, right? So what did we get? We got the moles of reactants and products present in the container at equilibrium. We got the moles of reactants and products present in the container at equilibrium. Now guys, if I ask you what is the concentration of reactant and product at equilibrium, let's say the volume of the container in which reaction is taking place is V liters. If I divide these moles with the total volume of the vessel, if I divide this also by the total volume of the vessel, what do I get? This is the concentration of reactant and product at equilibrium. Simple. Concentration of reactant and product at equilibrium. I believe it's clear. I believe it's clear. Yes? Right, people? Now see, if I, for example, change the stoichiometry like this, let's say I'm writing A gives 2 times B plus 3 times C. Let's say I'm writing something like this. This is the reaction, a balanced chemical equation. Let's say initially at time t is equal to 0, we have got A moles of reactant. This is 0, this is 0. Now at equilibrium, let's assume that out of A moles of reactant, X moles got converted into product. So I'll be left with A minus X moles of reactant, right? Now, 1 mole gives 2 moles. So from X, you'll get 2X. 1 gives 3 moles. From X, you get 3X. So these are the moles of reactants products in the container at equilibrium. Correct? For example, you have got the reaction like this. Let's say A plus 3 times B. It gives 2 times C. Let's say this is the reaction. I'm assuming initially at time t is equal to 0. For example, we have got A moles of this reactant. Let's say we have got B moles of this reactant, and this is, for example, 0, because I'm assuming reaction has not started. Let's assume at equilibrium, out of A moles of reactant, X moles have reacted. So I'll be left with A minus X moles of the first reactant. Now, 1 mole of reactant reacts with 3 moles of this. X moles would have reacted with 3X. I had taken B. Out of B, 3x are reacting. So I'll be left with B minus 3x. 1 mole gives 2 moles. So from x, you would have got 2x. So this is how you can calculate the moles of reactant and product in the container when you have such kind of the reaction. One more. For example, I'm writing the reaction like this. 2A in equilibrium with 3B plus 5C. Let's say this is the reaction. Let's assume initially I have got A moles of reactant, I've got B moles of this, I've got C moles of this. Let's assume before the start of the reaction itself. There is B and C in the container as well. Let's say before the start of the reaction itself, there is B and C. Now, when the reaction will start, more B and C will get formed. Right? More B and C will get formed. Yes? More B and C will get formed. Now, try to understand. At equilibrium, assume that out of A moles of reactants, X moles got converted. X moles got dissociated, so I'll be left with A minus X. Correct? I'll be left with A minus X. Now, my dear students, understand. 2 moles are giving 3 moles. Right? So, 1 mole will give 3 by 2. X will give 3 by 2x. Already there was B. Now, some more 3 by 2x moles of B will get formed. So, this will be B plus 3x. Correct? Similarly, 2 moles are giving 5 moles. So, 1 will give 5 by 2. So, this has to be C plus 5 by 2x. I hope you can calculate the moles of reactant products at equilibrium in any type of the reaction. Is that clear? Am I perfectly clear to you? Am I perfectly clear to you? Can you let me know in the chats? Am I perfectly clear? Say yes or no in the chats quickly. If all these things are clear, then have a look how the questions will be solved. For example, this is the first question which we have. Understand carefully. As per the question, we are given with the reaction which is A gas plus B gas. It is in equilibrium with 2 times C gas. This is the reaction. Okay. Now, at time t is equal to 0, we are given with 2 moles of A, 1 mole of B, and 1 mole of C. So already C is there in the container. This is something which is given to me. This reaction is taking place in a vessel which has got the volume of 10 liters. Equilibrium is established in the reaction. Final concentration of C is 0.2 molar. What is meant by final concentration of C? It means concentration of C at equilibrium is equal to 0.2 molar. That means 2 by 10 molar. What do we have to calculate? We have to calculate the value of Kc. Tell me first of all, how do we calculate the value of Kc? How do we calculate the value of Kc? How do we write the expression for Kc? I'll write concentration of C at equilibrium raised power stoichiometric coefficient 2 divided by concentration of A at equilibrium raised power stoichiometric coefficient 1, concentration of B at equilibrium raised power stoichiometric coefficient 1. So in order to calculate the value of Kc, what do we need? We need the concentrations of reactants and products at where? At equilibrium. At equilibrium, we need that. Concentration of reactants as well as products we need at equilibrium. Right? Now the point is, how do we get the concentrations of reactants, products at equilibrium? That is the point now. That is the point. How do we get the concentration of reactants, products at equilibrium now? Try to understand. First of all, let's assume at equilibrium, out of 2 moles of A, X have reacted. So I'll be left with 2 minus X. Right? Since 1 mole reacts with 1 mole, X would have reacted with the X moles of B. I had taken 1. Out of 1, X is reacting. So I'll be left with 1 minus X. Already there was 1 in the container. 1 mole of C in the container. Now, 1 mole gives 2 moles. So X would have given 2X. Correct? I got the moles of reactants, products in the container at equilibrium. Okay? Do I need moles or I need concentration? I need concentration. If I divide these terms by the total volume of the vessel, which is 10 liters, can I say I got the concentration of each reactant product at equilibrium? Yes, absolutely. I got the concentration of each reactant product at equilibrium. Now, concentration of C at equilibrium, that is 1 plus 2x by 10. 1 plus 2x by 10. That is given to me as 2 by 10. So 10, 10 cancel. When you solve, x value will come out to be 1 by 2. That means 0.5. You got the value of x. If you got the value of x, calculate the actual concentration of each reactant product at equilibrium. 2 minus 0.5 is 1.5. 1.5 divided by 10 is 0.15. This is the concentration of A at equilibrium. 1 minus 0.5 is 0.5. 0.5 divided by 10 is 0.05 molar. Similarly, 1 plus 2x by 10. 1 plus 2x by 10 is given to me as 0.2 molar. So I got the concentration of each reactant and product at equilibrium. And if you get the concentration of each reactant product at equilibrium, you can easily write the expression for Kc, which is going to be concentration of C at equilibrium, that's 0.2, raised power what? Raised power 2, divided by concentration of A at equilibrium is how much? 0.15. Raised power what? Raised power stoichiometric coefficient 1. 0.05. Raised power stoichiometric coefficient 1. Solve it and get the value of Kc, which I was supposed to calculate. Am I clear to this? Am I clear to everyone? Am I clear with this? Isn't it simple, guys? It is just you should know the procedure. You are done. You are done. Perfect. Let's try to solve one more question on this. Let's try to solve one more question on this. On starting with 1 mole of HI, calculate the concentration of each species at equilibrium if Kp for decomposition of He. What is the decomposition reaction of HI? 2 times HI gives H2 gas plus I2 gas. Right? This is the decomposition reaction of your HI. This is how HI undergoes decomposition. This is how HI undergoes decomposition. Okay? First of all, if I ask you what is the delta Ng for this reaction? What is the delta Ng for this reaction? What is the delta Ng for this reaction? Delta Ng for this reaction is 0. If delta Ng is 0, then definitely Kp and Kc are equal. Kp and Kc are equal. And as per the equation, it's given as 16. Correct? Now, initially, at time t is equal to 0, we are starting with 1 mole of HI. Right? This is 0. This is 0. Now, when equilibrium is established, this is going to be, for example, 1 minus x. Out of 1 mole, let's say x moles got dissociated. Right? So, I'll be left with 1 minus x. 2 gives 1. 1 gives 1 by 2, x gives x by 2. So I got the moles of each reactant product in the container at equilibrium. If I divide these moles by the total volume, I'll be getting the concentration. So 1 minus x divided by total volume is 2 liters. X by 2 divided by 2, that means x by 4. This will be also x by 4. So these terms, these represent concentration of reactants and products at equilibrium. Okay? Concentration of reactants and products at equilibrium. Now guys, if I write the expression for Kc, what will be the expression for Kc? Concentration of H2, which is x by 4. Concentration of I2, x by 4. So x square divided by 4 for 16, whole divided by. Concentration of Hi, which is 1 minus x divided by 2, raised power 2. So it is going to be x square divided by 16, x square divided by 16. This is 1 minus x square divided by 4. So the value comes out to be how much? This is 4144. So this is x square divided by 4 multiplied by 1 minus x square. And this value as per the equation is given to me as 16. Correct? Now, if you look at this particular equation, a bit of mathematics is needed here. You can write it as x divided by 2 multiplied by 1 minus x whole square is equal to 16. So you can say x divided by 2 minus 2x is equal to 4. So x is equal to 8 minus 8x, right? So 9x is equal to 8. So x is equal to 8 divided by 9. You got the value of x. If you got the value of x, what were we supposed to calculate? We were supposed to calculate the concentration of each species. So concentration of Hi you can easily calculate 1 minus x by 2 because x you have calculated. So 1 minus 8 by 9 by 2. X by 4. X you have calculated. X by 4. X you have calculated. So you can easily calculate the concentration of each reactant product at equilibrium. Okay. So this was how do we calculate Kc. In order to calculate Kc, what do we need to do? In order to calculate Kc, what do we need to do? We need to first of all get the moles of reactants products at equilibrium. Then get the concentration of reactant product at equilibrium by dividing those moles by the total volume. Then write the expression for Kc. But how do we get Kp? How do we calculate Kp? Okay, how do we calculate Kp? Let's check that out too. Try to understand what exactly I'm going to say. This was how do we calculate Kc. Now, how do we calculate Kp? My dear students, for example, a reaction you have that A gas in equilibrium with 2 times, or let me keep it simple, A gas in equilibrium with B gas plus C gas. Let's say this is the reaction. Let's say this is the reaction. Okay. I'm just showing you the procedure of calculation of Kp with the help of mole method. With the help of mole method. Initially at time t is equal to 0, let's say we have got A moles of reactant. This is 0, this is 0. Let's say at equilibrium, I'm left with A minus X, this is X, and this is X. So tell me one thing, at equilibrium, how many gases are there in the container? What do you think? At equilibrium, how many gases are there in the container? Can I say at equilibrium, there are 3 gases in the container? So can I say at equilibrium, there's a gaseous mixture present? Yes, there's a gaseous mixture present, right? There is a gaseous mixture present. If I ask you how many total moles are there in the container at equilibrium, you will say the total moles in the container at equilibrium are A minus X plus X plus X, right? So which comes out to be A plus X. So at equilibrium, basically there are three gases in the container. At equilibrium, there are some moles of A left, there are some moles of B which would have got formed, there are some moles of C which would have got formed. How many moles of A are there in the container? A minus X. How many moles of B? X. How many moles of C? X at equilibrium, correct? Now, look carefully. My dear students, since this is a gaseous mixture, how many moles of A are there in the container? A minus X, right? How many moles of B are there in the container? X. How many moles of C? X at equilibrium. If I divide them with the total moles present in the container at equilibrium, what do I get? What do I call these terms now? What do I call this particular term now? Should I be calling this as mole fraction of A in the container at equilibrium? Should I be calling this as mole fraction of B in the container at equilibrium? Should I be calling this as mole fraction of C in the container at equilibrium? Absolutely. So, mole fraction of each reactant product at equilibrium will be equal to A minus X divided by A plus X. Similarly, X divided by A plus X. Similarly, X divided by A plus X. I got the mole fraction. If the total pressure of the mixture at equilibrium is PT, if the total pressure of the mixture at equilibrium is PT, if I multiply all these terms by the total pressure at equilibrium, by the total pressure of the mixture at equilibrium, what do I get? I get the partial pressure of each reactant product at equilibrium. Partial pressure of each reactant product at equilibrium I got. These are the partial pressures. These are the partial pressures. And my dear students, if you got the partial pressures, you can easily write the Kp expression now. Kp expression is written as partial pressure of B raised by stoichiometric coefficient, partial pressure of C at equilibrium raised by stoichiometric coefficient, partial pressure of A at equilibrium raised by stoichiometric coefficient. What is the partial pressure of B? We got this. What is the partial pressure of C? We got this. What is the partial pressure of A? We got this. So put it here and get the expression for Kp. This is how your Kp calculation is done. For Kc calculation, what do we do? For Kc calculation, what do we do? We calculate moles at equilibrium first, then calculate the concentration of reactant product at equilibrium. But here, what do we calculate? We calculate partial pressure of reactant product at equilibrium, right? Am I clear? Am I clear, people? Perfect. Let's try to solve a few more questions first of all. Let's see if you can solve them or not. One simple question I'm giving you. Think over it once. Think over it once. Think over it once. What do you think? We are given with a reaction and the reaction is given to you as N2 gas plus 3 times H2 gas. It gives us 2 times NH3 gas. This is the reaction that's given to us. As per the question, when equilibrium was established in the reaction, tell me one thing, when equilibrium is established in the reaction, how many gases will be there in the container? some moles of this will be left, some moles of this will be left, and some moles of this would have got formed. So there are 3 gases in the container at equilibrium. Okay, there are 3 gases. So basically at equilibrium, again I would say I have got a gaseous mixture. Total pressure of the mixture as per the question. Total pressure of the mixture as per the question at equilibrium is how much? 2.8 atm. Can I say the total pressure of the mixture will be equal? Partial pressure of N2 at equilibrium, partial pressure of H2 at equilibrium, plus partial pressure of NH3 at equilibrium. That's equal to 2.8. The total pressure at equilibrium is basically the sum of contributions made by each. Yes. Now, what is the partial pressure of N2? Given to us as 0.8 atm. H2, 0.4 atm. Partial pressure of NH3 is equal to 2.8. So, partial pressure of NH3 is equal to 2.8 minus 1.2. That comes out to be 1.6 atm. So, I got the partial pressure of each reactant product at equilibrium. And if I got the partial pressure of each reactant product at equilibrium, what do I need to do? I just need to write the expression for Kp. We are done. So it is partial pressure of NH3 at equilibrium raised by stoichiometric coefficient 2 divided by partial pressure of N2 at equilibrium raised by stoichiometric coefficient 1, partial pressure of H2 at equilibrium raised by stoichiometric coefficient 3. What is the partial pressure of NH3? 1.6. So 1.6 square divided by partial pressure of N2 at equilibrium is 0.8 raised power 1. Partial pressure of H2 at equilibrium 0.4 raised power 3. When you solve it, the value comes out to be 50. Value comes out to be 50. If I ask you what are the units of it, what are the units of Kp? Units of Kp are going to be atm raised power delta Ng. What is delta Ng? 2 minus 4. The value comes out to be minus 2. So 50 atm raised power minus 2 is basically going to be the unit of Kp at the end. Right? Okay. Am I clear with this? Am I clear with this, people? Say it in the chats quickly. Am I clear with this? My dear students, there are some more questions, some different types of questions can be asked, right? In mole method as well, some different types of questions. What are those? For example, you have got a gaseous phase reaction like this. A gas is in equilibrium with. I'll show you one example only. B gas and 3 times C gas. Okay. Tell me one thing. You know your PV is equal to nRT. If this reaction is carried out at constant volume and temperature, can I say pressure at that point of time is directly proportional to moles? Yes, I can say that. If moles are decreasing, pressure will be decreasing. If moles are increasing, pressure will be increasing. Absolutely. Now, imagine this reaction is taking place at constant volume temperature. So it has to follow this particular rule which I gave you over here. Okay. Now tell me one thing. As the reaction proceeds, moles of reactant decrease with time. So pressure due to reactant also decreases. Pressure due to product also increases. Right? When the reaction proceeds, pressure due to reactant decreases, pressure due to product increases. My dear students, initially at time t is equal to 0, when the reaction was not started, whatever was the total pressure that was due to A, and call that as P naught. This is 0, this is 0. Now treat the pressure in the similar way as you used to treat moles. Treat the pressure in the similar way as we used to treat the moles. So at equilibrium, pressure due to A is nothing but P naught minus X. Pressure due to B is going to be equal to 2X. Pressure due to C is going to be equal to 3X. So you got the partial pressures of reactants products directly over here at equilibrium. Now you can write Kp expression directly. Kp is equal to partial pressure of B raised power 2, partial pressure of C raised power 2, and divided by partial pressure of, this is C, right? Partial pressure of C raised power 3 divided by partial pressure of A raised power 1. Okay. So my point is, when you will be having a reaction which is carried out at constant volume and temperature, at that point of time, whatever procedure you used to do with the moles, the same procedure you will be doing with the pressures as well. For example, let me give you one example. This is one example which is in front of you. We are given with a reaction that is AB3. AB3, it gives what? It gives AB2 plus what? Plus half of B2. Plus half of B2. This is the reaction that's given to us, okay? As per the question, the initial pressure of AB3, which I'm representing with P naught, is 900 torr. This is 0, this is 0. Now tell me at equilibrium, treat the pressure in the similar way as we treat the moles. Can I say this has to be 900 minus 6? Matlab P naught minus 6. 1 gives 1, x gives x. 1 gives 1 by 2, x will give x by 2. Correct? As per the question, the total pressure of the mixture at equilibrium. The total pressure of the mixture at equilibrium. How much is that? That is 1000 torr. Now tell me, total pressure of the mixture at equilibrium will be this plus this plus this. Correct? So this is going to be 900 minus x plus x by 2 is equal to 1000. X got cancelled. So x value over here you will find as 200 torr. X is 200. If x is 200, so 200 minus x, 900 minus 200 comes out to be 700. So this is 700 torr. This is 200 torr. This is 200 by 2, which comes out to be 100 torr. So these are the partial pressures of reactants products at equilibrium. Now get the Kp expression. Kp is going to be partial pressure of AB2, that is 200, raised power 1. Partial pressure of B2, that is 100, raised power 1 by 2, divided by partial pressure of AB3, that is 700. Perfect. So the value comes out to be 20 divided by 7. Now what are going to be its units? It's going to be torr raised power delta Ng. Delta Ng is 1 plus 1 by 2, 3 by 2, 3 by 2 minus 1 is 1 by 2. So this is how you get the Kp value for this particular reaction. If I'm clear, let me know once in the chats. Yes? If I'm clear, let me know once in the chats. Let me know once in the chats. Let me know once in the chats. Break I'll be giving after chemical equilibrium is done. Right? And after the break, we'll start ionic equilibrium. It is not going to take more than half an hour. It's done almost. It is done almost. Yes? Perfect. All right, people. Now comes calculation of Kp and Kc with the help of degree of dissociation method. Degree of dissociation. First of all, how do we calculate the degree of dissociation? Let's say I've got the reaction A gives B. Okay. I'm assuming initially we have got A moles of reactant and this is 0. Now at equilibrium, I'm assuming a term alpha over here. Alpha is what you call as degree of dissociation, which is defined as number of moles of reactants dissociated into product divided by initial moles of reactant. Number of moles of reactant dissociated into product divided by initial moles of reactant. So alpha is equal to number of moles of reactant dissociated divided by initial moles of reactants are A. So number of moles of reactant dissociated has to be equal to A alpha. So I am assuming out of A moles of reactants, how many moles of reactant got dissociated? A alpha. So I'll be left with A minus A alpha. These are the moles of reactants present in the container at equilibrium. Now, 1 mole gives 1 mole. From A alpha, you'll be getting A alpha here. Okay? So this is how you calculate moles. This is how you calculate moles of what? This is how you calculate moles of reactants and products at equilibrium with the help of degree of dissociation. Till now, we used to call this A alpha as X. That's why we used to write A minus X, X. But here, right, we wrote X in terms of alpha. Perfect? For example, let me show you calculation of Kp, Kc with the help of degree of dissociation method. Understand properly. For example, we have got the reaction like this. 2 times A, it gives B plus C. Let's say this is the reaction. Understand what I'm going to say. This is important. For example, initially at time t is equal to 0, I'm given with A moles of this. This is 0 and this is 0. Let's say degree of dissociation at equilibrium is alpha. So at equilibrium, I'll be left with A minus A alpha. Now 2 gives 1, 1 gives 1 by 2. A alpha gives A alpha by 2. Similarly, 2 gives 1, 1 gives 1 by 2. A alpha gives A alpha by 2. So I got the moles of reactants products at equilibrium. If I ask you, how many total moles are there in the container at equilibrium? Total moles there in the container at equilibrium is this plus this plus this, which will come out to be this plus this is A alpha cancel. So total moles at equilibrium is, or leave total moles aside. Let's do one thing first of all. Let's assume that this reaction is taking place in a container whose volume is V. So divide with V, divide with V, divide with V. What did I get? I got the concentration. I got the concentration of each reactant product in the container at equilibrium. Now, can I write the Kc expression? Kc expression is going to be concentration of B at equilibrium raised power 1, concentration of C at equilibrium raised power 1 divided by concentration of A at equilibrium raised power 2, concentration of B at equilibrium. How much is that? A alpha divided by 2V. Concentration of C at equilibrium is equal to A alpha divided by 2V. Whole divided by concentration of A at equilibrium is equal to A minus A alpha divided by V whole raised power 2. Perfect. Right? This is how you wrote the expression for Kc over here. You can simplify it further. Right? Now, if you want to write the expression for Kp expression, you know what to do. For Kp expression, what do we need to do? First of all, I'll get the total moles. Total moles is A. So I'll be dividing with total moles. When I divide with the total moles, what did I get? I got the mole fraction of each reactant product. I got the mole fraction of each reactant product at equilibrium. If I multiply it with total pressure, of the mixture at equilibrium, what did I get? I got the partial pressure. So I got the partial pressure of each reactant and product at equilibrium. And once you get the partial pressure of each reactant product at equilibrium, you can write the expression for Kp. It's going to be partial pressure of B at equilibrium raised power 1, C at equilibrium raised power 1, partial pressure of A at equilibrium raised power 2. I got the partial pressures, put it here and get the expression for Kp. Right? I hope you got to know, right, how do we write the Kc expression with the help of degree of dissociation method as well. Yeah? Am I clear? Am I clear, people? One question for this, right? You'll get the idea of what we are doing. As per the question, let's see what the question says. We are given with a reaction N2O4 gas. It is in equilibrium with 2 times NO2 gas. It's in equilibrium with 2 times NO2 gas. Total pressure at equilibrium is given to us as 1.5 atm. Degree of dissociation alpha is given to me as 0.25. 0.25, calculate Kp. Calculate Kp. We have to calculate Kp. Let's say initially at time t is equal to 0, I've got A moles of this is 0, right? Let's say at equilibrium, I'm left with A minus A alpha. This will be automatically 2 times A alpha. Okay. How many total moles are there? This plus this, which is A plus A alpha. So divide this with A plus A alpha. Divide this with A plus A alpha. So this is the mole fraction of N2O4 at equilibrium. This is the mole fraction of NO2 at equilibrium. Mole fraction of N2O4 at equilibrium. Mole fraction of NO2 at equilibrium. Okay. Perfect. Since you got the mole fraction, if you multiply these mole fractions by total pressure, I'll be getting the partial pressure. So this term gives you the partial pressure of N2O4 at equilibrium. Even this term gives you the partial pressure of N2O4 at equilibrium. Correct? See guys, if you take A common, A gets cancelled here, A gets cancelled here. So this is 1 minus alpha. 1 minus alpha divided by 1 plus alpha multiplied by 1.5. A gets cancelled here. This is 2 times alpha divided by 1 plus alpha multiplied by 1.5. Multiplied by 1.5. Now alpha value is given to us 0.25. Right? If you put alpha here, you'll be exactly getting the value of partial pressure of N2O4 at equilibrium. And if you put the value of alpha here, you'll be getting the partial pressure of NO2 at equilibrium. And once you get the partial pressures, you can easily write the expression for Kp. Kp expression is going to be partial pressure of NO2 at equilibrium raised power 2 divided by partial pressure of N2O4 at equilibrium raised power 1. It is just the matter of calculation now. It is just the matter of calculation. I hope I'm absolutely clear to every one of you till now. Yes? Let me know once in the chats if all these things are clear. Let me know once in the chats if all these things are clear till now. Quickly, people. Quickly, every one of you. Every one of you. Quickly. Quickly, everyone. Quickly, quickly, quickly. Is it done? Perfect. Now, there is one more way of calculating this degree of dissociation alpha. How do we get that? Try to understand. For example, I'm taking the case of dissociation. I'm not deriving the expression. I'll give you the expression and show you how do we use it. Let's say I've got the reaction as AN in equilibrium with N times A. Stoichiometric coefficient here is 1. Here the stoichiometric coefficient is N. And I believe N value is greater than 1. I believe N value is greater than 1. So, one particle is giving N particles. N is greater than 1. N can be 2, 3, 4. So, 1 is giving 2, 1 is giving 3, 1 is giving 4. So, this is the case of dissociation. From one particle, you are getting more than one particle. From one particle, you are getting more than one particle. So, this is the case of dissociation, first of all, right? My dear students, how do we calculate alpha here? There's a formula which I'm going to write, which you'll remember directly. Capital D minus small d divided by small d multiplied by N minus 1. What is capital D? What is small d here? I remember these terminologies. Capital D is equal to, this is what you call as theoretical vapor density. Theoretical vapor density of the reactant, which is equal to molar mass of reactant divided by 2. So molar mass of reactant divided by 2 will give you the value of capital D. What is small d? Small d is what you call as experimental vapor density. Experimental vapor density, or you call it as the vapor density of the mixture, of the gaseous mixture at equilibrium. Vapor density of the gaseous mixture at equilibrium. And let me tell you, the small d, it will be most of the times given in the question, right? Small d is the experimental vapor density, or you call it as the vapor density of the mixture at equilibrium. Capital D is theoretical vapor density of the reactant, which is molar mass of reactant divided by 2, right? What is N? N represents number of moles of products. N represents number of moles of products produced from 1 mole of reactant. Produced from 1 mole of reactant. Number of moles of products produced from 1 mole of reactant. Okay, 1 mole of reactant. What kind of question can be asked from this particular equation? Let's see that. Let's see. For example, this is one very simple and basic question. The question says, vapor density of N2O4 and NO2 mixture at equilibrium is 30. So what is this value? What is this 30? Is this small d or capital D? Vapor density of the mixture at equilibrium, that's small d, 30. Calculate the percentage dissociation. Percentage dissociation means degree of dissociation multiplied by 100. This is percentage dissociation. So basically we have to calculate alpha. The reaction that's given to us is N2O4 gas in equilibrium with 2 times NO2 gas. This is the reaction which we have, correct? Okay. What do I have to calculate? Alpha. First of all, tell me the N value. One particle is giving 2, so N value is 2. So alpha here has to be equal to capital D. I need to calculate capital D first of all, which is molar mass of reactant divided by 2. What is the molar mass of reactant? Molar mass of N2O4 is 92, right? Divided by 2, the value comes out to be 46. So alpha is equal to capital D minus small d divided by small d multiplied by N minus 1, correct? When you solve this, this value comes out to be 0.52, right? So percentage dissociation at equilibrium will be this multiplied by 100, 52%. So I would say when 52% of the reaction gets completed, then equilibrium is established in the reaction. Am I clear? Am I clear, people? Am I clear to everyone? Say it in the chats. Am I clear? Am I clear, people? All right, look at this particular question. In the reaction, the vapor density of the mixture is reduced to half. Vapor density of the mixture is reduced to half. When equilibrium is achieved, if the percentage dissociation is 25%, calculate how many moles of B will be formed at equilibrium on starting with 2 moles of A. Guys, have a look. Understand. We are given with a reaction that is A gas in equilibrium with N times B gas. So first of all, I do not know the value of N. My first priority is going to be to calculate N, right? I'll first of all try to calculate N. Now, how do I calculate N? As per the question, the vapor density of the mixture, that is small d, the vapor density of the mixture is reduced to half. Half of what? Half of the theoretical. Is reduced to half of the theoretical, right? If the percentage dissociation is 25, percentage dissociation is 25, so alpha is 25 by 100, that means it's 1 by 4. So I'll be using the formula alpha is equal to, again, capital D minus small d divided by small d multiplied by n minus 1. What is alpha? 1 by 4. Capital D minus small d is capital D by 2. D minus D by 2 is D by 2 whole divided by. This is D by 2, n minus 1. So this term cancel. 1 by 4 is equal to 1 divided by n minus 1, which tells you that n is equal to 5. So first of all, I got the reaction exactly. I got the reaction in the balanced format. My reaction in the balanced format is A gas in equilibrium with 5 times B gas. This is the reaction. Now, as per the question, since alpha we already know that's 1 by 4, correct? Initial moles of reactants are already given. How many? 2. Initial moles of reactants are already given. That is 2. Correct? Initially this will be 0. Now we are asked to calculate the moles of B. Calculate the moles of B formed at equilibrium. I'll say at equilibrium this is A minus A alpha, right? This will be 1 mole gives 5, so A alpha gives 5 times A alpha. So I would say number of moles of B at equilibrium is nothing but 5 times A alpha. This is 5. A value is how much? 2. And alpha value is how much? 1 by 4. The value comes out to be 2.5. So I would say 2.5 moles of B. 2.5 moles of B have got formed when equilibrium is established in the reaction. Am I clear with all these things? Say it in the chats. Am I clear with all these things? Is it done? Is it done, people? I hope these sort of questions you can easily solve from now on. Yes? All right. Now comes a term that's reaction quotient. What is a reaction quotient? What is exactly a reaction quotient? For example, I'm writing the reaction like this. Let's say the reaction is N1A plus N2B, it gives N3C. Let's assume that this is the reaction. Can we write the expression for equilibrium constant in terms of concentration? Yes, I can do that. It's going to be concentration of C at equilibrium raised by N3, concentration of A at equilibrium raised by N1, concentration of B at equilibrium raised by N2. Correct? This is the expression for equilibrium constant. These are all the concentrations of reactants and products at equilibrium. Now guys, if I write the same expression, concentration of C raised by N3, concentration of A raised by N1, concentration of B raised by N2. I wrote the same expression, but difference is, here I took all these concentrations of reactants and products at equilibrium. Here I am taking all these concentrations of reactants and products at any stage apart from equilibrium, right? Before equilibrium or after whatever, right? These are the concentrations. Here I am taking all the concentrations of reactants and products at any stage apart from equilibrium. Whenever the same expression, whenever the similar expression like equilibrium constant is written at any stage apart from equilibrium, you call that as the reaction quotient. So try to understand the difference between reaction quotient and equilibrium constant. Reaction quotient, here you take the concentrations of reactants products at any stage apart from equilibrium. Here particularly you take the concentration of reactants and products at equilibrium. Okay? Perfect. That's the difference between the two. Here you take concentrations of reactants products at equilibrium. Here you take concentrations of reactants products at any stage apart from equilibrium. Yeah, at any stage apart from equilibrium. Right, people? Okay. Now, at equilibrium, what do we say? At equilibrium, when equilibrium is established in the reaction, can I say at equilibrium your QC will be equal to Kc? Right? At equilibrium, your QC and Kc, they are supposed to be equal. At equilibrium, your QC and Keq, they are supposed to be equal. When there is already equilibrium in the reaction, QC value and K equilibrium, they are supposed to be equal. Okay. Now guys, try to understand one more thing. As I told you already, every reaction wants to attain equilibrium as quickly as possible. Why is that? Because equilibrium state is the most stable state, right? As per thermodynamics. Equilibrium state is the most stable state as per thermodynamics. That is the reason why every reaction wants to attain equilibrium. So can I say it like this? Can I say every reaction wants its QC to get equal to Keq? Then only equilibrium is established. Then only equilibrium is established, and hence more is the stability. More is the stability of the system, right? I can say it like this. Every reaction wants to attain equilibrium as quickly as possible, right? That means every reaction wants its QC to get equal to Keq as soon as possible. Then only I would say equilibrium is established, stability has arisen, right? Now guys, tell me one thing. Tell me just one thing. Tell me just one thing. Tell me just one thing. I have got the reaction like this. N1A plus N2B. It gives N3C. Okay. I'm writing its reaction quotient. Reaction quotient is concentration of C raised per N3, concentration of A raised per N1, concentration of B raised per N2. Right. I'm writing its equilibrium constant Kc. It is concentration of C at equilibrium raised per N3, concentration of A at equilibrium raised per N1, concentration of B at equilibrium raised per N2. Correct? I wrote QC as well as Kc. I wrote QC as well as Kc. Correct? Now, first thing we already know, at equilibrium, your Kc is equal to Qc. At equilibrium, Kc is equal to Qc. Now, my dear students, if you have got the reaction, whose Qc is less than Kc, if you have got the reaction whose Qc is less than Kc, but you already know every reaction wants to attain equilibrium. So every reaction wants its QC to get equal to Kc. If you have a reaction whose QC is less than Kc, I would say QC would try to increase its value. Then only it can become equal to Kc. How QC will increase its value? QC will increase its value if this increases and denominator decreases. This increase means concentration of product increases. Concentration of product can only increase if forward shift is favored. I'll say if forward shift is favored. Right? Similarly, I can generalize one more statement. If QC is greater than Kc, let's say you have got the reaction whose QC is greater than Kc. If QC is greater than Kc, then I would say QC will try to decrease its value. How QC will decrease its value? How QC will decrease its value? How? How QC will decrease its value? If this decreases and this increases, how this will decrease? How this will decrease? How concentration of C will decrease? How amount of C will decrease? When backward shift is favored. When backward shift is favored. Perfect. When backward shift is favored. So do remember these three statements. When QC is equal to Kc, right? Reaction is at equilibrium. Here forward reaction will proceed and here backward reaction will proceed. Do remember these three statements. Guys, there is one last topic in chemical equilibrium. What is that? That is Lee-Chatelier principle. Have you heard about this? Well, if you go into the details of Lee-Chatelier principle, it will take not less than 2 hours, right? But we just have to remember some tricks, shortcuts by means of which we can solve the questions in lesser time, right? Okay. Just a second. Just give me a second. Just a second, people. Okay. Guys, just give me a second, okay? All right. So let's talk about Lee-Chatelier principle. See, guys, what this Lee-Chatelier principle in one statement was just one statement you guys are going to remember. See, you already know when the reaction is at equilibrium, when the system is at equilibrium. When the system is at equilibrium, that is considered to be the most stable state of the system, right? If you would try to disturb the stability, then what's going to happen? If you would try to disturb the stability, I would say system will resist that. System will resist that, right? It will show resistance towards the change. So in short, whatever we do to the system, equilibrium does opposite of that. Okay? Look at the statement carefully. According to this principle, if any change is imposed on a system at equilibrium, then the equilibrium will shift in such a direction in which effect of change is nullified. So whatever we try to do to the system, equilibrium is going to do opposite of that. Just to nullify the change. Okay? So here we have effect of change in the concentration. For example, we have got the reaction at equilibrium. Reactants in equilibrium with products, right? But dear students, just tell me one thing. If you increase the concentration of reactant, or if you decrease the concentration of product, what's going to happen? If you try to increase the concentration of reactant, equilibrium will try to decrease it. How? When it will make the reaction to shift in the forward direction. Equilibrium shifts forward. This is how you can remember it. The actual way of explaining it is in terms of QC, but I don't want to go there right now. Just remember it the way I'm telling you. Similarly, if you decrease the amount of products, equilibrium will try to increase it. How? Forward shift. If you decrease the concentration of reactant, or if you increase the concentration of product, if you decrease the concentration of reactant or increase the concentration of product, if you decrease the concentration of reactant, equilibrium will try to increase it. How concentration of reactant will increase? When backward shift favors. So equilibrium shifts in backward direction. So this is the effect of change in the amount of reactants. Right, guys? This was point number 1. That was effect of addition of reactant or product. So in short, guys, whatever you do to the system, equilibrium does opposite of what we do to the system. That's all. Okay. Now, effect of change in pressure. Effect of change in pressure. My dear students, I'm assuming that. Just a second. Okay. Just give me a second, guys. Okay. For example, effect of change in pressure. I'm assuming we have got a reaction which is carried out at constant volume and temperature. Let's say this reaction is carried out at constant volume and temperature. If this reaction is carried out at constant volume and temperature, you know PV is equal to what? PV is equal to nRT. Volume, temperature constant, are already constant. So I can say pressure is directly proportional to moles. I can say pressure is directly proportional to moles. Correct? If moles increase, pressure will increase. If moles decrease, pressure will decrease. Right? I'm assuming that this reaction is carried out at constant volume and temperature. Okay? First of all, if I ask you on reactant side, how many gaseous moles do we have? 3 plus 1, 4. On product side, 2. So in the forward direction, gaseous moles are decreasing. In the forward direction, gaseous moles are decreasing. So pressure in forward direction is decreasing. Pressure in forward direction is decreasing. Pressure in backward direction. Pressure in backward direction will be increasing. Right? Pressure in backward direction is increasing. Pressure in forward direction is decreasing because gaseous moles are decreasing. Pressure in backward direction will be increasing because gaseous moles are increasing. Now tell me one thing. If we increase the pressure of the system, imagine we are increasing the pressure of the system, equilibrium will try to decrease it. If we are increasing the pressure of the system, equilibrium will try to decrease it. It will make sure that the reaction moves in the forward direction, because in the forward direction, your pressure decreases. I hope you are understanding what I'm trying to say. Right? Got it? Let's say you have got this type of the reaction. In the forward direction, pressure is decreasing. In the backward direction, pressure is increasing. So, if I try to increase the pressure, equilibrium will try to decrease it. So, it will send the reaction to forward. Right? If we decrease the pressure, equilibrium will try to increase it. That means it will send the reaction backward. Now, try to understand, in the forward direction, total gaseous moles are decreasing. I can say something like this. On increasing the pressure, reaction shifts in such a direction in which the total gaseous moles decreases. If the gaseous moles are decreasing in forward direction, then forward shift. If the gaseous moles are decreasing in backward direction, then backward shift. Okay. Whenever you see such kind of the reaction whose delta and G is 0, because on reactant side 2 gaseous moles, product side. So moles are not changing. So if you change the pressure, there will be no shift. Nothing will happen. Nothing will happen in such a reaction whose delta and G is equal to 0. If you change the pressure, change it, nothing is going to happen. Now, effect of change in temperature. Just in one statement, I'm going to, just you can remember it like this. The actual explanation is different, but I'm not giving you the actual explanations right now. I'm just telling you the things with the help of which you can remember it. Okay. Let's say you have got endothermic reaction. Here you have got exothermic. Okay. Endothermic means, let's say you have got the reaction A plus heat. A plus heat gives B. Exothermic means A gives B plus heat. Correct? You can remember it like this. I'm telling you, this is not the actual explanation, okay? You can remember it like this, so you can solve the questions. Otherwise, you know, we have to use that formula, which if you have seen my detailed lecture of equilibrium, there you would be already knowing that. But I'm not going there. Okay? So, just remember one thing. On the left side, you have got heat, right? On the left side, you have got heat. So, consider as if on left side temperature is more. Consider as if on left side temperature is more. Consider as if on right side temperature is less. Similarly, on the side of heat, consider temperature is more. Consider temperature less. Just consider. Okay? Just to remember. Now guys, in case of endothermic reactions, if we increase the temperature, equilibrium will try to decrease it. In which direction temperature is decreased? Forward. Reaction moves forward. Okay. If we decrease the temperature, equilibrium will try to increase it. So backward. This is for what? This is for endothermic. This is for endothermic. Now, what about exothermic? If we increase the temperature, equilibrium will try to decrease it backward. Right? If we decrease the temperature, equilibrium will try to increase it forward. Okay, you can remember it like this. I hope it's easy. I hope it's easy for you. You can remember it like this. Yeah? Am I clear, guys? Am I clear, people? Am I clear? Perfect. Now let's move on to one more. Effect of inert gas addition. Effect of inert gas addition at constant pressure. So guys, again, remember one statement. Effect of inert gas addition at constant pressure. At constant pressure, if you are going to add the inert gas, what is going to happen? Reaction shifts towards highest number of moles. Reaction shifts towards highest number of gaseous moles. Okay? When you add the inert gas at constant pressure, reaction will shift towards highest number of gaseous moles. And if the inert gas is added at constant volume, there will be no shift. Nothing is going to happen. Nothing is going to happen at constant volume. At constant volume. Similarly, catalyst. What a catalyst does? Catalyst does not do anything. It does not change the equilibrium constant. Catalyst just increases the rate of forward and backward reaction, due to which equilibrium is established quickly. Nothing else. Nothing else. Just tell me the answer of this question so that I'll understand whether you got it or not. Whether you got all the things or not. See guys, you have got the reaction, more H2 is added. If you are adding more H2, equilibrium will try to decrease it, so forward. Right? NH3 is added. If you increase NH3, equilibrium will try to decrease it, so backward. Correct? If temperature is increased, so on this side temperature more, on this side temperature less. If you increase the temperature, equilibrium will try to decrease it, so forward. Right? Forward. Inert gas addition at constant volume, nothing happens. At constant pressure, towards highest number of moles. Highest number of moles means backward. Correct? As simple as that. Am I clear with this? Am I clear with this, people? Tell me the answer of this particular question. The equilibrium is attained in a closed container. Closed container means volume constant. Closed container means volume constant. Right? Inert gas is added at constant volume. Nothing will happen. No change. Inert gas is added at constant volume. No change. No change. Okay. In the reaction at a given temperature, the equilibrium amount of carbon dioxide can be increased by. How can you increase the amount of carbon dioxide? You can increase the amount of carbon dioxide when you will shift the reaction forward. Now, how reaction will shift forward? Reaction will shift forward if we increase the amount of CO, equilibrium will try to decrease it, then only reaction shifts forward. So, increasing the amount of CO. Simple. Right? Perfect, guys. I hope all these things you can do from now onwards on your own. And now it is the time for ionic equilibrium. And ionic equilibrium we shall start exactly at what time? Tell me the time. So I'll see you at we'll get back at 3:40, okay? Take 30 minutes break. We'll also take a break. Because I'm not well today. You would have noticed that, correct? Because I'm not shouting, etc. I'm teaching slowly today. Yeah? So take a break for 30 minutes, get back on time, have some tea, refresh yourself, and come back. But do come back, every one of you, huh? Because Ionic Equilibrium, after this, we are done. Okay, see you. Is everyone back? Is everyone back? Quick, quick, quick. So people, we are done with chemical equilibrium. Now it's the time for the ionic equilibrium. Yes? Now it's the time for the ionic equilibrium. I hope whatever I've discussed in chemical equilibrium, I hope all those things are absolutely clear to you. Right? Just give me a second and we shall be starting. Huh? Well, it's not going to take a lot of time to finish this one, as I can see the slides. I think everyone is back. Yeah? I think everyone is back. No, I did not have my lunch, because if I have lunch, then I'll feel sleepy, right? So I'll have it once I'm done with this marathon. Well, during the breaks, I keep on having the tea or coffee. Yeah? Perfect then. Let's start the, well, you know, this particular chapter people find very tough. Okay? But if your chemical equilibrium concepts are clear, I don't think it's going to be tough for you. No way. Okay? And I shall be starting again from the basics only. So you need not to worry. So without wasting any sort of time, let's get going. Let's get started. And the first and the basic topic, which you all can see on your screen right now, what is that? That is electrolyte. How do we exactly define the term electrolyte? What is an electrolyte? My dear students, it's a complete basic terminology. Any substance which on dissolving in water, dissociates into their ions. Any substance which on dissolving in water dissociates into its respective ions, you call that particular substance as the electrolyte. Okay, for example, you have got HCl. When you put HCl into water, it dissociates, it breaks down into H positive and Cl negative. So it's an electrolyte. You take H2SO4, put it into water, it breaks down into H positives and SO4 dinegatives, electrolyte. You take NH4OH, put it into water, it gives NH4 positive, OH negative. So again an electrolyte. So what is an electrolyte in general? Any substance which on dissolving in water dissociates into its respective ions. We call that substance as electrolyte. Now guys, we have got two different types of electrolytes. One is called as strong electrolyte, one is called as weak electrolyte. What is a strong electrolyte? Strong electrolyte is the one which completely dissociates into its respective ions. Weak electrolyte, it partially dissociates. It does not completely dissociate. It partially dissociates into its respective ions. Okay. Well, if I talk about the strong electrolytes, in case of strong electrolytes, alpha value is equal to 1. In chemical equilibrium, we used to call this alpha as degree of dissociation. Here, I'll be calling alpha as degree of ionization. Meaning is same, it is just terminologies are different. Okay? Alpha here I'll be calling as degree of ionization is 1. for strong electrolytes. What are the examples of strong electrolytes? All your strong acids, all your strong acids, all your strong bases, right? All your strong bases and all your water-soluble salts. All your water-soluble salts. They are the examples of strong electrolytes. That means they dissociate completely into their ions when introduced in water. Okay. Now, what about weak electrolytes? In case of weak electrolytes, alpha value is less than 1. Degree of ionization is less than 1. Or I can say the value of alpha, it ranges between 0 to 1. It is between 0 to 1. The point is, what are the examples of weak electrolytes? My dear students, all your weak acids, all your weak bases, all your sparingly soluble salts, all your sparingly soluble salts, they are the examples of the weak electrolytes which partially dissociate when you introduce them into water. Okay, let's have a look. Exactly. Strong electrolytes are completely ionized. All strong acids, all strong bases and water-soluble salts, right? Now, if you ask me what are the examples of strong acids? Example of strong acid is, for example, your HCl, your H2SO4. These are the common examples of strong acids. Common examples of strong bases. Let's say you have got NaOH, it's a strong base. Water-soluble salts. My dear students, remember the general salts of alkali metals. The general salts of alkali metals. For example, NaCl. It is one general salt of alkali metal. The general salts of alkali metals. Number 1. Number 2. Salt of NH4 positive and NO3 negatives. NH4 positive. Tell me any salt of NH4 positive. It's NH4Cl. NH4Cl is the salt of NH4 positive, right? Let's say you have got NaNO3. NaNO3. This is the salt of NO3 negative, right? Do remember general salts of alkali metals, salts of NH4 positive ion and salts of NO3 negative. They are water soluble. And all the water soluble salts, they are what? They are the examples of strong electrolytes. As simple as that. Okay. Similarly, when it comes to the weak electrolytes, right? What are weak electrolytes? They are partially ionized. I told you already. Okay. All the sparingly soluble salts, these are the examples of your sparingly soluble salts. These are the examples of the weak electrolytes. All the weak acids. Weak acid, for example, CH3COH. It's a weak acid, right? Weak base, for example, NH4OH. It's a weak base. They are the examples of the weak electrolyte, right? They are the examples of the weak electrolytes. My dear students, one very important statement from where I'll be starting this chapter. Do remember, a weak electrolyte always remains in equilibrium with its ions. Whenever you introduce a weak electrolyte in water, the weak electrolyte is going to remain in equilibrium with its ions. For example, if you talk about CH3COOH, it's a weak acid. If it's a weak acid, it's going to remain in equilibrium with its ions. And its ions are these two, right? For example, you have got NH4OH. It's a weak base, weak electrolyte. When you put it into water, it's going to remain in equilibrium with its ions. And its ions are NH4 positive aqueous plus OH negative aqueous, right? So in short, do remember, weak electrolyte, it always remains in equilibrium with its ions. Okay? It remains in equilibrium with its ions. This is one of the most important points. Okay? Now guys, let's move on to the first topic which we have. That is ionization constant of a weak electrolyte. Ionization constant of a weak electrolyte. What it means? Let's have a look. For example, my dear students, try to understand carefully. Let's say I have got a weak electrolyte AB. I'm introducing this weak electrolyte into water. It is going to remain in equilibrium with its ions. Its ions are A positive aqueous plus B negative aqueous. A positive aqueous plus B negative aqueous. Okay. For example, at time t is equal to 0, let's say the concentration of this electrolyte was C molar. This is 0, this will be 0. Let's say the degree of ionization is alpha. So at equilibrium, can you let me know the concentration of AB left? It is going to be C minus C alpha. The way we did in equilibrium, chemical equilibrium, A minus A alpha. In the similar way, we are directly starting with concentration. So it has to be C minus C alpha. Now 1 mole gives 1 mole. From C alpha, you get C alpha. This will be also C alpha. So what did I get over here? If you look carefully, this is the concentration of AB at equilibrium. This is the concentration of A positive at equilibrium. This is the concentration of B negative at equilibrium, right? I took a weak electrolyte AB. I introduced that in water, right? The weak electrolyte remained in equilibrium with its ions. And at the end, I'm telling you, These are the concentrations of all the species in the container. These are the concentrations of all the species in the container, right? Now, my dear students, in case of the weak electrolyte, if you want to write the equilibrium constant expression, the equilibrium constant here is called as ionization constant. It is just terminology is different. Meaning is same. Equilibrium constant here is called as ionization constant, right? And my dear students, how do I write the expression for Ki? You know it. Start with the product. Concentration of A positive at equilibrium raised by stoichiometric coefficient. Concentration of B negative at equilibrium raised by stoichiometric coefficient divided by concentration of AB at equilibrium raised to the power stoichiometric coefficient. That's 1. Correct? Now, after this, if you look carefully, what is the concentration of A positive at equilibrium? I'll be writing first of all Ki is equal to concentration of A positive at equilibrium is nothing but C alpha. Concentration of B negative at equilibrium is nothing but C alpha divided by concentration of AB at equilibrium is C minus C alpha. This is how you wrote the expression for Ki, which is basically the equilibrium constant, but here we call this as the ionization constant of the weak electrolyte. Okay? Now guys, if you write it properly, Ki is equal to, if you take C common, 1C cancelled, so this becomes C alpha square divided by 1 minus alpha. So this is how you write the expression for ionization constant of a weak electrolyte. Right? This is how you write the ionization constant of the weak electrolyte. Okay? My dear students, try to understand. From here, the actual scenario is going to start. Till here, it's all easy. You know it. Instead of A, we are writing C, nothing else. Instead of equilibrium constant, we are writing Ki. Rest, everything is same. Now, from here, we are going to assume certain things. Let alpha be less than 0.05. I'm assuming alpha is less than 0.05. This is something which I'm assuming. Let alpha be less than 0.05. When you assume alpha to be less than 0.05 at that point of time, instead of 1 minus alpha, we can neglect alpha, we can just write 1. Okay. Now, if I write the Ki expression again, so Ki now becomes C alpha square. Instead of 1 minus alpha, it's 1. So from here, alpha is equal to under root of Ki divided by C. From here, we got to know alpha is equal to under root of Ki divided by C. Okay. My dear students, in the question, you will be given with alpha value, you will be given with C value. That means you can calculate the actual value of alpha. If the actual value of alpha comes out to be less than 0.05, that means whatever you assumed here, that's absolutely right. Whatever your assumption was, that is right. If alpha does not come out to be less than 0.05, then you cannot neglect alpha in comparison to 1. So I'm just telling you when to neglect alpha, when not. So first of all, I assumed let alpha be less than 0.05, right? I got the alpha value, under root of Ki by C, right? Under root of Ki by C. If Ki is given, C is given. I can calculate alpha, right? When the alpha which you will get from here, if it actually comes out to be less than 0.05, that means your assumption is absolutely right. You can neglect alpha in comparison to 1. If the alpha value comes out to be greater than 0.05, then you cannot neglect alpha in comparison to 1. Am I clear? Am I clear, people? Am I clear? Am I clear? And I am assuming the value of alpha which we get from here, I'm assuming that is coming out to be less than 0.05. Then in the question, they'll ask you the concentration of A positive at equilibrium. The concentration of A positive at equilibrium is C times alpha, and alpha is nothing but under root of Ki by C, right? They'll ask you the concentration of B negative at equilibrium. It's nothing but C alpha. Alpha is nothing but under root of Ki divided by C. I hope I'm clear. I hope I'm clear, people. Right? Perfect. Let's try to do one question so that you can understand this concept, right? So that you can understand this concept. Let's try to do one question. Let's try to do one question. Let me tell you, in your NEET examination, they'll always give you those questions where alpha will be less than 0.05 only, right? In JEE, they used to give alpha greater than 0.05, wherein quadratic equations were supposed to be solved. But in your NEET, they won't do that to you. Now guys, see, Calculate the concentration of each ion at equilibrium for 0.1 molar solution of weak electrolyte AB. As per the question, you have got the weak electrolyte AB. If it's a weak electrolyte, it's going to remain in equilibrium with its ions. Ions are A positive aqueous plus B negative aqueous. A positive aqueous plus B negative aqueous. Now, initially, at time t is equal to 0, the concentration of AB here is 0.1 molar. This is 0 and this is 0. At equilibrium, this is C minus C alpha. This will be C alpha. This will be C alpha. You know it. If I write the expression for ionization constant, it has to be C alpha square divided by 1 minus alpha. Few minutes back, I told you how to write it. Now, what do we do after this? We assume things. Let alpha be less than 0.05. At that point of time, instead of 1 minus alpha, you can write 1. Instead of 1 minus alpha, you can write 1. Okay. Instead of 1 minus alpha, you can write 1. Now, my dear students, understand. So, Ki I can further write as simply C alpha square. And alpha I can calculate as under root of Ki divided by C. Now, as per the question, if you look carefully, Ki is given as 10 raised power minus 5. C is given as 0.1. That means 10 raised power minus 1. It comes out to be under root of 10 raised power minus 4, which is 10 raised power minus 2. That means 0.01. So, alpha value you are getting as 0.01, which is actually less than 0.05. That means your assumption is absolutely right. Whatever you assume, that's perfectly fine. Yeah. Now, what am I supposed to calculate? I'm supposed to calculate the concentration of each ion. You know the concentration of A positive and the concentration of B negative at equilibrium. Both are equal to C times alpha. Since C is given to us as 0.1, alpha we got to know as 10 raised power minus 2. The overall value comes out to be 10 raised power minus 3 molar. So this is the concentration of A positive and B negative in the container at equilibrium. I hope this is clear. Am I clear with this? Quick people, am I clear with this? Am I clear with this? Let me know quickly in the chats. Now, I told you the general way. I gave you the general electrolyte AB. What if that electrolyte, that weak electrolyte, till now I took the electrolyte AB. I took the weak electrolyte as AB. Now, what if that weak electrolyte is your weak acid? Right? What if that weak electrolyte is your weak acid? Okay, HA. Let's say HA, it's a weak acid. Weak acid means weak electrolyte. So, in aqueous solution, it's going to remain in equilibrium with its ions. Its ions are H positive aqueous and B negative aqueous. Correct? My dear students, when you take weak acid particularly, right, then Ki is called as Ka. Dissociation constant or ionization constant of a weak acid. Okay? Right? Perfect. You call it as Ka. It is same equilibrium constant only. It is just if you take weak electrolyte in general, then it's Ki. If you take weak acid, then it's Ka. That's all. Rest everything is normal. You know it. Right? This is, for example, C. This is 0. This is 0. Degree of ionization is alpha. So at equilibrium, this is C minus C alpha. This is C alpha. This is C alpha. If you write the expression for Ka, that is going to be C alpha square divided by 1 minus alpha. If you assume alpha to be less than 0.05, at that point of time, instead of 1 minus alpha, you can write 1. So your Ka is equal to C alpha square. Alpha is equal to under root of Ka divided by C. Correct? Right? Right, people? Now tell me one thing. Tell me one thing. Alpha and Ka, they are directly proportional to each other. Tell me just one thing. More the value of Ka, more the ionization constant of the weak acid, more the value of Ka, more is going to be alpha. More is going to be alpha. More the value of alpha. That means more the degree of ionization. More the degree of ionization. What is meant by more degree of ionization? That means more ions are going to get produced. More ions are produced. More ions produced means more H positive concentration. More ions produced means more H positive concentration in the container. More H positive concentration in the container. More the H positive concentration in the container, more is going to be the strength of the acid. Right? More is going to be the strength of the acid. So do remember this particular point as well. Simple, right? Perfect. All right, let's talk about the weak base. Let's assume the weak electrolyte which you have taken, that is your weak base. If you are taking weak base as BOH, if you introduce this in water, it's going to remain in equilibrium with its ions, which is B positive aqueous plus OH negative aqueous. B positive aqueous plus OH negative aqueous. Now, my dear students, try to understand. Initially, at time t is equal to 0. Imagine this is C, this is 0, this is 0. This is alpha. So at equilibrium, this is going to be C minus C alpha. This will be C alpha. This will be C alpha. The same procedure. It is just when you take the weak electrolyte as weak base, then instead of Ki, you just have to write Kb. Rest everything is same. C alpha square divided by 1 minus alpha. And after that, we'll assume things. Let alpha be less than 0.05. At that point of time, instead of 1 minus alpha, you can write 1. So your Kb comes out to be C alpha square. So from this particular expression, you can get alpha, which is under root of Kb divided by C. Under root of Kb divided by C. Now let me tell you one thing here. More the value of Kb, more is going to be the value of alpha. More the value of Kb, more is going to be the value of alpha. If the value of alpha is more, that means degree of ionization is more. So what you'll observe? You'll observe more ions in the solution. More ions in the solution means more will be the OH negative concentration in the solution. And more the OH negative ion concentration, I'll say strength of base has to be more. Strength of base has to be more. I believe all these things are clear. Yes. I believe all these things are clear. Right, people? Perfect. Now, guys, can we solve this question quickly? Can we solve this question quickly? Check it out. Calculate the concentration of H positive ion. Sorry, calculate the H positive ion concentration of a 0.05 molar CH3COH. K is given. Okay. So as per the question, you are given with a weak acid CH3COH. Weak acid means weak electrolyte. When you put it into water, it's going to remain in equilibrium with its ions. Its ions are CH3CO negative aqueous plus what? Plus H positive aqueous. Correct? Now, you know, at equilibrium, I'm directly writing, at equilibrium, this is going to be C minus C alpha, this will be C alpha, this is C alpha. What am I supposed to calculate? I'm supposed to calculate the concentration of H positive. And concentration of H positive is nothing but C alpha. Okay? How do we get alpha? Alpha, you already know it's under root of Ka divided by C. So, under root of Ka, 1.25 into 10 raised power minus 6 divided by C. What is C? C is the concentration, 5, 0.05. 0.05. This is 1, this is 25. Root of 25 is 5. So this 5 into 10 raised power minus 3. So alpha is coming out to be less than 0.05. Alpha is coming out to be less than 0.05. Now after this, if alpha you got, what was I supposed to calculate? Concentration of H positive in the container at equilibrium. That's going to be just C alpha, and C is your concentration of weak acid, that's 5 into 10 raised power minus 2 multiplied by 5 into 10 raised power minus 3. The value comes out to be 25 into 10 raised power minus 5 molar. Am I clear to everyone? Am I clear to everyone, people? Quick. Okay, guys? Done? All right, let's see one more question then. Look at this particular question. It's again simple. Sir, these type of questions are asked in NEET. Why do you think I'm teaching you all this then? Did you see the name of the channel? Unacademy NEET English. My dear students, if you look at this particular question, calculate the ionization constant of a weak base. Calculate the ionization constant of a weak base. The base that's given to us is NH4OH. Since it's a weak base, right, it's going to remain in equilibrium with its ions. Ions are NH4 positive aqueous, and with that you have got OH negative aqueous as well, right? OH negative aqueous as well. As per the question, if the concentration of OH negative in its 0.1 molar aqueous solution, so I'm given with the concentration over here as 0.1 molar. This will be 0, this will be 0. At equilibrium, you already know this has to be C minus C alpha. This is C alpha, this is C alpha. Now, as per the question, if the concentration of OH negative, in the solution is how much? 0.05 molar. This is given to me. Concentration of OH negative in the solution is 0.05 molar. Now, what is the concentration of OH negative in the solution? That is C alpha. So, C alpha is 0.05. So, alpha has to be equal to 0.05 divided by C. What is C? 0.1, right? The value comes out to be 0.5. Alpha here is coming out to be 0.5. So, it is not less than 0.05. That means you cannot say 1 minus alpha is equal to 1. This assumption will be wrong. This assumption will be wrong, right? This assumption will be wrong. Now here, what do we have to calculate? Ionization constant of the weak base. I have to write the complete expression, C alpha square divided by 1 minus alpha. I cannot neglect alpha here. Okay, so it is C. C is 0.1. Alpha square, alpha is 0.5 cos square divided by 1 minus 0.5 is 0.5. So 0.5 cancel. The value comes out to be 0.05. This is the value of ionization constant of the weak base which I was supposed to calculate. Am I clear with this? Am I clear with this, people? Right? Now comes one simple topic which I believe all of you would be already knowing. Have you heard about Oswald's dilution law? Have you heard about Oswald's dilution law? Oswald's dilution law, right? It's a simple law over here. What it states is that it states with dilution, degree of ionization of a weak electrolyte increases. With dilution, degree of ionization of a weak electrolyte increases, right? With dilution, degree of ionization of a weak electrolyte increases. Let's say I've got the weak electrolyte AB, putting it into water. So it's remaining in equilibrium with its ions. Ions are A positive aqueous plus B negative aqueous, right? Initially, time t is equal to 0. Its concentration is C. This is 0. This is 0. Degree of ionization is alpha. At equilibrium, this is going to be C minus C alpha. This will be C alpha. This will be C alpha. Now, if I write the expression for Ki, that's going to be C alpha square divided by 1 minus alpha. Let alpha be less than 0.05. At that point of time, your alpha comes out to be under root of Ki divided by C. This expression we know? Yes, this is something which we already know, correct? Now, guys, tell me one thing. What we did exactly? We have introduced weak electrolyte into water. Perfect. Let's say that weak electrolyte. Let's say everything is happening in this container. Okay, in this container, your weak electrolyte is in equilibrium with its ions. Correct? Now, guys, one thing. What is C? C is concentration, number of moles per unit volume. As per Oswald's dilution law, if you do the dilution, if you introduce extra solvent here is water. If I'm putting extra water in the container, if I put extra water in the container, volume of the solution will increase. If volume of the solution is increasing, concentration will decrease. If C is decreasing, that means alpha will increase. That's what I was telling. With dilution, degree of ionization of a weak electrolyte increases. So if you keep on doing dilution continuously, degree of ionization of weak electrolyte is increasing. That means this electrolyte is getting more and more converted into its ions, right? Perfect. And if you keep on doing the dilution, there will be a scenario when this weak electrolyte also would get completely dissociated. And that time, we call that as infinite dilution. We call that as infinite dilution. At infinite dilution, the weak electrolyte behaves as, it behaves like a strong electrolyte. It behaves like a strong electrolyte. Okay, so I'll say at infinite dilution, degree of ionization of a weak electrolyte also is equal to 1. Only at infinite dilution. Your weak electrolyte behaves as a strong electrolyte at infinite dilution. Correct? I hope this is clear. Moving ahead, let's talk about something very important, that's common ion effect. Have you heard about this common ion effect? Tell me in the chats, have you heard about this one? Have you heard about common ion effect? Common ion effect. See guys, what this common ion effect exactly is all about. Try to understand, right? Because this common ion effect will be frequently used in this chapter. See guys, as per this common ion effect is concerned, common ion effect is defined as the suppression means decrease. The suppression of degree of ionization of a weak electrolyte when a strong electrolyte containing a common ion is added into it. What does that mean? What does that mean? What does that mean? See guys. For example, this is the container which I have. Okay. This is the container which I have. Assume that I'm taking a weak electrolyte here, CH3COH. I've introduced weak electrolyte into water, so it's going to remain in equilibrium with its ions. Its ions are CH3CO negative aqueous plus H positive aqueous. Let's assume the degree of ionization of this weak electrolyte is less than 0.05. Let's assume that it is less than 0.05. Okay. So initially its concentration was C, this was 0, this was 0. Now this is C minus C alpha at equilibrium. This is C alpha and this is C alpha. Okay, now this is C alpha. Now this is C alpha. My dear students, since this weak electrolyte is in equilibrium with its ions, and I'm assuming alpha value for this weak electrolyte is less than 0.05. It is less than 0.05. It is less than 0.05. Now, in the same container, wherein this weak electrolyte is in equilibrium with its ions, in the same container, I'm introducing a strong electrolyte. If I'm introducing a strong electrolyte, it will get completely dissociated into its ions. It will get completely dissociated into its ions. Let's say its concentration was C1, this was 0, this was 0. Now it got completely dissociated. So this is 0. This will be C1, this will be C1. Correct? Correct, people? Now try to understand one thing. Try to understand one thing. In the same container, I have got a weak electrolyte and a strong electrolyte. Both are having one ion in common. Both are having one ion in common. Whenever you see such kind of the scenario in which in the same container you have got a weak electrolyte and a strong electrolyte, both having one ion in common, remember, common ion effect is going to operate here. Common ion effect is going to operate here. And what happens due to common ion effect? What happens due to common ion effect? Since before the addition of strong electrolyte, this weak electrolyte was in equilibrium with its ions. Now when you added the strong electrolyte, okay, what is happening? The concentration of H positive is increasing. Since you are adding HCl, that means you are adding H positives. So if I ask you what is the total H positive concentration, C alpha is the concentration of H positive which we got from weak acid. C1 is the concentration of H positive which we got from strong acid. So total common ion concentration is C1 plus C alpha. This is the net H positive concentration. So basically, due to the addition of HCl, we are trying to increase the concentration of H positive. And if you look, this reaction was already at equilibrium. Okay, this was at equilibrium. Now you're trying to increase the concentration of H positive. You're trying to increase the concentration of H positive with the help of the addition of HCl. If you are trying to increase the concentration of H positive, you know, this reaction was at equilibrium. Equilibrium will try to shift in such a direction in which concentration of H positive decreases. Which direction is that? That is backward direction. That is backward direction. So this reaction will now shift backwards. What will happen due to that? These ions will, right? This ion and this ion, they'll react and form what? CH3COH back, right? Backward reaction is happening here. Due to which ions in the container are decreasing because they're again forming CH3COH. They're again getting converted into CH3COH. Ions in the container are decreasing. What does that mean? That simply means the degree of ionization of a weak electrolyte is suppressing. It's decreasing. It is decreasing. That suppression in the degree of ionization of a weak electrolyte, when a strong electrolyte carrying a common ion is added, that suppression in the degree of ionization is something which you call as common ion effect. Did you get it? Okay. Now, my dear students, already I had told you alpha value of the weak electrolyte was already less than 0.05. Now, due to common ion effect, degree of ionization has further decreased. So, alpha value has further decreased. So, wherever you see alpha, you can neglect that. So, instead of C1 plus C alpha, I can just write C1. Instead of C1 plus C alpha, I can just write C1. Correct? Now, guys, if I write the expression for Ka, Ka is concentration of CH3CO negative, which is C alpha. Concentration of H positive, that is just C1, divided by concentration of CH3COH, that is C minus C alpha, C common, 1 minus alpha. So C and C cancel. Instead of 1 minus alpha, you can write 1 because, you know, alpha has decreased. So Ka is nothing but C1 multiplied by alpha. So alpha here comes out to be Ka divided by C1. Tell me, is it the alpha, is it the degree of ionization of the weak electrolyte before the common ion effect or after the common ion effect? Or in short, tell me, is this the old alpha or new alpha? Old alpha was less than 0.05. New alpha will be very less than that also. Right? Perfect. Perfect, guys. So you got the alpha, new alpha. After the operation of common ion effect, this is the new alpha. Right? Now there will be questions which will be asked. Calculate the concentration of CH3CO negative, right, in the container. You will say it is C times alpha. C will be given to you already. Alpha you got from here, right? If they ask you calculate the concentration of H positive in the container, you need not to do anything. Concentration of H positive in the container is C1 directly. So basically from this particular statement, you can analyze one thing. The concentration of common ion is governed by strong electrolyte. The C1 was the concentration of H positive which was coming from strong electrolyte. And I told you the concentration of common ion at the end is equal to C1 only. So the concentration of common ion is entirely decided by what? Strong electrolyte. Am I clear? The concentration of common ion is entirely decided by the strong electrolyte. Perfect? Perfect, guys? Remember this particular point. This is important. This is very important. The concentration of common ion is decided by the strong electrolyte. Look at this question. These are two questions basically. Let's have a look. Calculate the concentration of each species at equilibrium in an aqueous solution containing. So first we have got only NH4OH in the container. NH4OH in the aqueous solution would have got dissociated as NH4 positive aqueous plus OH negative aqueous. Right? Let's say initially this is C, this is 0, this is 0, degree of ionization is alpha. So at equilibrium, I must say this will be C minus C alpha, this will be C alpha, and this will be C alpha. Okay? So, if I write the expression for Kb, you know it, it is C alpha square divided by 1 minus alpha. What do we do after that? We assume let alpha be less than 0.05. At that point of time, instead of 1 minus alpha, we are just going to write 1. So your Kb is equal to C alpha square. So from here, alpha is equal to under root of KB divided by C. So alpha is equal to under root of KB divided by C. What is KB? KB is 1.8 into 10 raised power minus 5 divided by C. C is the concentration of NH4OH, that is 0.1 molar, right? Root of 1.8 is 1.34. So 1.34 into 10 raised power minus 2. So this is alpha. This is alpha. This is the alpha of this weak electrolyte which we got. So already alpha is less than 0.05. As you can see, alpha is less than 0.0. Correct? Now, calculate the concentration of each species at equilibrium in an aqueous solution. Okay. Alpha is already less than 0.05. Perfect. In the first question, we are supposed to calculate the concentration of NH4 positive as well as the concentration of OH negative. And both are equal to C times alpha. C is how much? C is 0.1. Alpha is this much. So C into alpha is 1.34 into 10 raised power minus 3 molar. Right? Concentration of each ion. Now, my dear students, the second part of the question says that already there was NH4OH in the container, right? Whose alpha was 1.34 in 10 raised power minus 2. Already this was there in the container. This was C. This was 0. This was 0. At equilibrium, this was C minus C alpha. This was C alpha. This was C alpha. Correct? In the same container, wherein already NH4OH was present, right, with its ions at equilibrium. In the same container, you are introducing what? You are introducing NH4Cl. NH4Cl is a strong electrolyte, which would have got dissociated completely into its ions. If this was C1, which is given as 0.1 molar here, right? This is 0, this is 0. Now this is 0, this is C1, and this is C1. So which effect will operate over here? I would say we have got a weak electrolyte and a strong electrolyte. Weak electrolyte, strong electrolyte, both having one ion in common. Which ion is that? NH4 positive. Both having one ion in common in the container. So the concentration of common ion should be C1 plus C alpha, right? But due to common ion effect, the degree of ionization of the weak electrolyte will decrease because this reaction will shift backwards. Degree of ionization will decrease, right? Already alpha was less than 0.05. Now it will further suppress. Therefore, wherever you want to neglect alpha, you can do that. Instead of C1 plus C alpha, you can just write C1. So if you want to write the expression for KB will come out to be same. I hope you remember. KB expression will be concentration of this, that is C1, concentration of this, that is C alpha, divided by concentration of this, that is C minus C alpha. Instead of 1 minus alpha, we can write 1. CC got cancelled. So KB is coming out to be C1 alpha. So alpha is equal to KB divided by C1. Alpha is equal to KB divided by C1. This is the new alpha. KB is given 1.8 in 10 raised power minus 5. C1 is how much? C1 is 0.1. So the new value of alpha will come out to be how much? 1.8 into 10 raised power how much? Minus 4. Right? It's KB by C1. KB you know, C1 you know. So this is the new value of this is the new value of alpha. Right? This is the new value of alpha. Now check one thing. Check the old value of alpha as well as new value of alpha. Compare them. Check the old and new value of alpha. Do you see actually alpha value has decreased? Earlier it was 1.34 in 10 raised power minus 2. Now due to the addition of strong electrolyte having one ion in common, alpha value has decreased. It's now 1.8 in 10 raised power minus 4. So this is the new alpha. This is the new alpha here. What am I supposed to calculate? Concentration of each ion. Now tell me the concentration of each ion. Concentration of NH4 positive will be equal to how much? C1, and C1 is 0.1 molar. Right? So concentration of NH4 positive in this particular case is what? 0.1 molar. Concentration of OH negative. Concentration of OH negative is C times alpha. How much is C? C is 10 raised power minus 1. How much is alpha now? It's a new alpha. 1.8 in 10 raised power minus 4. So this value will come out to be 1.8 in 10 raised power minus 5 molar. Did you get the idea of how to solve these sort of questions? Did you get the idea, people? Quick. Quickly, people. Done? Sir, increase the brightness. I cannot do that. There is electricity cut. There is electricity cut, so I'm just managing to take the session. Is it clear, people? Is it clear? Can you tell me the answer of this one? So first of all, how do you calculate nu alpha? Now you need not to do the entire procedure again and again. Nu alpha is equal to ionization constant divided by C1, where C1 is the concentration of the common ion, which is decided by the strong electrolyte, right? This is the nu alpha. Concentration of common ion is always equal to what? It is always decided by the strong electrolyte. These two things directly remember. If you remember them, you can solve the equations in lesser time. Okay? You can solve the equations in lesser time. Now, try to understand. Try to understand, guys. Calculate the concentration of H positive and CH3CO negative at equilibrium if 0.5 molar HCl is added in an aqueous solution containing. So, again, weak electrolyte, strong electrolyte case. So, common ion effect is going to operate, right? Common ion effect is going to operate. So, what will be the nu alpha? Nu alpha will be Ka divided by C1. What is Ka? 1.8 into 10 raised power minus 5. What is C1? C1 will be 0.5 molar. So it will be 3.6 into 10 raised power minus 5. This is nu alpha. Got it? Concentration of common ion is entirely decided by the strong electrolyte, which is HCl, right? So 0.5 molar, direct answer. Concentration of CH3CO negative is asked too. Concentration of CH3CO negative will be C times alpha, where C is the concentration of CH3CO is, that is 0.1 molar. Nu alpha is how much? Nu alpha is 3.6 into 10 raised power minus 5. Answer comes out to be 3.6 into 10 raised power minus 6 molar. Correct? Correct, people? So if you remember the procedure, you are not supposed to do it all the time. Just remember things and do it. That's all. Right, people? All clear? All clear till here? I hope this is clear. Now comes one more topic, that's ionic product of water. Ionic product of water. I believe you all must be knowing water. If you talk about pure water, H2O liquid, pure water, it is considered as a weak electrolyte. If it is considered as a weak electrolyte, it is going to remain in equilibrium with its ions. Right? It's going to remain in equilibrium with its ions. Since water being the weak electrolyte, if I write its ionization constant, it is going to be concentration of H positive raised power 1, concentration of OH negative raised power 1 divided by concentration of H2O. Okay. Well, Ki, if I talk about Ki, ionization constant of water here, it's a constant. Concentration of water is also constant. It is going to be concentration of H positive multiplied by OH negative in the container. Basically, this water is in equilibrium with its ions in the container, correct? This is constant, this is constant. Multiplication of two constants is a new constant, Kw. So, Kw has to be equal to concentration of H positive multiplied by concentration of OH negative. Okay? This is what you call as ionic product of water. This Kw is what you call as ionic product of water. Kw is what you call as ionic product of water. This is what we call as ionic product of water, right? Ionic product of water. Now guys, this particular result, it is valid at all temperatures. It is valid at all temperatures. Let me tell you. The value of Kw, right? It's valid at all temperatures. Number one. Number two, if I keep the temperature 25 degrees centigrade, let me tell you at 25 degrees centigrade, concentration of H positive and concentration of OH negative in the container will be equal, which will be 10 raised power minus 7 molar. Which will be 10 raised power minus 7 molar. So your Kw, which is basically concentration of H positive multiplied by concentration of OH negative. 10 power minus 7, 10 power minus 7 comes out to be 10 raised power minus 14. Correct? 10 raised power minus 14. But this is valid, this particular one is valid only at 25 degrees centigrade. Now people, if you look carefully, have you heard about pH? What is P basically? P stands for minus log, nothing else. And pH means minus log of H positive. POH means minus log of OH negative. PK means minus log of K. So P is a mathematical operator which stands for minus log, nothing else. P is a mathematical operator which stands for minus log. So what I'll be doing over here, if I multiply throughout by minus log, it becomes minus log of Kw is equal to minus log of H positive concentration, OH negative concentration, which is minus log of 10 raised power minus 14. So I would get something like this. PKW is equal to, this is going to be pH plus pOH, and the value comes out to be 14. This is one result which I believe all of you would be knowing. pH plus pOH is equal to 14. But remember, this result is only valid at 25 degrees centigrade. This result is only valid at 25 degrees centigrade, right? My dear students, one more thing. The value of Kw increases on increasing the temperature. Okay? Kw depends on temperature, and the value of Kw increases on increasing the temperature. The value of Kw increases on increasing the temperature. When you increase the temperature, what happens? When you increase the temperature, its degree of ionization increases, right? More H positives and more OH negatives are generated. Perfect. More H positives and more OH negatives are generated. And more H positive, more OH negative generated means more will be the value of Kw at the end. Right? Am I clear with this? Am I clear with this, people? More the value of temperature. If you increase the temperature, Kw will increase. One thing which I would want you to remember directly, okay? On increasing the temperature, since Kw increases, pH of water decreases, but neutrality of water remains the same. Neutrality of water remains the same, right? Remember this particular point also, and remember it directly. It can be asked. When you increase the temperature of water, what will happen? Its pH will decrease, number one, right? But nothing will happen to its neutrality. Neutrality is going to remain the same. Okay, remember this particular point as well. This can be asked. And my dear students, one thing which I believe you all would be knowing, what is that? Imagine in the solution, if the concentration of H positive and OH negative are equal, we call that particular solution as a neutral solution, whose pH is taken as how much? Whose pH will be 7, right? And if the concentration of H positive in the final solution is greater than that of concentration of OH negative, then it is going to be the acidic solution, whose pH will be less than 7. And at the end, let me tell you, if the concentration of OH negative is greater than that of concentration of H positive, then it's going to be an alkaline solution, or you can call it as the basic solution, whose pH will be greater than, right? Okay. At what? At 25 degrees centigrade. If temperature is not mentioned in the question, assume the temperature is 25 only. Okay? Perfect. Okay, all these things we have discussed in detail. I'm moving ahead. Calculation of pH. There are different cases in pH, right? And let's try to understand this pH. Let's try to see how do we calculate the pH of different species. The first one is pH of strong monoprotic acids and bases. How do we calculate pH of strong monoprotic acids? First of all, how do we calculate pH? P is nothing but minus log. If you will be having a solution, right? You want to calculate the pH of that solution. Just get the concentration of H positive in the solution first. Get the concentration of H positive in the solution. Once you get the concentration of H positive in the solution, take minus log of it. Whatever value comes, that's going to be the pH of the solution. That is going to be the pH of the solution. For example, these are different cases which are given to us. Let's have a look. These are different examples that are given to us. For example, calculate the pH of 0.1 molar HCl. What does it mean? It means that you have taken HCl, you have introduced it into water. First of all, these are all strong acids or strong bases, right? You have introduced it into water. So strong acid is a strong electrolyte which would have got completely dissociated, H positive plus Cl negative, correct? So initial concentration of HCl was given as 0.1 molar. This is 0, this is 0. Now it's a strong acid, so completely dissociated. So this is 0. This will be 0.1 molar. Even this will be 0.1 molar. If I ask you, what is the concentration of H positive in the final solution? Concentration of H positive in the final solution is how much? 10 raised power minus 1 molar. If you got the concentration of H positive in the final solution, pH is nothing minus log of H positive concentration, which will come out to be 1. Minus log of 10 raised power minus 1 is 1. So this was question number 1. Similarly, question number 2. When you solve the question second, what you'll get? When you solve the question second, you get the pH of the solution as how much? You get pH of the solution as 3, right? Over here, if you look at this particular question, let's try to solve that. 10 raised power minus 7 molar HCl aqueous. Now try to understand what this is and remember this particular case. My dear students, when you introduce HCl into water, what you are going to get? This HCl will get 100% dissociated into H positive aqueous plus Cl negative aqueous, correct? Initially, its concentration is given as 10 raised power minus 7 molar. This is 0, this is 0. Now what is HCl? It's a strong electrolyte. It would have got completely dissociated into its ions, right? So this will be 0 now. 1 mole gives 1, 10 raised power minus 7 gives 10 raised power minus 7. Even this is 10 raised power minus 7. So when you introduce HCl into water, the concentration of H positives coming from HCl, the concentration of H positive coming from HCl is 10 raised power minus 7 molar. You got the concentration of H positive. Can you calculate its pH? It will be minus log of H positive concentration. Correct? The value comes out to be 7. But, if the pH is 7, then this solution has to be neutral. But this HCl, it's acidic solution, right? Its pH cannot be 7. Its pH has to be less than 7. My dear students, whenever you see this kind of the scenario, wherein pH of the acidic solution comes out to be 7 or greater than 7. Whenever you see such kind of the scenario in which pH of the acidic solution at 25 degrees centigrade comes out to be 7 or greater than 7. At that point of time, you have to take H positives from water into consideration as well. What does that mean? This is the concentration of H positive which has come from HCl, correct? But this HCl you introduce where? In water. Water is already a weak electrolyte. It would have also given some H positives. And you already know concentration of H positives generated from water at 25 degrees centigrade. That's also 10 raised power minus 7 molar. Now if I ask you, what is the net H positive ion concentration? Net H positive ion concentration is this plus this. So 2 into 10 raised power minus 7 molar. This is the net H positive ion concentration. If this is the net H positive ion concentration, now you are in a position to calculate pH. I would say pH of the final solution is equal to minus log of H positive net, right? Which is going to be minus log of 2 into 10 raised power minus 7. So minus times. This is going to be log of 2 plus log of 10 raised power minus 7. Log of 2 is 0.3. This will be minus 7. The value comes out to be 6.7. 6.7 is the pH of the final solution. Am I clear? Am I clear, people? Clear, guys? So do remember, whenever the pH of the acidic solution with our normal procedure, if we follow the normal procedure and if the pH comes out to be, pH of the acidic solution comes out to be 7 or greater or equal to 7 or greater than 7. At that time, you have to take H positives into consideration as well, which would have come from water. Okay, that is the point. That is the point. Now, similarly, let's have a look on one more question. 10 raised power minus 4 molar NaOH. You can solve this easily. NaOH. When you introduce this NaOH into water, since NaOH is a strong base, so completely dissociated into its ions, and these are its ions. Correct? So initially, its concentration is how much? 10 raised power minus 4 molar. This is 0, this is 0. Now it's a strong base, completely dissociated. So this has to be, This has to be 0. This has to be 10 raised power minus 4 molar. This has to be 10 raised power minus 4 molar. So, concentration of OH negative in the solution is how much? 10 raised power minus 4 molar. So, here I can calculate POH. P stands for minus log of 10 raised power minus 4. The value comes out to be 4. Now, you know, at 25, pH plus POH is equal to 14. Therefore, pH will be equal to 14 minus 4. The value comes out to be 10. So, pH of the final solution exactly comes out to be 10. Right? Correct, people? Simple? Yes? Right, people? I hope this sort of a question you can solve from now on. So this was how do we calculate pH of monoprotic acids. All right, let's say you've got this sort of question. It's again a strong acid, H2SO4. This H2SO4, when you would have introduced it into water, since it's a strong acid, so 2 times H positive plus SO4 di negative. Initially, its concentration is how much? 0.1 molar. This is 0, this is 0. Now, this will be 0. 1 mole gives 2, 0.1 gives 0.2 molar, right? This will be 0.1 molar only because 1 mole gives 1 mole, 0.1 gives 0.1. If you ask me what is the concentration of H positive coming from here, it is 0.2 molar, which means 2 into 10 raised power minus 1 molar. So, pH has to be equal to minus log of H positive concentration. Minus log of H positive concentration. So, minus. This will be log of M plus log of N. So, this has to be 0.3 minus 1. The value comes out to be 0.7 exactly. So, this is the pH of the final solution. Right? Got it? Similarly, you can check for this as well. You can check for this as well. You can calculate POH from here. It is just BaOH whole twice. It would be dissociated in the format of what? Ba di positive aqueous plus what? Plus 2 times OH negative aqueous. It is just you have to take care of stoichiometry here. It is just you have to take care of stoichiometry here. So initially this was 10 raised power minus 3 molar. This would be 0, this would be 0. Now it's a strong base, so 0, 10 power minus 3. 1 mole gives 2 moles. 10 power minus 3 gives 2 into 10 raised power minus. So this is the concentration of OH negatives which came from BOH whole twice. Now we can calculate POH, which is minus log of this particular value, right? Once you calculate POH, you can say pH is equal to 14 minus POH. Done, understood, right? Can be solved? 11.3, yes. 11.3, correct. Right? Perfect. Now, when you have got a mixture of 2 strong acids, understand. This is case number 1. Mixture of 2 strong acids, strong acid 1 and strong acid base. Strong acid 1 and strong acid 2. Mixture of 2 strong acids. Whenever you'll be having 2 strong acids, right, if you are mixing them, you'll be getting a mixture. You'll be getting a mixture. The point is, what is the pH of that particular mixture which you obtained upon adding 2 strong acids? Simple thing I'll tell you. Let's say normality of this solution is N1, volume of this solution is V1, normality is N2, volume of this solution is V2. So, net H positive concentration you will write like this. It is going to be N1 V1 plus N2 V2 divided by V1 plus V2. Once you get the H positive concentration, you can easily calculate pH minus log of net H positive concentration. This will give you the pH of the final solution. Simple. Simple. I'm not going to calculate millimoles, millimoles, etc. Let's do it in this way only. Let's do it in this way only. When you have got two strong acids, if you are adding two strong acids, you'll be getting a mixture. How do we calculate pH of the mixture containing two strong acids? Right? This is the way, this is the procedure of doing it. Correct? Similarly, case number 2, I'm giving you here. If you have got a mixture containing two strong bases, strong base 1 plus strong base 2, when you add them up, you get a mixture. How do we calculate pH of this particular mixture? How do you calculate pH of this particular mixture? Let's assume its normality is N1, which will be given. Volume is V1. This is N2. Volume is V2. Here you will calculate the net OH negative concentration. Net OH negative concentration here is going to be N1 V1 plus N2 V2 divided by V1 plus V2. Once you calculate OH negative concentration, you can calculate POH. Once you calculate POH, your pH is nothing but 14 minus POH. This is the procedure. This is the procedure case number 2. Okay, this is the procedure case number 2. Now case number 3. Case number 3. Imagine you have got strong acid and strong base. You are adding strong acid and strong base. How do I calculate pH of the final solution? How do we calculate pH of the final solution? How do we do it? Try to understand. Try to understand. Strong acid and strong base you are mixing. How do we calculate pH of the final solution? You can remember it like this. Let's say its normality is N1, volume is V1. Normality is N2, volume is V2. Volume is V2. First of all, if N1 V1, if mod of N1 V1 is equal to mod of N2 V2, right? If mod of N1 V1 is equal to mod of N2 V2, pH of the final solution is 7. The final solution is neutral. The final solution is neutral. The final solution is neutral. If mod of N1 V1 is greater than that of mod of N2 V2, if mod of N1 V1 is greater than mod of N2 V2, the resulting solution is acidic. How do I calculate net H positive concentration at that point of time? It's going to be N1 V1 minus N2 V2 divided by V1 plus V2. Once you calculate net H positive ion concentration, then you can easily calculate pH, which is minus log of net H positive ion concentration. The last case here, if N2 V2 is greater than that of N1 V1, if N2 V2 is greater than that of N1 V1, N2 V2 is greater than that of N1 V1, resulting solution is basic. So net OH negative concentration you can calculate as N2 V2 minus N1 V1 divided by V1 plus V2. Once you get OH net, you can calculate POH. Once you calculate POH minus log of OH negative, then you can calculate pH, which is 14 minus POH. Right? These are all the possible cases when it comes to what? When it comes to your strong acids, etc., etc. Okay? Am I clear, people? Remember all these cases. Remember all these cases. These are going to be super important. For example, you have got a question. Strong acid 1, strong acid 2. Strong acid 1, strong acid 2. Tell me one thing. On one side, you have got H2SO4. On the other side, you have got HCl. You are mixing them up. You will be getting a mixture. You have to calculate its pH. pH of the mixture. So first of all, if I ask you normality of H2SO4, normality of H2SO4, you know normality is equal to molarity multiplied by n factor. N factor of this is 2. So 0.5 into 2 will be 1. Its volume is 400 ml. Normality of HCl. Its n factor is 1. HCl's n factor is 1. So 0.5 only. Its volume is how much? 400. Right? I'll be getting the net H positive concentration here. The net H positive concentration is going to be what? N1 V1 plus N2 V2. Plus N2 V2 divided by what? Divided by V1 plus V2. Correct? All the terms are given. Then calculate pH, which will be just minus log of H positive net. Or you can solve it also. N1 into V1, that's 400. This is 200. So 600 divided by what? 600 divided by 800. So the value comes out to be 6 by 8. That means 3 by 4. 3 by 4. So pH is equal to minus log of 3 divided by 4, which is equal to minus. This will be log of 3 minus what? Minus log of 4. So log of 3 is 0.47, log of 4 is 0.6, the value comes out to be 0.13. So 0.13 is the pH of the final solution, right? 0.13 is the pH of the final solution. Correct, people? Sir, they are all chatting and irritating. Let them chat. They'll chat in the exam center as well. Okay? They'll chat there also. Don't worry. Let them chat. Perfect? Who is this Pinky? Pinky promise. You have come here to make friends with people. Huh? There's Instagram, WhatsApp, Tinder is there. Go there, right? Let people study here. Download Tinder. Huh? Or shadi.com something. Do that. It'll help you out. Make friends. Good friends. Anyone else here who has come to make friends? Can you let me know how this sort of a question will be solved? Can you check it out? Can you check it out, people, quickly? Strong acid, strong base, right? Its N factor is 2. So N1 will be 1. N1V1 is 400. Here N2V2 is 200. So N1V1 is more, right? So resulting solution is basic. So net OH negative will be 400 minus 200, that is 200. 200 divided by 800. So it is going to be 1 by 4. So POH will be minus log of 1 by 4. Log of 4 is 0.6. So POH is 0.6. If POH is 0.6, that means pH will be 13.4. So 13.4 has to be the answer of this question, right? Is that? Is that, people? You can give it a try. Perfect. I believe you can solve these sort of questions from now on easily. Now, let's move on. How do you exactly calculate pH of weak acids or weak bases? Right? Weak acids or weak bases. 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 Try to understand, guys. Assume that you have got a weak acid HA. You are introducing this weak acid into water and you are getting the ions which are in equilibrium with it. Let's assume the ionization constant of this weak acid is Ka1, degree of ionization is alpha. Let's say initially at time t is equal to 0, its concentration is C. This is 0, this is 0. At equilibrium, this is going to be C minus C alpha. This is C alpha. This is C alpha. Now, if you write the Ka expression, that has to be C alpha square divided by 1 minus alpha. If I assume alpha to be less than 0.05, at that point of time, 1 minus alpha is written as 1. So Ka is equal to C alpha square, and alpha is nothing but under root of Ka by C. First thing. Alpha is equal to under root of Ka by C. Now, if I ask you what is the concentration of H positive in the final solution, concentration of H positive finally is C times alpha. So alpha already I know, that is under root of Ka divided by C. So it has to be under root of Ka multiplied by C. Ka multiplied by C. Or I'll say H positive concentration will be equal to Ka multiplied by C whole raised power 1 by 2. So if you want to calculate the pH, pH is equal to minus log of H positive. So minus log of Ka multiplied by C whole raised power 1 by 2. So pH is equal to minus. This is 1 by 2. And then it's going to be log of Ka multiplied by C. So use a bit of calculation. This minus 1 by 2 log of m into n is log of m plus log of n. So pH will come out to be 1 by 2 minus log Ka means P of Ka minus log of C. So this is one direct result which you will be remembering from now onwards to calculate what? To calculate pH. pH of a weak monoprotic acid whose alpha is less than 0.05. Okay? This is a general formula which we got. Half of pK minus log C. This is a general formula with the help of which you can calculate pH of a weak monoprotic acid, right, whose alpha is less than 0.01. I mean less than 0.05. Similarly, if you will have the weak base of the same manner, you'll calculate pOH of that weak base. That will be half of P of Kb minus log C. Right? I believe it can be solved. Okay, can you solve one of the question out of the three? One question I'll solve. 10 raised power minus 3 CH3COH. Now you know CH3COH is your weak acid. It is your weak acid, correct? First of all, check its alpha. Alpha will be equal to under root of Ka by C. Ka is how much? 1.8 into 10 raised power minus 5. C value is 10 raised power minus 1. It will be 1.34 into 10 raised power minus 2. So alpha is less than 0.05. So I can use my formula. pH is equal to, it will be half of P of Ka minus log of C. Correct? So it's going to be half of P of Ka. Remember, if K is given as 1.8 into 10 raised power minus 5, do remember minus log of this value. Minus log of this value always remember as 4.74 because this will be frequently used in ionic equilibrium. Minus this particular value is always equal to 4.74, right? So this is 4.74 minus log of C, where C is the concentration of this acid. That's 10 raised power minus 1. Now it's just a matter of calculation. This is 4.74 plus 1. So 5.74 divided by 2. 5.74 divided by 2. So 2.87 is the pH of the final solution. Similarly, you can check for this. First, get the alpha value. Then check whether the formula is applicable or not. Get the alpha value, right? Check whether the formula is applicable or not. If the formula is not applicable, then use the general procedure, right? Dissociate the CH3COH. Write the Ka expression, C alpha square divided by 1 minus alpha, right? There you can calculate alpha. And accordingly, you can get the H positive concentration as C alpha. And finally, you'll be getting the pH. But in your NEET, they won't ask you those lengthy questions, right? They won't ask you those lengthy questions. They're not going to ask those lengthy questions at all. Got it, guys? Am I clear? Am I clear? Am I clear? Can you solve this question without using pen paper? Without using pen and paper, can you solve this? without using pen and paper. If you look carefully, you have got a strong acid, weak acid. Both will be having one ion in common, that is H positive. So what will be the concentration of H positive in the final solution? Concentration of common ion is decided by the strong electrolyte. So concentration, net H positive concentration will be 0.1 molar. If H positive concentration is 0.1 molar, minus log of 0.1, that will come out to be 1. 1 is the pH of the final solution, right? So directly use the common ion effect. You're done. Perfect? Directly you'll use the common ion effect. You're done. So guys, this is how, these sort of questions are asked in your NEET examination from the pH. Now I'm moving ahead. There is something called as salt hydrolysis. Salt hydrolysis. Guys, I'll take the break for 15 minutes first, okay? I just want to have a tea. Let's take a break for 15 minutes. Is that cool? Is that cool? After that, we'll finish it off, huh? Okay? Because I'm feeling dizzy. So let's take a break for okay, but be back. Everyone be back. These topics which I'm going to tell you now, they are super important, okay? They are super, super important. Be back on time. Chalo, I'll see you in some time. So are you guys back? Are you all back? Are you all back? Yes. The break is over. I'm feeling well. I'm feeling well. So finally the break is over and let's get into business. Let's talk about the salt hydrolysis, right? Guys, this is again one very important topic, salt hydrolysis, right? I'll show you all the types of the questions which can be asked from it. Number one. But before that, let's get to know first of all what the salt hydrolysis is all about. Okay, what the salt hydrolysis is all about. How do we define it? My dear students, if you look at this particular definition, salt hydrolysis, it's defined as the interaction of ions of salt, the interaction of the ions of salt with water to produce either acidic or alkaline solution. The interaction of ions of salt with water to produce either acidic or alkaline solution. What does that mean? For example, you have got a salt AB. Right? For example, you're introducing the salt into water. You know, in water already you have got H positives and OH negatives. What is going to happen? The ions of this particular salt, they are going to interact with water. For example, the first case 1. Let's say the cation of salt interacts with water. Imagine the cation of salt is going to interact with water. Now tell me, this cation, it is going to interact with either H positive or OH negative. What do you think? I'll say this cation is going to interact with what? This cation is going to interact with OH negative, right? This cation will interact with OH negative and will lead to the formation of AOH, and here you'll write H positive. Similarly, the anion of salt can interact with water as well. It can interact with the H positive of water. So it will form HB, and with that you'll write OH negative. The interaction of ions of salt, as I told you, the interaction of ions of salt with water to produce either acidic or alkaline solution is what you call a salt hydrolysis. Okay? This phenomenon is called a salt hydrolysis. Now, in the first case, as you saw, cation of salt interacted with water. Whenever cation of salt interacts with water, this hydrolysis is called as cationic hydrolysis. When the anion of salt is going to interact with water, this hydrolysis is what you call as anionic hydrolysis, right? This is what you call as anionic hydrolysis. Okay? Perfect. Now, first of all, what kind of different salts do we have? I hope you got the meaning of salt hydrolysis. The interaction of ions of salt with water to produce either acidic or alkaline solution. Okay? Now, my dear students, for example, I'm taking a salt CH3COONA. Right? So over here you have got CH3CO negative, Na positive. Can I say this CH3COO negative, can I say it would have come from CH3COH? And Na positive would have come from what? NaOH. And you know CH3COH is the weak acid, NaOH is the strong base. So can I say this CH3CONA is the salt of, I'll be calling it as the salt of weak acid and strong base. So this is the first category of our salt of weak acid and strong base. Number 1. Number 2. Let's say I'm taking NH4Cl. NH4Cl. Over here you have got NH4 positive, Cl negative. Can I say this NH4 positive would have come from NH4OH and Cl negative would have come from HCl? NH4OH is the weak base, HCl is a strong acid. So I'll be calling the salt as the salt of strong acid and weak base. Strong acid and weak base. Similarly, CH3, COO, for example, NH4, right? This one more salt. This is negative, this is positive. I'll say this CH3CO negative would have come from CH3COH. NH4 positive would have come from NH4OH, right? This is a weak acid, this is a weak base. So I'll believe this particular salt, it is going to be the salt of weak acid and weak base. It is going to be the salt of weak acid and weak base. In the similar way, my dear students, let's say you have got the salt NaCl. This is Na positive, Cl negative. Tell me this Na positive. Can I say it has come from NaOH? Cl negative has come from HCl. Both are strong. So this is the salt of strong acid and strong base. So first of all, this is how you identify what kind of salt is given to you. What type of salt is given to you? Is there the salt of weak acid, strong base, strong acid, etc., etc.? Right? This is how you identify. Okay? Now, after the identification of the salt, I'm directly going to make a table. Right? I am going to make a table. You need to remember this table because I'm going to write all the different types of formulas from which questions can be asked. My dear students, for example, you are taking the salt of, or just a second. Just a second. See what kind of questions can be asked. How many types of questions can be asked. Here I'm writing the type of the salt. Here I'm writing KH. KH is what you call as hydrolysis constant. Hydrolysis constant. Right? Here I'm writing H, which is called as degree of hydrolysis. Degree of hydrolysis. And here I'm writing pH. The first salt is going to be the salt of, for example, strong acid and weak base. If the salt of strong acid and weak base undergoes hydrolysis, if the salt of strong acid and weak base undergoes hydrolysis, how do you calculate the hydrolysis constant? How do you calculate degree of hydrolysis? How do you calculate its pH? Remember the formulas directly, right? Your hydrolysis constant is going to be equal to Kw divided by, which one is weaker component here? Base. So it is Kw divided by Kb. What is Kw at 25 degrees centigrade? You know, Kw at 25 degrees centigrade is what? That's 10 raised power minus 14. So this is the first question which will be asked. Calculate the hydrolysis constant of a salt which is basically the salt of strong acid and weak base. This is the formula which you'll have to use. Kb will be given to you. Kw value will be 10 raised power minus 14. I'll show you the question in some time. Number 1. Degree of hydrolysis H is equal to under root of Kw divided by C. Kw divided by C. Sorry, not Kw divided by C. Under root of Kh divided by C. Kh divided by C, which can be written as under root of. What is Kh? Kh here is Kw divided by Kb multiplied by C. What is C here? C is the concentration of this particular salt. C is the concentration of this particular salt. How do we calculate pH? How do we calculate pH? It is strong acid and weak base. Strong acid and weak base. So pH is going to be 7 minus. 7 minus half of. This is going to be P of Kb plus log of C, where C is the concentration of salt. These are the 3 questions which will be asked from this particular case. Right? These will be 3 questions. I'm not deriving these formulas. Right? We don't have that much of time. I'll just give you the results and I'll show you how to apply them. Number 1. Number 2. Salt of weak acid and strong base. Salt of weak acid and strong base. When the salt of weak acid and strong base undergoes hydrolysis, how do we calculate all these things? First, hydrolysis constant Kh. Hydrolysis constant will be equal to Kw divided by, the weaker part is acid here, so this is Ka, right? And Kw, you know, at 25 degrees centigrade, that is 10 raised power minus 14. Degree of hydrolysis H is equal to under root of Kh by C. KH here is under root of, KW divided by Ka multiplied by C. What is C? C is the concentration of this salt, right? And its pH. It is weak acid, strong base. So pH will be 7 plus. So 7 plus half of. This is P of Ka plus log of C. Plus log of C. Plus log of C. Similarly, the salt of weak acid and weak base. Salt of weak acid and a weak base. So KH here will be equal to Kw divided by Ka multiplied by Kb, number 1. H will be only equal to under root of KH, which will be equal to under root of Kw divided by Ka multiplied by Kb. And how do we calculate its pH? It is 7 plus half of, it is going to be P of Ka minus P of Kb. So these can be possible 9 types of questions which can be based on the salt hydrolysis. And remember, the salt of strong acid and strong base, it does not undergo hydrolysis. Salt of strong acid and strong base, it does not undergo hydrolysis. Right? It does not undergo hydrolysis. Okay? I would want you guys to take the screenshot of this particular slide. I'll show you what kind of question can be asked. So, first of all, you just have to identify the salt. Accordingly, you'll have to use the formula. That's it. Identify the salt and apply the identify the salt and use the formula. I did not derive any formula. Okay, I just gave you the formula directly. For example, this is one formula-based question. It's one formula-based question. Calculate the degree of hydrolysis and pH of the solution obtained by dissolving 0.1 moles of CH3CONa. So the salt given is CH3CONa. Perfect. So first of all, you need to identify the salt. This is the salt of what? This is the salt of weak acid and strong base. What all things do we need to calculate? We need to calculate degree of hydrolysis, pH. So first of all, if I have to calculate KH here, hydrolysis constant, that will be equal to Kw divided by Ka. The second thing, I'll be calculating degree of hydrolysis under root of Kw divided by Ka multiplied by C. Third thing, pH. pH is going to be, it's weak acid, strong base. So 7 plus half of P of Ka plus log of C. So these are the 3 questions which have been asked to us. These are the 3 questions which have been asked to us. First of all, you have got 0.1 mole of salt in 100 liter of solution. So what is the concentration of salt? It will be moles of salt divided by volume of solution in liters, right? So it's going to be 10 raised power minus 3 molar. So you got the concentration of salt. Kw, as you all must be knowing, I have told you already, 10 raised power minus 14. Ka is given to us as 2 into 10 raised power minus 5. Matter of calculation. Do it, right? Get the KH value, number 1. Number 2, it's going to be under root of Kw is 10 raised power minus 14. Ka is given to us as 2 into 10 raised power minus 5. Concentration of salt C. Concentration of salt, you know, that's 10 raised power minus 3. Perfect. Solve it. Get the value of hydrolysis constant, degree of hydrolysis here. In the similar way, how do we calculate pH? It is 7 plus half of. P stands for minus log of Ka, minus log of 2 into 10 raised power minus 5 plus log of C. What is C? C is the 10 raised power minus 3. Again, just the calculation is needed and you can solve this question. Right? Perfect. Perfect, guys. So these can be formula-based questions which can be asked from salt hydrolysis, right? You just need to identify the salt. Accordingly, you can do all the things. Okay. For example, there is one more question, similar type of question. Identify the salt and calculate the pH. You just have to use the formulas. That's it. That's it. That's it. Okay. Now, some good questions on salt hydrolysis can be only solved if we study the buffer first. So let's try to understand buffer. Let's try to understand what buffer exactly is, then we can collaborate buffer with salt hydrolysis. Okay. My dear students, what is a buffer exactly? These are the solutions whose pH does not significantly change upon the addition of small amount of acid or base into them. So you have got some solutions, if you introduce small amount of acid or base into them, their pH won't significantly change. So basically they show resistance. They show resistance towards the change in pH. Basically they show resistance towards the change in pH, right? There are some solutions which show resistance towards the change in pH. There are some solutions in which if you add small amount of acid or base, their pH does not significantly change. You call those solutions as the buffer solutions, right? Now, the types of buffer, you have got simple buffer, you have got mixed buffer. Simple buffer, mixed buffer. What is simple buffer? Simple buffer is made of single substance. For example, if you take the salt of weak acid and weak base, let's say you are taking the salt of CH3CONH4. This is the salt of weak acid, weak base. It is going to behave like a buffer. It is going to behave like a buffer. Number one. Number two, you have got mixed buffers. Mixed buffers, you have got more than one component, right? Two components in total. These mixed buffers we further classify into two types, which actually we have to study. Acidic buffer and basic buffer. Acidic buffer. How this acidic buffer is made? How this acidic buffer is made? My dear students, if you take a weak acid, and you take the salt of same weak acid which it has formed with a strong base. This mixture which you get, this is something which you'll be calling as acidic buffer. For example, let's say you are taking CH3COH, and you are taking, for example, CH3CONA. This is a weak acid and this is the salt of same weak acid with a strong base. So I'll be calling this particular mixture as the acidic buffer. So this is your acidic buffer, number one. Number two, how do you make the basic buffer? You take a weak base and you take salt of same weak base with a strong acid. For example, here you have got NH4OH. It's a weak base. What is the salt of this weak base with a strong acid? For example, you take NH4Cl. Weak base and the salt of same weak base with a strong acid. This mixture is something which you call as basic buffer. So first of all, you should be able to identify an acidic as well as the basic buffer, right? Right, people? Is it clear? So first of all, you need to identify how to check whether the mixture is the acidic buffer or the basic buffer. So remember, weak acid and the salt of same weak acid with a strong base, it will give you acidic buffer. Weak base and the salt of same weak base with a strong acid, it will give you the basic buffer. Now, I'm not going into the mechanism and stuff. You just need to know how to calculate pH of acidic buffer. How do you calculate pH of acidic buffer? There is a result for that, pKa plus log of concentration of conjugate base divided by acid, or I'll directly say concentration of salt divided by acid. This is how you calculate pH of the acidic buffer. Similarly, if you have got the basic buffer, how do you calculate its pH? Its pH is calculated as pKb plus log of concentration of salt divided by base, right? Sorry, this is not pH here, this is pOH. You can remember these two results by means of which we can calculate pH and pOH of acidic and basic buffers. Now, people, I'll let you know what kind of questions are asked and how do we approach them. First of all, you have to remember these two. This is how you calculate pH of acidic buffer. This is how you calculate pH of basic buffer. So let's try to solve certain questions with the help of which you'll get to know exactly, right, what kind of questions are asked. First, I'll start with a basic question, a complete basic question, a formula-based one. Calculate the pH of 1 liter solution containing 0.01 molar CH3COH. So CH3COH 0.01 molar with CH3COONA right? 0.02 molar. Perfect. If you look at this, identify first of all, which kind of buffer is it? Weak acid, salt of same weak acid with a strong base. So it is the acidic buffer. It is the acidic buffer. How do we calculate pH of the acidic buffer? It is P of Ka. P of this value minus log of this value is 4.75. 4.74 plus log of concentration of your salt here is 0.02 divided by concentration of acid is 0.01. So it becomes log of 2. Log of 2 is 0.3. So 4.74 plus 0.3 makes it 5.04. So pH of the final solution is 5.04. Number one. Number one. Number one. Okay. This was a formula-based question. Now understand what kind of questions can be asked. Before solving the questions, there are few things which I would want to know. My dear students, whenever in a question you get stuck, whether to use the formula of a buffer or formula of salt hydrolysis for the calculation of pH, whenever you get confused, that whether we should use the formula of buffer to calculate pH or formula for salt hydrolysis to calculate the pH, give priority to buffer. As simple as that. Give priority to buffer. Okay, number one. Number one. Okay, I hope this is clear. Number two. If you get confused whether to use salt hydrolysis formula or strong acid formula, give priority to strong acid. Salt hydrolysis, strong base. Give priority to strong base. Why am I telling you all these things? Just have a look. Why am I telling you all these things? Calculate the pH of the solution obtained on mixing 100 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. So basically you are making CH3COH to react with NaOH, acid plus base, which will lead to the formation of salt and water. So this is CH3CONa, and with that you'll write water as well. So this is going to be the reaction that's going to happen first of all. You are going to react, acid and base is going to react in a container. It will lead to the formation of salt and water, right? Right, people? Now, initially at time t is equal to 0, if I ask you how many millimoles of CH3COH do we have, how do we calculate millimoles? Molarity multiplied by volume in ml. Molarity multiplied by volume in ml. So this multiplied by this will come out to be 10. So initially we have 10 millimoles of CH3COH. How many millimoles of NaOH do we have? This multiplied by this, again 10 millimoles, right? So this will be 0, this will be 0. Now, is the reaction balanced? Reaction is balanced, yes. Reaction is balanced. Now, my dear students, which concept am I going to use here? I have told you in the last session, whenever in a question you are given with the amounts of all the reactants, you use the concept of limiting reagent. Now, if I ask you which one is limiting reagent among the two, you will say this is the case of complete neutralization. 10 by 1 is 10, 10 by 1 is 10. So this is the case of complete neutralization. This is gone, this is gone. So this will be 10 millimoles. Even this will be 10 millimoles. So check at the end what is left in the container. At the end, what is left in the container? You have got the salt and water, which is left in the container. Salt and water. Salt and water. And you know salt plus water. What it does? Salt hydrolysis. So which formula you'll be using here to calculate pH? You'll be using the formula for salt hydrolysis. Right? Now, which salt is it? It is the salt of weak acid and strong base. Weak acid and strong base. So 7 plus half of, it is P of Ka plus log of C, where C is the concentration of salt. So it's going to be 7 plus half of P of Ka. P means minus log. Minus log of this value is 4.74. Minus log of this value is 4.74 plus log of C. C is the concentration of salt. How do we calculate concentration of salt? These are the millimoles of salt finally left in the container. Divide by total volume. Total volume will be 100 plus 100, 200, right? So 10 divided by 200, you got the concentration of salt, right? Now it's again a matter of calculation, and over here you can get the pH of the final solution, which is asked, right? This was question number 1. This was question number 1. Let me solve one more question so that you get the idea properly. See guys, again the similar type of question, your CH3COH. Your CH3COH, you are mixing it with NaOH and it is going to form the salt and water. It is going to form the salt and water. It is going to form salt and water. Now, first of all, you tell me, how many millimoles of CH3COH do we have? Molarity into volume in ml. So 10 millimoles. How many millimoles of NaOH do we have? This multiplied with this, 5 millimoles. So initially this is 0, this is 0. Now, which one is the limiting reagent? 10 by 1 is 10, 5 by 1 is 5. So this is limiting reagent, completely exhausted. How many millimoles of CH3COH are left in the container? 5. This 5 has got formed. Similarly, 5 has got formed. Now, my dear students, finally, after the end of the reaction, if you observe, this is salt and this is water. Salt and water. Salt and water, salt hydrolysis. Weak acid and its salt with strong base. In the same container, we have got weak acid and salt with strong base. So it's forming acidic buffer. So which one to prioritize? You'll be prioritizing buffer here. You'll be prioritizing buffer. Now, which formula you'll be using to calculate pH? You'll be using buffer formula, which is, what is that? That is P of Ka, since it's acidic buffer, P of Ka plus log of your concentration of salt divided by your concentration of acid. Correct? So your pH is equal to P of Ka minus log of this value, that is 4.74, plus log of, what is the concentration of salt? Concentration of salt means millimoles of salt divided by total volume. So millimoles of salt is this, total volume is how much? 50 plus 100, that's 150. So it is 5 divided by 150, whole divided by concentration of acid, millimoles of acid divided by total volume, which is again 5 by 150. So this term cancel, log of 1 is 0. So the final answer of this particular question will come out to be 4.74. Did you get it? Is it clear? Is it clear, guys? Is it clear? Is it clear to everyone? Quickly. Quickly, people. Look at one more similar type of question. Similar. I'm just changing the values and accordingly your questions are changing. Simple changing the values, your questions are automatically changing. Otherwise, the reaction is same. In this question also, your CH3COH, you are making it to react with NaOH and it's leading to the formation of CH3CONa. And with that, you are writing water as well. So initially at time t is equal to 0. How many millimoles of CH3COH do we have? 0.1 multiplied by 50 is 5. 5 millimoles. NaOH, how many millimoles? This multiplied by this is 10. So 10 millimoles. So this is 0. This is 0. Now which one is limiting? This is limiting. So 0. This is 5. This is 5. This is 5. Correct? Now if I ask you, finally, when the reaction ended, right? When the reaction stopped, what all things you are seeing are left in the container? There is no weak acid in the container. There is a strong base left. There is a salt. There is water as well. Now, you know, salt plus water will give rise to salt hydrolysis. But if you look carefully, it's a strong base which is left. Strong base. I told you, strong base plus salt hydrolysis. Which one to prioritize? Strong base. So, entire pH will be decided by the strong base NaOH. Right? How many millimoles of NaOH are finally left in the container? 5 millimoles of NaOH are left in the container. This NaOH, it's a strong base, completely dissociated into its ions, right? Completely dissociated into its ions. So tell me, how many millimoles of OH negative are finally in the container? How many millimoles of OH negative are finally in the container? 5. What is the net OH negative concentration? Final OH negative concentration. Millimoles of OH negative divided by total volume. Total volume is how much? 150. The value comes out to be 1 upon 30 molar. Right? Now you just need to calculate POH, which will be minus log of OH negative concentration. And once you calculate this POH, you can automatically get the pH value, which is 14 minus POH. I hope this is also clear to every one of you. I hope this is also clear to every one of you. Right? Perfect, guys. Is it clear? Is it clear? There is one last topic which is left in the chapter, that is your salt hydrolysis. Sorry, that is your solubility product. And see exactly how questions are asked from solubility product and how they are to be solved. This is a simple topic, you should know it. Right? You know it already. See guys, directly I'm showing you the question by means of which you will understand how do we solve the questions based on your solubility product. Understand. As per the question, if I talk about MgOH whole twice, MgOH whole twice, right? Tell me, what will be its ions? Mg di positive plus 2 times OH negative. Correct? As per the question, if you look carefully, your solubility product of MgOH whole twice is given as 3.2 into 10 raised power minus 14. What are we supposed to calculate? We are supposed to calculate the solubility of MgOH whole twice in water. Now guys, if it is solubility is S, 1 gives 1, so S gives S, 1 gives 2, so S gives 2S. And how do we write the expression for KSP? Expression of KSP is written as concentration of Mg di positive raised power stoichiometric coefficient, concentration of OH negative raised power stoichiometric coefficient. So KSP is equal to, what is the concentration of Mg di positive? It is S. What is the concentration of OH negative? It is 2S. 2S raised power 2. So 4S square means 4S cube. So S over here can be written as KSP divided by 4 whole raised power what? Whole raised power 1 by 3. And what is KSP here? KSP is given to me as 3.2 into 10 raised power minus 14 divided by 4 whole raised power what? Whole raised power 1 by 3, which will come out to be 8 into 10 raised power minus 15 whole raised power 1 by 3. The final answer is going to be 2 into 10 raised power minus 5 moles per liter. So this is the solubility of MgOH whole twice in water. Right? Is it clear? These sort of basic questions, my dear students, are asked in your NEET examination when it comes to solubility. Right? When it comes to solubility, number 1. Number 2. Remember mercurous chloride, Hg2Cl2. 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 How it undergoes dissociation? You have to remember this one, okay? It undergoes dissociation as Hg2 di positive plus 2 times Cl negative. Hg2 di positive plus 2 times Cl negative. Calculate the solubility of mercurous chloride if its KSP is given. Again, KSP is given, you have to calculate solubility. Can you do it? Can you do it? If its solubility is S, this will be S, this will be 2 times S, correct? So if you write the KSP expression, it is going to be solubility of this is S, solubility of this is 2S, 2S ka square is, this will be 4S cube finally. So S will be again KSP divided by 4 whole raised power what? Whole raised power 1 by 3. So KSP is given to us 10.8 into 10 raised power minus 23 divided by 4 whole raised power 1 by 3. So it will be how much? 27.8. Is that? 2.7, sorry. Or you can write it like this. 108 divided by 4 into 10 raised power minus 24 whole raised power 1 by 3. This is 27. 27 raised power 1 by 3 is 3. So 3 into 10 raised power minus 8. This will be moles per liter. I hope this is clear. I hope this is clear. Right? I hope this is clear. Now guys, one more. Calculate the solubility of silver phosphate. I'll calculate in moles per liter. Okay, leave it. Calculate the solubility of silver phosphate in moles per liter. Calculate the solubility of silver phosphate in pure water. This is the first question. So when you put silver phosphate Ag3PO4 into pure water, this is how it's going to give 3 times Ag positive aqueous plus PO4 tri-negative aqueous. Correct? If its solubility is S, this will be 3 times S, this will be S. Okay? Correct? So if you write the expression for KSP, it is going to be it is going to be concentration of Ag positive raised power 3. So 3S raised power 3. Then it's going to be multiplied by S. So KSP here is going to be 3393, 27, 27 S raised power 4. So S from here will be equal to KSP divided by 27 whole raised power 1 by 4. Now, what is KSP here? What is KSP here? KSP is 2.7 into 10 raised power minus 23 divided by 27 whole raised power what? Whole raised power 1 by 4. Perfect. You can make it as 10 raised power minus 24, 27 cancel. So 10 raised power minus 24 whole raised power 1 by 4, which comes out to be 10 raised power minus 6 moles per liter. Right? Is that clear? Is that clear, people? Similarly, if you look at the second question, calculate the solubility of Ag3PO4 in what? In a solution that contains AgNO3. In a solution that contains AgNO3. See, this is the salt of NO3 negative, and I've told you salts of NO3 negative, they are water soluble, and all the water soluble salts are strong electrolytes, right? So this will be Ag positive aqueous plus NO3 negative aqueous, right? Similarly, this Ag3PO4, how it's undergoing dissociation? 3 times Ag positive plus PO4 tri-negative. This is something which you know. So this S, this is 3S, this is S, correct? What is the concentration of AgNO3? It is 0.02. Initially, this will be 0, this will be 0. Now this is 0, this is 0.02, this is 0.02. My dear students, do you see one thing? Do you see you have got weak electrolyte, strong electrolyte, both having one ion in common? So which effect you are going to operate? Common ion effect. Due to which this particular reaction will shift in the backward direction. So its solubility will decrease, right? Solubility will decrease in such a way that you can neglect solubility. So the concentration of Ag positive, finally you can write as 0.02 molar. Right? 0.02 molar. Now after this, what am I supposed to calculate? Solubility. Solubility of Ag3PO4 whole twice. Sorry, Ag3PO4 in AgNO3. If I write the KSP expression, it is going to be equal to concentration of Ag positive whole raised power stoichiometric coefficient, concentration of PO4 negative raised power 1. KSP is given to me as 2.7 into 10 raised power minus 23 divided by, this will be 2 to 4 to 8, 8 into 10 raised power minus 6 is equal to S. Solve this and get the answer exactly in moles per liter. This is the solubility of Ag3PO4 in AgNO3. This is the solubility of Ag3PO4 in water. I believe it's clear. I hope this is clear to everyone. Right, people? Is it clear? Is it clear to everyone? Quickly. Yes? I'm giving you one homework question. And with that, we are done with this chapter as well. Perfect. So this is your homework question, which you need to do on your own. So we are left with one topic, that is thermochemistry. And I think I'm done, guys. I'll be posting you a link of thermochemistry in the comment section. That will be for 2 hours. Right after the session, watch that. Okay? Right after the session, watch that. Or let me show it to you. Where will you find the thermochemistry link? Just a second. Just a second. What is opening here? Arjit Singh is opening here. Unacademy NEET English. See guys, when you drag it down, you'll find a playlist here. 75 days, 75 chapters, right? In this one, I have taken one session of 2 hours, which was for thermochemistry, right? This one. Just watch this. Perfect. Right after the session, watch it. And complete the thermochemistry part as well from here. Because I'm super tired. Correct? I was not well also. Alright, so with this, your class 11th chemistry is done. With this, your class 11th chemistry is done. Right? In the upcoming days, I'll be coming up with one session in which I shall be discussing, like, that will be the complete revision of class, a complete revision of your chemistry. Complete revision of your chemistry. Right? There'll be one session which I'll be conducting soon. Complete chemistry revision. PDF I'll share you right after the session. It will take like 5-10 minutes to download the whole PDF and I'll share that with you. Okay? But do complete this part, please. Huh? This is the only topic which is left, that is thermochemistry part. Do complete it right after the session. Okay? Chalo then, with this I'll be taking a leave. I'll see you in the next session. Till then, you take care. Bye-bye. See you guys.